CNU Imprint. I'm the team captain, Nigel Armstrong. This is my third year on the team and second year as team captain.
I'm Austin Solar. I'm the safety pilot. This is my third year with CNU Imprint and first year as the team captain.
I'm Erica McLaughlin. This is my first year on the team and I serve as the payload technician.
My name is Bashir Davis. I'm the aeronautics pilot. This is my second year on Imprint and I have an SEL.
My name is Davis Catherman. I am the ground control station manager and the autopilot operator, and this is my second year on the team.
Morning, my name is David Cole. I'm a software sub-team member and I'm the interoperability specialist on the team, and I've been on this team for 2 years as well.
Hey, how's it going? My name is Deontay White. I'm the safety manager. I've been on this team for 3 years, but I've been attending this competition for 6 years.
My name is Cortland Lizer. I am the payload operator and it is my first year on the team.
So we're going to start off with a short introduction of the system itself. To start off, Bashir will talk about the airframe.
This is the ready-made RC Anaconda that we bought off the shelf. It is a twin boomer, a fixed pressable landing gear with a inverted V-tail. It has it's powered by a 15x6 prop. We decided to use packing tape to strengthen the wings and the fuselage for increased resistance against scratches and debris, as well as added longevity on extended flights and the testing. It is a newer aircraft compared to the aircraft we used last year, which was the X8. And we decided to use this for a multitude of reasons. It is an easier platform to launch and recover because the X8 uses a launcher-based catapult system and belly lands, where all we have to worry about is taking off and landing. It also has the clearance between the fixed landing gear and the belly fuselage, so we could use the increased payload and customize.
Okay, so as I said, I'm going to explain about the platform and everything that's going around.
Now to Austin for the sensors and.
They said it's our 9
So for our autopilot,
so that's different for
the Ardu pilot series.
that's an octocopter.
In addition to the gyros, accelerometers, and barometric altitude sensors, we added an airspeed sensor so we could get our airspeed relative to the air, ground, and a LiDAR so we could get precise altitude on takeoff and landing. Now for our power system, we chose two 4 amp hour, 4 amp hour, 4 cell LiPo batteries, put to an 8 amp speed compactor that gives us overhead.
The system we're using
that is hooked to a 800 kV 35 millimeter motor, to, as Bashir said, a 15x6 pressure propeller.
The autopilot allows us to easily control the plane using our ground control station software. The primary software we use is Mission Planner. It provides a heads-up display as well as an easy way to plan waypoint missions. It also allows in-flight retasking, and so therefore we can complete the emergent target task. We also, from the ground station, communicate to the plane with a 2.4 gigahertz RC link, which is held by the safety pilot, as well as a 900 megahertz telemetry link, and a 5.8 gigahertz data link, which is a ubiquity bullet to communicate to the payload computers, which will be talked about more in a moment. Also part of our ground control station setup is our interoperability server task system, and that will be described more by the remote control.
So this year the interoperability was handled through the use of a JSON server and several modules that allowed us to post and request data to and from the competition server. With this, we were able to use the framework Node.js that allowed us to complete the secondary task of the interoperability and achieve a threshold of a 10 hertz data transmit rate. At the same time, these modules allowed us to post a display that allowed us to display where the plane was in relation to key targets and where different tasks and targets were based on where the plane was. You can see here that we also displayed headings and artillery data that we were posting to the competition at the same time while we were in flight. And to talk more about SRIC and other tasks handled by the payload, I have Mr. Liza.
The payload ground station is responsible for controlling and maintaining the payload subsystems. These systems include the camera, the gimbal for the camera, the wireless for the SRAM system, and we will also work with the autopilot to capture images for the off-axis target. The ground station is also responsible for downloading all of the images from the plane for the actual intelligence task. And we will be post-processing this later manually rather than doing ADLC. And the computer will be working with the computer on the plane, and for more information on that,
Our payload system itself is controlled by a Raspberry Pi 2 model box. In the actual unit, we use a camera here, we use a G15 large plane shoe, and the camera itself actually is mounted to the system through a custom 3D printed gimbal. And the gimbal rotates on 2 axes. It helps us with the non-axis.
We have done so many tests.
Our payload computer itself actually communicates to the ground control station through a serial link. The serial link operates on a 5.8 gigahertz Wi-Fi connection. And the Wi-Fi connection is necessary because it actually helps us with the completion of the S-ray.
So that's an overview of our system. To talk about more about one of the most important aspects of the system is safety. So we're going to have Deontay talk more as our safety manager about what he does.
Well, as the safety manager, my job is to make sure that the team can efficiently get through the mission, but also safely as well. I also have to vigilantly observe the flight line, as well as make sure that all the equipment is safely stored and in the right place in order to complete the mission. Also, I have extensive knowledge not only on the hardware, but the software portions of the team as well. So I'm inside each part of the team. And as well as that, I have the master checklist as well as the go, no-go criteria. If we do not fit the go, no-go criteria, then we will not fly as it is not safe, and we put safety first here on this team. All of these pilots here, as well as the safety pilot, all of them are AMA certified, as well as they've been trained on the competition aircraft, as well as similar aircraft as well, and quadcopters as well. As well as they've been trained on different uses of batteries, such as LiPo and LiPe, which is lithium polymer and lithium ion batteries. They've been trained on the usage of the batteries. They've been trained on the charging of the batteries, as well as the storage of the batteries to make sure that they're safe and stored in fiberglass batteries. When it comes to the competition, if there are any malfunctions inside the aircraft, we have a triple redundancy system. I'm more in the triple redundancy system.
So the Pixhawk comes with a multitude of redundancies built in. One of the main is that it has an I/O coprocessor. This allows for, if the main processor stalls because of some bug in the code, the I/O coprocessor can allow for us to continue manual control even in the failure of the autopilot. And that allows for a nice backup system. And the autopilot has a lot of fail-safes built in. Of course, we have the 3-minute flight termination that's required by the competition. So if we lose communication for 3 minutes, but we also have additional fail-safes in the event of smaller loss of connection. So if we lose our safety link after 10 seconds, we go into circle mode. After 1 minute, we'll return to launch, and after 3 minutes, terminate. And similar fail-safes exist for loss of communication to the ground control station. So these fail-safes work together with our redundancies to make a safe aircraft. And that's really important to us. And one of the biggest ways we're able to ensure safety of our aircraft is through extensive testing, because if you haven't tested it, it's not safe. So to talk more about our testing procedures, Mr. Catherine.
So we use a 3-tiered testing system for all of our testing. Everything begins with a unit test by the subsystem by itself, the individual item. If that requires the plane simulation software to simulate it, then we will be running that with the testing. We'll develop test cases specifically for the code, and only once passing all those will it go on to integration testing. And with the integration testing, it will be integrated usually with 1 or 2 more subsystems that are relevant to it. And from there, they will still have some simulation, some hardware in the loop, and more bugs will be worked out and more kinks will be fixed. And upon passing those tests, it will go to the full system test. The full system test has 2 stages. first the ground state, where we test the entire system on the ground in a nice safe location, and upon passing that, if we then proceed to a flight test with the entire plane configured and flying to test the system. A prime example of our testing systems is our camera startup script code last year. We found that there was a bug in our camera startup script that if under specific conditions the camera would not boot properly and therefore not take pictures. So as a unit test for that, we made some regression tests to specifically target the bugs that were encountered with that specifically. And we tested them, we added more code to our unit tests, we tested them, we did some integration tests to test it with the Raspberry Pi, which will control it, as well as some of the ground station. And then we went to the full system test to test the full ground station, the entire plane put together, triggering cameras on the ground, and then we went to the flight test and were able to successfully gain images repeatedly over and over again. A good example of of the strength of the integration test is that we found that it would be useful to be able to control the camera via our Raspberry Pi over a serial connection and from the ground station. So we added that to it, so that way if there is a bug, we can check the status of it, and we can manually reboot it from the ground while the plane is flying. And we have tested that also on the full system scale. And then to talk about evidence of mission accomplishment is Mr. Schuler.
So we had a 2.5-week testing period where all of the code went through all of the processes the system listed, except for the flight phase. And then we took the plane to the flying field for 2.5 weeks straight. We performed 24 autonomous flights, totaling over 5.5 hours of flight time in full
Also, we had some guys
11 of these flights included the search area grid and using the camera to search through field.
what they were doing.
7 of these flights were actually intelligence, so took intelligence and then turned it back into maneuvering the aircraft. Emergent target, we tested 7 times, retasking the plane in flight. We did 14 different tests with the interoperability server running and with the competition server.
Pretty much just every
We
single
did 5 flights with the S-RIP,
also for
put a router out in the field and tested that.
the problem that we might
We
have.
did 5 flights doing off-axis target from within a
Loss,
defined area.
loss so much.
Yeah, and a lot of this mission accomplishment, not all of these tests were successful. So we did attempt 24 autonomous flights. Not all of those flights included autonomous takeoff. By the end, we were able to have about two full mission tests where we tested every system and conducted a full mission, attempting all tasks we would attempt this year at the competition. And a big part of our missions are the pre-mission brief. It's very important to us to ensure part of our safety is the pre-mission brief. So the big parts of the pre-mission brief are me as the team captain. I make sure that all of my team members understand what we're attempting at this mission. So what tasks we're attempting, because oftentimes we're not attempting all tasks of the mission. We're focusing on any issues we had in previous attempts. We'll talk about what issues we had, what corrective actions we're taking, and where our focus areas are, where we're looking to improve, and any safety hazards that may arise during that day's flight mission. So I think overall, it's very clear that Team CNU Imprint is ready for this year's competition. We have evidence of our success, and we're able to fly safely, and we will be able to complete the autonomous flight task, including autonomous takeoff and landing. We'll be able to do the search area task. We'll be able to complete actionable intelligence. We'll be able to do the emergent target. We'll be able to complete interoperability, including the interoperability secondary task. We'll be able to complete the SRIC task and the off-axis target.
And it's
Thank you.
built from ourselves. And the software is also from.
My name is Ritvik Agarwal, Captain for Team Aurora. We are here to represent Indraprasth Institute of Information Technology, Delhi, India. So this is our first participation in AUVSI SUAS, and we are 7 members in the team with our backgrounds in computer science and engineering and electronics and communication engineering. So we have 4 members here representing the team. at the on-site competition. Myself, the team captain, Aditya Jain, the vice captain, Mandeep Singh, our backup pilot, and Manshu, our system support. So 3 others, Vijay, Siddharth, and Tushar couldn't get to the venue. So we're using a fixed wing aircraft this time, and so basically this is our thing. And he's our advisor, Mr. Preet. He's also our safety guy. So now Mandeep and Manshu will kick off the FRR with the description of the airframe.
Hello, good morning everybody. My name is Mandeep Singh. I have been working in the autopilot and ground station team, and also I'm the backup pilot for the team. So,
Hi, I'm Manshu. I'm responsible for all systems and flight readiness.
so we'll start with the description of our airframe. This one is a Skywalker 1900 wingspan. Due to its large wingspan, we can get a huge lift and stability. Through which we can actually get our huge capacity batteries and electronics and a longer mission time due to our huge capacity batteries. So the assembly of the split fuselage design works very well in order to place the wires and the equipment straightforward. During the assembly, the plane was in 2 half pieces, and we can actually see the designs. The wires are going just inside the fuselage and behind. One minor drawback was that the motor has to be mounted perfectly for permanently. That means it has to be glued inside, but we have tricked it, and we have actually made the motor mount such that we can actually remove the battery, remove the motor, and replace it. So our wings have a conventional airfoil. That means it has a maximum width at the 25% of the chord length, and that provides actually high lift and low speed as compared to the laminar airfoil, where the maximum width of the wing is at the 50% of the chord length. Now, high wing area and the wingspan provides us a good glide ratio.
We have used 550 watt and 1050 kV rating motor with a combination of 9x6 propeller. This backsoft motor shows that it can extract 34 ampere crank at its full throttle. So for safety measures, we use an ESC of 50 ampere earlier, but it shows the problem of heating up. So we tried an ESC of 60 ampere, and the problem of heating up gets resolved. We also used 4 9-gram servos to control ailerons, rudder, and elevator. We use transmitter receiver pair of 2.4 GHz frequency. We have checked its range up to 1 kilometer. Our receiver and autopilot picks up are both SUAS compatible. During the autonomous flight, the receiver and autopilot communicate via SUAS communication.
Now Aditya Jain will introduce the autopilot module that we are using.
Good morning, cadets. Myself Aditya Jain, Vice Captain of the team. I've been working in the autopilot module, and I'm also the ground control station operator. I'm also responsible for interoperability, which is the data communication between the ground station and the server. The team has been using the Pixoc autopilot system. It is an advanced autopilot system designed by the PX4 and the RD-Pilot community. It is an open source and an open hardware project. It contains an array of sensors which includes the GPS, compass, accelerometer, barometer, magnetometer, and gyroscope. The team had done a lot of research to choose the most appropriate autopilot system for the team. Among those which were compared includes the Navajo Plus, Pixoc, and the Early Brain. Pixoc was chosen among these on the following grounds. Pixoc RD-Pilot has a strong and well-established online community and discussion forums. A low complexity of the system setup as compared to the rest, satisfies our budget constraints, and the most important thing, it helps us to achieve all the mission capabilities required in this competition. The team uses Mission Planner and open source software for the ground station. It is a fully featured ground station application developed for the RD-Pilot open source project. It allows us to run the Python scripts to communicate with the server. Compatibility with the Pixoc, sensor tunings, and GUI-based mission planning makes Mission Planner the most appropriate ground station for the team. It also allows us to do the in-flight retasking for the emergent target tasks. we would be uploading a new waypoint file which would be having the emergent target coordinate to the PICSOC while the aircraft is in air. The aircraft will assume the flight with the new waypoint file. Also, to ensure that the aircraft does not go out of the no-fly zone, we have used the geofence feature of the mission planner. If there is a geofence breach, the aircraft will come in the guided mode and it will return to the nearest waypoint inside the fence. The most important thing, considering the safety of the equipment and the risk factors involved in flying a UAV, we have done a complete simulation of the flight, which includes the takeoff, landing, waypoint navigation, as well as tuning of the various autopilot parameters before actually sending the aircraft in the air. We first did the HITL simulation, which stands for the hardware in the loop, which requires the PICSOC in the simulation. We later switched to SITL simulation, which stands for software in the loop simulation. As the name suggests, it only requires software in the simulation. It simulates the plane, the flying environment, as well as the PICSOC. It reduces the dependency of the autopilot board, thus we can simulate anywhere and any point of time even without the PICSOC board. It's been implemented by installing the MAF proxy, which is the command line based ground control station, and the SIGWIN, which installs the libraries to build the autopilot on Windows. We do exhaustive simulation before any new feature is being tested in air. The team will be performing a complete autonomous flight, which includes auto takeoff, waypoint navigation, as well as auto landing. The team has done 40 autonomous flights, which includes 28 complete autonomous flights, which ensures that we are quite confident in doing a well-structured, successful autonomous flight. For the search area task, the UAV had to cover a long mover pattern in the search area such that there is sufficient overlapping of the aerial imagery collection so that there is no missing of the target flying on the ground, but at the same time optimizing the flight time. Thus, the search area was implemented using the auto-grid feature provided with the mission planner, which generates the waypoint in a long mover pattern. Now, Mandeep will continue.
I would like to talk about the frequency that we are using to communicate between the autopilot and the ground station. We are using a 915 MHz radio transmitter and receiver for the communication, and we are using the cloverleaf antennas 5 dB. The gain of this antenna is 5 dBi. We have tested its range up to 500 meters in the autonomous mission, due to its circular polarized capability, it actually rules out the need for the antenna tracker for this system at least. Now I would like to talk about the placement of our components. The PICSOC is actually placed just, this is the larger compartment, this is the smaller compartment just inside, beneath these wings. And that the PICSOC is placed inside this due to the center of gravity, its close proximity to the center of gravity. And also the GPS compass is placed on its GPS mast so that it's away from the interference from the ESC, the video transmitter, and the high current. Also, it actually gives the exposure to the sky for a better GPS log. Also, in order to ensure the safety during the flight, autonomous flight, the throttle has to be armed both via the ground station as well as the safety switch. If any of this, if any of the ground station or the safety switch is disarmed, the plane will not be armed. Is deactivated, the plane will not be armed. Now we'll talk about the fail-safes. We have configured fail-safes for RC, GPS, and telemetry fail-safe. The radio control, after 2 seconds, let's say the radio control is braked up, it will go into circle mode, and after 20 seconds it will come back to its launch position. Also, in order to ensure the safety of the team personnel, the team pilot has to fill out a safety check form that we have made on Google Forms in order to assure whether the battery voltage is appropriate, whether the configuration of the functioning of the servos is appropriate, and the direction of the motor is appropriate. Now, I would like to talk something about our imagery system that we are using here. In order to take a real-time video, we are using a 1-port video transmitter that is just beside it. 1-port video transmitter, and we are using a 7-turn 11 dBi helical antenna. Since the beam width of it is very less, it needs to be pointed towards the UAV manually. And the frequency rating of this is 5.8 GHz. We are operating it on 5.8 GHz. And also the minimum OSD board installed in the UAV allows the real-time telemetry data from the PIXWalk embedded on the video. Also, we can access it on the head-up display on the mission planner, the real-time video.
We are using Canon IXS 160 camera for collecting imagery data for search area task. It is powered by a 3.6 lithium-ion battery. It is 20 megapixel camera with optical zoom capacity of 8x and digital zoom capacity up to 32x. We hacked that camera via CHTK firmware, Canon hack development kit firmware. We write scripts in UBasic so that it can click photographs at regular interval of 2.4 seconds. For robustness, we also add a 5 megapixel camera connected with RFI, which we write scripts to click photographs at a regular interval of 1 second. We power RFI via 2700 mAh Vivo battery, which is also powering the video transmitter.
Yes, I'm back again. So I'm working on the computer vision module, and I'm going to operate the image processing ground station perfectly. So the primary input to the station is going to be the aerial imagery that we get from the Canon camera, because it's a high resolution. It has a high resolution of about 20.1 megapixels. So for the search area and emergent target tasks, we have created a command line utility that prompts us for entering or choosing the target characteristics and crop the thumbnails and arrange these characteristics and the thumbnail in a format that is compatible with the interoperability that has been provided by the competition. For the actionable intelligence, we are using the same utility, and we are dependent on the video feed that we get from this video transmitter, which is operating on the 5.8 gigahertz link. The auto detection task is happening on the Linux computer that we have, the image processing ground station that runs Linux, and so for that we are dependent on.
You can run the
you can just run it after this. So after we get the RGB.
2 minutes.
So after we get the RGB images from the Canon camera, the aerial imagery, we convert it to YCBCR color space. There we remove the grass, segment out the grass using histograms, and using the YCBCR histograms, we reject the wrong blobs, the false positive blobs. These ROIs are then input to the QR code decoder, and if something is detected, some QR code is detected, we report it and through the interoperability file, and otherwise we just input it to the secondary target checker. So yeah, and target files is updated, and I just
so Divine is running the script. I'll be talking about interoperability now, which is a primary task and a secondary task, both of them. The interoperability requirement has been met by transferring the HTTP package in the JSON format. The script was written in Python for the ease of coding. The team was successfully able to build the test server, and we were able to upload the UAS telemetry on the server. We tested it communicating via both Wi-Fi and Ethernet cables, with Wi-Fi giving an average rate of around 8.7 Hz, and LAN was able to give well above the objective level of 10 Hz. For uploading the UAS telemetry, the mission planner was integrated with the interoperability network using 2 Python scripts, which was provided by the SUAS organizers. One script runs outside of the mission planner, which uses the interoperability client to send it data received from the mission planner to the server, and one script which runs inside the mission planner sends the telemetry data to the client proxy. Also, we would be uploading both the target and its characteristics of the final target and the QRC over the interoperability network.
Last but not the least, I just forgot to mention the battery that we are using actually to power our plane. It's a 4-cell 5000 mAh depot battery. It's at the 50C version.
That's the end of the...
Good morning, respected judges. My name is Hanish Mehta. I am the founder and team captain for Michigan State University Unmanned Systems. I will also be serving as the air boss for the mission, and with me I have...
I'm John Lefevre, I'm the safety pilot.
I'm Kevin Dolinar, I'm the portable ground control station operator.
I'm James Young, I'm a remote video terminal.
I'm Matt Avenshine, I'm also on the remote video terminal.
I'm Charlie Guidarini, and I'm on the antenna tracker.
I'm Zachary Taylor, electrical engineering.
So just to give you a basic system overview, the maximum takeoff weight of the system is 6.16 kgs or approximately 13.3 pounds. The speed which we will be flying at during the mission is 6 meters per second. The range of our system has been tested to 1.5 miles, so we know for sure that it will work till that range. And the endurance has been tested to approximately 20 minutes based on weather conditions. Our crew members are extremely well trained because we have been flying since mid-March. With even Michigan weather, we have been making consistent flights every weekend, or at least trying our best to. We've had a few minor crashes, but we've still always recovered. And we've had approximately 30 plus autonomous takeoffs, which means 30 plus flights and 30 plus autonomous landings. Our testing commenced mid-March, which also provided us with extensive time to validate all the subsystems and make sure that everything is working in order. Our propulsion system was actually also placed on a vehicle of the first iteration of the vehicle, which was delivered to a department on campus. So we actually sold the product to a department on campus, and it has been in active service for almost a month and a half, and it's been used for commercial operations. So that also validates our propulsion system because we use the exact same propulsion system. And to talk a little bit about the pre-flight checks, I will let John take over.
Alright, so for our pre-flight, we have a checklist that we've made through our testing, basically to verify the mechanical integrity on the craft and all of our connections that we've led through our testing. We're learning what we, anytime we had a failure, we go back and see what we can add to our pre-flight checks to try and avoid that. Our main link to the aircraft is our radio transmitter, the UHF transmitter. Because it's the main link, the range of this is far greater than ground control station, because we want this to be the last link to basically go out of range, because it's the primary link. We have several different flight modes we're using with this. We can set it to autonomous mode. We can give it the command to come back and land with this or land in place, and we also have a last minute backup that it overrides the GPS and the written mission to fly it. Now to talk about the secondary link or ground control station.
So like John said, I'm the portable ground control station operator, and through the PGCS we're able to see the location of the drone, the speed, the altitude, the battery life remaining, what mode we're in, if we're on with the song. And basically the software we're using to plan the missions is Mission Planner. And to start off with testing the Mission Planner and our autonomous missions, we started going, flying about 30 feet high, doing simple box patterns, but as we progressed, we were able to move on to our surveying grid and go out farther and go out longer. Quite a higher altitudes. And I basically write the mission in this software, and I write the waypoints, and then it sends it to over here to the LRU system. The LRU system on the drone. The LRU system is designed for modularity and also simple weatherproofing. So for the modularity, we have a mil-spec connector on the back, so all are connected to just that harness right there, so we can unscrew that and pop a new LRU system in if we need to. And also, it's also a protective box, so basic weather conditions we will be okay. And then I'll let John talk about.
So the mounting of our flight computer inside. We've had some issues with vibrations, overloading the IMU, and that actually caused a crash. So we did some testing for vibration dampening. We used a shaker table to determine the best solution for mounting our Pixhawk flight controller, and we're currently using a 3D printed mount with rubber dampening balls and foam to provide adequate protection. And to talk a little more about the mechanical aspects, James?
Yeah, so as you can see with our frame, there's a little room to mount the battery, so we designed and 3D printed a battery holster. The batteries are Velcro strapped on the side here, and it's being held up within several standards. Above we have the RU, and below we have a composite conducting material which protects the autopilot and the RU from EMIs from the post below here. Since we designed this ourselves, we wanted to test for stress and deformation, which you can see here. We assumed for a large crash. So during a large crash, we noticed that there's a lot of deformation here, here, and here at the point of impact. But the deformation was only 3.4 times 10 to the negative 4 millimeters, which was very insignificant. But during flights, we noticed a bit of wobbling. So during post-flight checks, we took it apart and noticed a couple screws coming loose. So after that, we decided to throw everything on here. And since this takes up so much space, I'll let Matt talk about where we put the payload.
So for the payload, we stress modularity in our design. So we've created, we have two parts for our payload. We have our gimbal on the bottom. If you've read our report, you'll notice this is a different gimbal than the 3-axis gimbal we originally had. We have permission from Wayne to use this new gimbal. We've also provided a new proof of flight. We switched to a 2-axis gimbal and allow the yaw on the drone to be able to control that. This is connected to me in the remote video terminal, and we primarily use it as a first-person view for our safety pilot and also search for targets for those tasks. We also have for our payload mounting plate, use hook and loop Velcro so that we can easily take off parts and put them on for different mission configurations. Once again, stressing our modularity. The current configuration uses this clover leaf antenna for our FPV mission, and we also have a Raspberry Pi camera for our search area vision. I'll let Zach do it. Our payload computer is a Raspberry Pi. It's really stable platform. That's very resilient. Crash testing. Very hardy. We have that connected to our ground network. It's a Wi-Fi network. And our software basically is built to be resilient. Any data dropouts or lost connections or anything, it automatically reconnects between all the different components of our network and the interoperability network and resends any lost data so we don't lose anything. And this whole imagery network is separate from our flight and autopilot network, so a failure causes a crash. And let's talk about the actual validation of our imagery.
So our image recognition code was developed with a method called test-driven development, which essentially means you sit down and you figure out all the sections of your code, what order they need to run, and then you do each one at a time. Once you're done with one section, you then test it rigorously. Once you confirm that it works the way you need it to work, then you go to the next section. Doing this, it means your code is very robust from the very foundation, from the very start. And that's how we built this entire system. Right now, code, all you have to do is you hit start and it just checks a folder for an image. If the image isn't there, just keep checking it. And the way the scripts work is that the index image will always be in that folder before the next one, so there's never any latency. And so images that we get, had to test images taken from Google Images, because being Michigan, 7 months of the year you can't fly, so we had to use images from previous APVSI competitions in order to do the testing of each section in the initial stages. Although near the end, when spring and summer started, we were able to get our own camera working and take our own pictures, which was actually better because they ended up being higher quality, so my code ran off poor quality pictures. So now it's even more accurate than it was before. And then for all those images to get down to the computer to run through this, and I'll let Trey explain.
Alright, so this is our antenna tracker. We originally started with an autonomous antenna tracker, but the original Wi-Fi antenna, which is the circuit here that we intended on getting, was significantly smaller, and as you can see it's a metal grid, so it weighs quite a bit. So this was the one that we had to end up getting just based on time and shipping. So our servos on our autonomous tracker could not handle the weight, so we decided to just switch to a manual to eliminate massive air and loss of signals that could occur. we have 3 antennas on here. This is the 2.4 gigahertz Wi-Fi antenna, and that connects to the LRU. That connects to the Raspberry Pi on the payload computer, and that transfers the images to the imager console for Jordan and Zach. Then we have a patch antenna right here running on 915 megahertz, and that connects to the LRU and transmits all of the data to Kevin with the PCS. And then we have a box antenna right here, and we chose that. It's a high gain antenna, and it has a 180-degree beam width. So for a PP antenna, no matter what, even if there's slight error in the manual antenna tracker, the safety file will always have a clear FPV feed, no matter really what, so it can always land safely and not harm landers. We carry a couple other things with us too on our ground control station when we move around. The first one is the fire extinguisher, because the light posts have a high fire rate, and we don't want any explosions or fires that cause harm to our crew members, the environment, or anybody around us. We carry that. We carry all of our light posts in this ammo box right here, which is fireproof, so if there's any concerns with it whatsoever, the fire will not spread. And then we obviously carry tools and spare parts in case we make quick fixes on the fly.
Right, so we talked a little bit about the pre-flight briefing. We have an extremely simple pre-flight briefing where I as the air boss will basically call out to the operator stations, and they will give me a go or no go based on their readiness level and the system integrity. Basically, if they give me a go ahead, we proceed with the mission, and if they give me a no go, we rectify the problem, then we go back to square one and we redo the entire procedure. So to sum up, we basically intend to attempt four major tasks. One is the autonomous flight task, the area search task, the ADLC task, and the actionable intelligence task. The off-axis target was attempted and fully accomplished, but due to a small crash we had, we lost the 3-axis gimbal, and because of losing the yaw axis, we are no longer able to do the off-axis target. And the emergent target is something we did not attempt, and we do not want to attempt at competition. So any questions from the group?
Good morning, everyone. My name is Lucas. This is my first year on the team, and during flight mission, I am the team captain.
Morning, everyone. My name is Mike. This is also my first year on the team, and for the competition, we obviously think
Hi, my name is Helmut. This is my second year here at this competition, and I am the safety pilot during the mission.
My name is Benjamin. It's my first year here for the competition. I'm responsible for mission planning and autonomous flight supervision.
Hi, my name is Michael. It's my first year also, and I'm mission control.
Hello, I'm David. For me, it's the first year in this competition as well. And during the flight, hopefully tomorrow, I will do the pre-selection of the pictures.
Hi, my name is Philip. It's my first year in the team, and my jobs are assist the launch of the aircraft, image processing and reporting.
So this final version of our UAS is a 3-year history of constant development and testing and operation. The UAV's design is based off a modular concept, as you can see, and we built most of the parts ourselves, almost all of the parts ourselves, and we think that'll give us the best possible performance. The software architecture is a smartphone-based system based around the Samsung S7 Galaxy smartphone that will be used to take pictures and also for image processing. We're using a Pixhawk autopilot system to guide the aircraft. As you can see over here, we've got a tracking radar, and that gives us the best possible data link. It's secure and reliable. The aircraft has a speed of approximately 28 knots and a takeoff rate of 4.5 kilometers. This configuration has an operation time of over 60 minutes, so we're confident that will give us plenty of time to accomplish the tasks very solid for competition. And finally, we anticipate completing all tasks, primary and secondary, excluding the ADLC phase.
So as a safety pilot, let's talk a few words about safety. General safety played a major role in the whole development and flight testing process of this vehicle. Concerning programmatic safety, we use customized autopilot software to match the safety regulations of this competition, which means in case of an RC communication loss in 30 seconds, the plane will perform a return to home maneuver, and after a total of 3 minutes RC communication loss, it will perform a flight termination maneuver. During flight testing, we found out that we can achieve a minimum energy flight termination with an opposite direction of ailerons and rudders and a full-up elevator deflection. Another very important point is that the home point of our mission, where possible flight termination actually occur, is in a safe distance from any operators and spectators, so that no person's safety is at risk in the event of flight termination. Concerning the system design safety, we made a major improvement, which is that the aircraft can be operated without any payload, so the aircraft is completely independent from the payload. And in addition to that, there is no power wiring between the aircraft and the payload. There are only signal buses between the payload and the aircraft, which means in the event of a major damage in the payload, like a short circuit or something like that, this will have no effect on the flight safety of the aircraft. Concerning operational safety, of course, we have different checklists for all the parts of the mission, preparing and the mission itself. And of course we have safety equipment like a helmet for the person who will launch the aircraft and a fire blanket so that we can also deal with a burning LiPo battery. To close, let me say some words about the safety pilot's experience. This is my second year here at this competition as safety pilot. I'm an RC aviator since 1997. and holder of a German sports pilot license with a flight instructor rating and a total of 990 flight hours. And I think all this experience was my biggest contribution to this project because it enabled me all the time maintaining safe and stable flight conditions during the flight testing and also recognize and avoid general safety risks in operating a model aircraft. So thanks for your attention and I'll give on to you.
Thank you, Helmut. My major role in the preparation for this mission and this competition was the developmental testing of the hardware, so especially the aircraft itself that you see here. As you might have noticed and might remember, this aircraft is very similar to the one which the Munich team brought here last year. It looks similar, it's the same concept, but all the components are completely refurbished and rebuilt, redesigned to fit the requirements for this year's mission and also to improve safety and operability. These improvements started already last year when our team went to the Ecuadorian rainforest with a UAV which was like the step between the last year's UAV and this UAV. And made of components from both of them. And what we did in Ecuador was we did a scientific research mission and collected high resolution imagery data. And the cool thing about it was that we operated the UAV at a distance of more than 7 miles away from the takeoff and landing point. And the operation was completely safe beyond the line of sight and also beyond the telemetry range, which was only about 7 or 8 kilometers. And the aircraft always returned back safely and we did complete autonomous flights. Very successful there. In the Ecuador missions we could collect a lot of not only data but also experience operating the aircraft and also have lots of lessons learned from it which we could then implement in preparation of this year's competition missions. Of course, all the improvements which we've made, for example, I encourage you to have a look at the printed circuit boards which we have in the wing center box, which replace all of the wiring which we had in the test last year. All of these components, of course, have been tested first in the lab conditions very extensively, and then afterwards also during flight testing extensively. In the lab, for example, on the circuit boards, we did a lot of testing under circumstances of voltage and power which were very similar to the ones which we expected in flight, and did also long-term testing in the lab and measured the temperatures along the board, and that was all very safe and very good dimension. Also we of course tested in the lab the autopilot system and the hardware in the loop, and also like when you deflect the aircraft, the rudders deflect in the respective way and everything like that. Also we tested in the lab the flight termination and the fail-safe modes and all the safety mechanisms in the autopilot. Then came the flight testing, the most important thing. It was divided in 3 stages. The first stage was the manual flying, where we did lots of takeoffs and landings, and also we could do lots of tests on the gliding capabilities without engine of the aircraft, and also the stalling properties and the turning properties and everything. After we figured that out with this aircraft configuration, which was pretty easy because it flies very well, we could go on to stage 2. That was the autonomous flying. We spent lots of hours just having the aircraft fly like pattern, a rectangular pattern or something in the line of sight, so that we could tune the autopilot and measure the turning radius and everything, the maneuverability of the aircraft, and also the accuracy of the navigation, so that it hits the turning points correctly and everything. And we could tune the autopilot to a state which is now in where it is really accurate and can follow the turning points at an accuracy of less than 30 feet, sometimes even less, in windy conditions. Stage 3 of the flight testing was the mission flying, which we did a lot. For example, we dropped lots of bottles on the model airfield where we are at normally, and also did all the other tasks extensively together with the IT guys. And so after all this, we are very confident that we are, from our hardware and everything and our testing, that we are going to be able to complete the mission here in the competition at a very, very high standard of safety and also performance. And now over to the IT.
Hey, I want to talk about what we did to make our software work properly and some aspects of cybersecurity. We have password-safe workstations, an encrypted Wi-Fi connection from the ground control station to the aircraft, and only use wired connections between our ground devices. During the development, I was also responsible for continuous integration and quality management. We use tools like Git or SonarQube to ensure that only good code can find the way into our software. Later on, Phil will talk about the major aspects of our software architecture, and now David will give us some testing we did.
We heard a lot about the hardware testing we did, but in software we also did a lot of testing. Besides of like normal unit tests, we did basically two kind of tests. We developed for each component we have, like the ground station or the image processing, which we used to have. We created a separated testing environment for mocking data so that you can test each of it separately. And then we developed a system to try actual flights in whole. So we had a flight simulator, the JSP sim, and we were able to do whole flights just at the computer. So whenever a developer finished something we did, you can try it during a flight, and that way nearly all of the errors occurred quite early, and we were able to fix them before we had actual flights. And then on the several actual flights we had, nearly never software errors occurred.
I want to tell something about the Machbox. The Machbox is our software component in our system, and the main task of the Machbox is to distribute telemetry communication data from the airplane to the ground station. We decided to use this component because of following advantages. We have a clear interface between the aircraft and the ground station. We have a standardized communication protocol. And we have a higher robustness because if one computer of the ground station breaks down, other computer still can receive and send telemetry communication data. And last but not least, we can distribute workload several multiple computers. So that was my part, and I can give it back to Lucas.
Thanks, Philip. All the information we have presented to you can find on our system overview right here, so feel free to have a look on this later. In summary, the question, are we ready for this competition, can be answered with 3 numbers. Number 1 is 40. We have over 40 hours flight mission experience on the mission planner on the similar UAV. Number 2 is 25. Our safety pilot has performed 25 flights on the competition configuration, including 9 full mission flights. And number 3 is 85. During software development, we achieved 85% of code coverage. These 3 numbers together ensures us that we are 100% sure to accomplish a safe and reliable flight during the competition. thank you for your attention, and need we say more?
So now we're looking forward to your questions, of course.
Here with the NC State Aerial Robotics Club. My name is Matthew Tompkins. I will be the flight test director and safety pilot, and I've been doing that for 2 years.
My name is Alex Schaefer. I'm the payload lead. I've been doing that for 3 years.
I'm Justin Distra. I'm on the payload team, and I've been doing it for 4 years.
Hi, my name is Michael Ashton. I'm on the payload team, and I've been doing it for 1 year.
Hello, my name is Caleb Upchurch. I'm the flightline director, and I've been doing it for 1 year. I'm here to Purdue. I've been doing autopilot.
Hi, I'm Ash Mason, and I've been on the payload for 1 year.
My name is Glenn Richards. I'm the autopilot team, and I've been doing that for 2 years.
My name is Kenneth Woodby, and I've been doing it for 3 years.
So this year, our teams here together has had 19 flight hours together over the course of 57 flights. Our team is divided into a hierarchy, which goes from individual team members to our sub-team leads, and then finally to our flight test director. The aircraft that we use is our Fenrir system. It's a twin-boom pusher aircraft. It's a 10-foot wingspan, a gross weight of 41 pounds, endurance of 1 hour, and a loiter speed of 38 knots. Our aircraft also has an integrated drop bay, and it's run by a gasoline engine. The autopilot system we use is a Pickrel LT with an integrated Honeywell magnetometer, laser altimeter, and a custom safety switch that we developed in order to completely isolate our autopilot from our RC system in case the autopilot has a failure. Finally, our payload system consists of an SVS 11 megapixel machine vision camera that is mounted on an auto tracking gimbal. The whole system is integrated to an x86 Linux flight computer, and for communication we use a 5.8 GHz microtech radio for our payload link, as well as a 2.4 GHz UAQD radio for our SR communication. And you can see this diagram that illustrates the interconnection between our entire system. Next up, Kate will be talking about system safety.
So we have a fully custom ground station curriculum. It provides an organized environment for all of the ground operators. This includes 5 payload operators and 2 autopilot operators. We have supporting infrastructure built in that includes 900 megahertz autopilot antenna and GPS antenna, plus auto tracking 5.8 gigahertz antenna for the payload. Each operator in the trailer has their own intercom so we can communicate. We plan to test every objective except SDA and ADS. Our programmatic risk is with airdrop. Through extensive testing, we have found some longitudinal accuracy problems. And then we have a high level of redundancy to ensure that any single point of failure does not cause loss of performance in the aircraft. This includes individual control surfaces, server for each independent RC and autopilot that can be separate power systems, 2 separate battery sets that can be downloaded. Michael will talk about testing and safety.
So when we talk about our system, we have our limitations. But our limitations, we also do have our capabilities. We can fly our aircraft in 22 knots of wind, speeds up to 22 knots, gusts up to 27 knots, and 17 knots of crosswind component. We have a flight endurance of 45 minutes with some extra reserve fuel minutes if we need it. We care about safety very much on this team. It's extremely important. So we have come up with a system of discrepancy, identification, and reporting. For instance, in a flight, if something is reported and somebody sees something that that's going wrong, it's immediately communicated to the sub-team through the intercom or the radio system. This system is then either sent to the flight director or other sub-team leads in order to determine if this will impact our mission success or the safety of our team members or other people watching. The flight director then will make the decision as to whether or not we need to change anything in our current mission in order to actually avoid this, because mitigating the issue is the key objective. In the event of any sort of a showstopper incident, it ultimately comes down to the flight director to make the decision. We have a very specific set of go, no-go criteria that we've come up with through extensive testing. But we have checklists that are divided. The checklist like you guys have here that we passed out. Those are divided by all of the key components in our mission and our pre-briefing. All of that is checked verbally through the intercom on radio by the flight director and communicated to the rest of the team prior to taking off. Any of these major mission steps, such as the power change or the engine start, all of that is communicated so that everybody knows what's happening so that we can maintain a safe environment. Before any of this happens, we go through very extensive ground testing just prior to any flight because we want to make sure that stuff works on the ground before we put it in the air. An example of this is we do sub and full system bench testing on all of the components, but specifically this year, some examples of that we've done are with our airdrop system and our brakes, because the brakes are a new addition to our plane. Kind of see them back there. But we do software, hardware, and loop simulations, which are really helpful for our autopilot. That allows us to simulate the flying of the plane in a simulated environment, so that way we can know how it will react when it's in the air and for the real thing. We also do other simulations, such as software unit testing and the flight ground PC virtual machines. Those are used for integration testing. A very important part is the connection between the plane and the ground system. And that is where the ground range and throughput testing and communication systems come from. So that way we can establish a link between our ground and next we will have Justin Easter present.
Alright, for developmental testing, when we get a new airplane, we first test it without payload. So we set up RC flight, we go through structural verification, so we do envelope expansion, we test building controls, make sure there's no flutter in the wings, we determine takeoff and landing distances, as well as maneuverability. Once we pass those tests, we move on to integrating our autopilot. With that, we practice land-off and takeoff and landing again, horizontal path tracking, altitude tracking to make sure we'll meet the waypoint objectives, as well as flight planning with different wind speeds and wind directions by testing at multiple days. For our payload testing, we constantly take imagery down. While we download them, we send down two different versions. We do a low quality and high quality. We do low quality so we can get all the pictures down. We identify the target and all the characteristics. That's the high quality picture, and you can see the difference here, and then we can hopefully get the rest of the characteristics. For our S-rig system, we've extensively tested it. It's fully automatic, so when we fly over the S-rig, we do download and upload. We can do up to 4 megabytes per pass at 300 feet HVO. For our airdrop system, it's also automated. Once the judge is given approval, we will authorize it. And the way it works is it calculates the optimal drop point. Once we are within the minimum radius of drop, it will automatically drop. And we also practice doing off-axis target testing as well as integrating with the interoperability server. And that.
Alright. Over the course of this year's flight testing, we've completed 28 full mission simulations. We've accumulated 19 flight hours, with 72% of that being autonomous. With that 19 flight hours, we now have 64 total flight hours on the Fenrir platform. We have an average system setup time of about 10 minutes with an average mission time of about 21 minutes. Our target accuracy is about 80% at 50 feet, and you can see here image location versus our actual location when we go back to check. We have reliable waypoint tracking with plus or minus 50 feet laterally and 25 feet altitude. We have reliable auto takeoffs and landings. We have full search area coverage ensured by different techniques that we've come up with for planning. For instance, Justin mentioned turning into the wind, optimal spacing on our search patterns. We have reliable SRIC download and upload, and we have quick dynamic recasting. Over the course of flight testing, we've come up with an expected list of goals. We plan to meet the objective of all the attempted tasks, with the exceptions being interoperability and airdrop, and we will meet at least the threshold there. Thank you for your time. We'll be happy to answer any questions.
I'm Eyal, and I'm the team captain of the TAS, Technion Aerial System, from Israel. It's my second year in the project, and I will be the primary flight controller. I would like to introduce introduce you our faculty advisor, Dora.
My name is Dora. This is my third year in the company, and I'm the safety pilot.
My name is Yanni, second year in the project, and I'm the GCS primary commander.
My name is Rea. This is my first year, and I'm the safety instructor.
I'm Ronnie, this is my first year, and I'm in charge of the payload system.
I'm Ori, this is my second year, and I'm in charge of the communication system.
I'm Nixon, this is my first year, and I'm in charge of image processing.
I'm Indo, this is my first year, and I'm the secondary GCS command.
Hey, I'm Daniel, this is my first year, and secondary flight controller. Now I'm going to present to you the development structure of the antenna system. As you can see, the development is based on the 5 main stages. In the first stage, we performed the touch test flight on our last year's platform in order to learn the airflow around our wings. Afterwards, we used the PLM software in order to determine our new aerodynamic characteristics for our new wings. And we used the storyboards and ANSYS in order to design and perform tests of the load on our platform. After the two platforms were ready, 2 types of tests were made. The first one was the ground test, in which we performed a wing load test to see that we can handle up to 3.5 Gs. We performed the radio communication ranges and the local structure. And finally, we performed a flight test. You can see here we have a flight testing process in order to make our schedules work better and to perform more flights. Here you can see our total of 163 hours of flight we performed, excluding the simulation we did when the US will arrive. And eventually you can see here at the end the table that shows all the documented missions performed and the success rate of the missions. Now we can show the overview of the antenna system.
Thanks, Daniel. I will introduce the antenna air system. Our system is a fixed-wing electric engine aircraft. The system based on the last year's system, however many improvements been made. The system composed from 4 detachable parts: the fuselage, 2 wings, and the tail unit. The attaching of the airplane takes less than 5 minutes, allows us to easy maintenance and transportation. Starting with the fuselage. Since our engines mounted on the wings, it allows us to put our main payload on the front. The payload includes the camera and the 3D printed gimbal. The gimbal stabilizes the camera in the pitch and the roll degrees of freedom. In the front part of the fuselage, we have the image processing computer, the GPS, and communication unit. In the middle part, we have the battery pack and the autopilot unit. In the aft part, we have the airdrop mechanism. This year, our wings are completely new design. They designed after a long period of structural and aerodynamical analysis, allowing us to build a lightweight, hollow, and composite materials-made wing. Finally, all the airplane is self-designed and self-built by the team using advanced techniques and composite materials. Now Rea will introduce the safety aspects of the project.
During the entire process, safety was a major consideration. When designing the ELD structure, safety factor of 2 was taken. The electrical system designed to withstand 1.5 times the expected load. Repeated testing was performed to ensure system performance. We choose the 2-motor configuration. This configuration has proven itself when in one of the flights, 1 motor failed, yet we were able to land the ELD safely. We developed a full system diagram to ensure correct hardware integration. We added a relay switch that can turn the antenna to a manual RC plane. By the order of the safety pilot, we changed last year's safety plug due to overheating. The safety plug disconnects the motor until its removal before the flight. The obstacle avoidance algorithm can be controlled and turned off directly from the command and control station. In order to prevent interference between the SRIC and the safety pilot links, 2 approaches were taken. First, custom design of the SREC hardware. And second, we wrote a software to ensure to remote control the emitted power. Moreover, ground and aerial experiments were done to ensure safe operation. In addition, a first aid kit is always available in case of one of the primary injury. Now we will present some of the missions.
Thank you, Ran. I will now present to you 3 of the tasks which we are going to perform during our flight demonstration. The first task is the interoperability test. This year, the interoperability algorithm was implemented directly into our command and control system, the mission plan. The picture you can see here is a snapshot of the flight controller's screen. Up here you can see the different messages sent by the server, as well as the data rates, stationary obstacles, and dynamic obstacles. The algorithm also automatically uploads any target identified by the image processing team in real time. To achieve a constant data rate, a control loop has been introduced into the code. The second task is the SDA task. Like the interoperability algorithm, the SDA algorithm was also implemented directly into the mission environment. The algorithm creates an alternate route for the plane to take in order to overpass the obstacle. As you can see here, this route updates constantly during the maneuvers to achieve an optimized result. In this diagram, you can see that the algorithm also takes under consideration different scenarios when deciding how to overpass the obstacle so that it won't hit other obstacles or fly out of the flight level. This is the development process we do for the algorithm. We first came up with an analytical solution, then created a MATLAB simulation to test the solution, and then implemented the code into the mission plan environment. To ensure us that the algorithm won't hijack the plane when not needed, several precautionary measures were implemented directly into the code. The third task is the off-axis test. This is our gimbal system, which is controlled by a BIT controller. Our algorithm closes the loop around the angles of the motors to point the camera to the required area using an IMU which sits directly on the camera. As you can see in this picture set, using the algorithm, we can follow a predetermined location long enough for us to take the necessary pictures. All of these algorithms were tested both on ground and in air several times to ensure that they don't interrupt with the mission plan normal operation. And now Daniel will present the airdrop test.
This year's airdrop mechanism is based on a single servo mechanism that opens the hatch on the rear of the aircraft when commanded by a script written in Python. The script takes into consideration all the needed aspects for a safe airdrop, and in order to anticipate the bottle's freefall trajectory, a number of experiments were made with the bottle, and the aerodynamic characteristics of the bottle were determined. And the script, as I said, is written in Python. It's loaded into the mission planner. And safety was taken into consideration to this mission also, and a radius of safe zone perimeter was determined. In case the UAV isn't inside this perimeter, the script won't run, and the UAV will perform another drop run. And now Ronnie will present the payload system.
In the payload system, we face many challenges, with the solutions required major engineering work and out-of-the-box thinking. These challenges and the solutions will now be presented. Mounted on the gimbal, we have the camera, the mirrorless camera, and the vector nav IMU. The camera is controlled by the onboard computer, an Ultra DXU3, and is also connected to the ADAC computer. This year, we decided to implement the complete ADAC pipeline on board the aerial platform. Using an NVIDIA Jetson TK1, which has a GPU for parallel processing, as will be explained later. To select the camera, we reviewed many different options, including Android-based and machine vision cameras. Based on their optical quality, control interface, and cost. Final selection was made after a ground and flight test. To control the camera, we had to reverse engineer the camera control protocol using methods such as USB sniffing. Custom driver was implemented, focusing on high transfer rates. Using this driver, we achieved 2 to 3 pictures per second compared to last year's single picture per 2 seconds. The camera produces 24 megapixel images compared to last year's 12 megapixels. We faced serious memory issues on board on the main onboard computer and the ADAC computer. To this end, we carefully optimized the onboard software. Each picture taken is paired with IMU and autopilot telemetry. And much work was done to achieve accurate timing of the pictures, providing highly accurate geolocation, more than 5 times better than last year. On the ground, we have the primary station for controlling the camera. Images are downloaded to the imagery hub, and and sent to several imagery stations for manual scanning by multiple crew members. In order to save communications bandwidth, only scaled-down images are sent to the ground. Regions of interest are cropped manually or automatically and sent to the ground at full resolution. ADLC results are sent to the ADLC station for display. For development and testing, we have also implemented a simulation mode in which imagery data from previous flights is used instead of the real camera, as you can see here. Now in its time, we'll present the image processing algorithm.
Thanks, Ryan. As you can see over here, we use a customly built software to manually scan and identify the targets. The software was designed to enable us fast scanning and analyzing in high frame rates. Geolocation of the targets is done with the image processing algorithm, which utilizes our highly accurate IMU vector map. The ADLC is done completely on board the aircraft this year. The algorithm is based on two deep learning networks, one for target shape classification and the second one for target character classification. Other image processing algorithm in the ADLC pipeline provide us with target color and orientation. In order to run the neural networks, I decided to use a GPU and a very low power consumptive GPU, the Jetson CK1. In order to train these networks, we synthesized hundreds of thousands of targets according to the competition rules. Following the conclusions from last year's competition, we decided to implement a mapping tool which shows us the search area coverage in real time, and you can see it running over here on the computer. This tool allows the flight controller to see uncovered areas that may contain targets in the search area, like over here, and you can send the aircraft to scan it again. All the algorithms I mentioned were tested both on ground and during flight tests. Now Ori will explain about our communication system.
Last year, communication system deficiencies have led us to redefine the mission profile and the resulting design objectives. The two links in focus were the SWIC link and the imagery link. Throughout the design and optimization process, several sets of antennas were simulated using CSD, built, custom-made by us, and tested. The design objectives were to maximize bandwidth performance, directionality, and range, while minimizing physical dimensions and weight. For the ground station, we modified the antenna tracker, thus achieving better system performance while reducing the required staff. For the proofing procedure, included solid performance measurement in an antenna range, where we obtained the real radiation patterns and used the spectrum analyzer to assess SNR. Bottom line is a robust mature system capable of transmitting more than 40 megabits per sec at a range of 1 kilometer. Back to our team captain, Eliran.
Hi again. Now I'm going to talk about our pre-mission brief. Since our pre-mission brief in the flight line is a bit long, I'm going to review it quickly. When we arrive to the flight line, we are going to split our team to 3 different stations: flight control, image control, and safety, pilot, and inspector. When we will start with presenting our crewmen, names, position, and responsibilities. Then we are going to verify the mission tests that are going to be performed by the roaders. After it, we are going to repeat on the safety aspects that are taken during the mission flight. Then, we are going to explain about the communication between the team members. Finally, I would like to emphasize this year's main achievements. As you can see here, we have new advanced wing and 3D printed gimbal. We have a novel onboard computer. We improved our algorithms of the SDA and the airdrome and the ADLC. We have improved the communication and the antennas. And overall, we improved our system reliability. Thank you very much.
Thank you for your attention.
Thank you.
And
I'm the team leader of our team captain. Students
So my name is Andrew Fitzgerald, and
hello, my name is Brendan Quinn. I'm a lead for Anywhere. I've been a member of this team for 3 years. And
My name is Alex Padmay. I'm the ground station operator. I'm an electrical. I'm studying in electrical engineering.
Hi, my name is Richard. So, here in the competition, I will analyze the video feed to spot any target.
Hi, my name is Jeremy. I'm a student in engineering.
My name is Portland Weiser. This is my first year.
In this
So we're going to start off with a short introduction of the system itself. To start off, Bashir will talk about
all the teams.
Hi, I'm Michael. In this competition, I will be in charge of the interrupt, and I will support the ground station.
I am Gabriel, and I'm the beat.
Hi, I'm Jonathan Cha. I'm our team captain. I'm here just for support the team.
So right now I'll begin to introduce to you Journalabs, because it's the team that we're a big member of. So Journalabs had been founded like 8 years ago, and this year is our second participation to this competition. So we joined, this is our 9th iteration of it, because each year we're doing a new version. We also participated in another competition that's in Canada, it's a Unmanned aerial vehicle. We have done it 3 times right now.
Design and okay, so as you said, I'm going to explain a little bit the platform and everything that's going around in the competition. So as Abdi said, it's our 9th iteration, so that's different from last year, if you guys remember that. That's an octocopter, which has around 30 minutes autonomy with 2 batteries. We're flying actually with the 2 10,000 milliamps batteries, and we can also add another one, but not for this competition, because we don't require 45 minutes of autonomy. Inside, we changed the autopilot. We're actually using a Pixhawk, the PX4 flight stack, which allow us to use Q ground control as our ground station. After that, the system is we're using QX30 from Sony. That's the camera. It got 20 megapixel resolution, and it allows us to take pictures at 400 feet from the ground, and still have a good resolution to decode the QR code. As far as thing goes, we're using 5.8 gigahertz ubiquity bullet M5 for the photo transfer, and we also got a live feed with a webcam right here, which Michelle is going to be analyzing. So if there's any target that we didn't spot with the QX30 camera, we actually we'll be able to change the mission and do a flyby to take extra pictures. Also, we got 900 megahertz XP for the telemetry, so data link will be over 900 megahertz. We also got another data link over the 5.8 gigahertz if we got any problem with the 900 megahertz XP. For the remote controller, we're using the Immersion RC 433 megahertz. And that's the only thing on this band. It's only for the remote controller. Other than that, on the ground, there will be one operator of the imagery software. That's the app. It's going to receive the photo in the picture in real time, and it's going to be spotting the target, which will be sent immediately to the interruptibility. In real time, and it's gonna be sent to the server. At that same time, the interruptibility well, Michael, it's gonna be telling me if there's any obstacle on the flight path, and it's gonna tell me if we have to change the trajectory and mission. And
Yeah, that's pretty much it for the platform. We choose an octocopter for the reliability. We got the redundancy on the motor, so we can actually use two motors without any problem. Well, we can still flew the drone perfectly, and we have done it. Last year we had some trouble with the connector, so we lost a motor in flight. That year, nothing happened so far, and we hope it's going to stay that way. So the platform is doing very well, and we have seen them perform in outstanding condition and in windy conditions, so we trust them a lot, and we think that's going to outperform any other quadcopter. Also, it's a homemade design, so I've already told some of you guys, we designed it ourselves, and we made most of the part for it ourselves, so that's something that is different from every other team. We know how it's performed, we know what it's capable of, and we have done so many tests and simulation on the software and we know how it can perform and how durable they are. So that's pretty much it for the platform and our flight, how it works inside.
So that's an overview of our system. To talk about more about one of the most important aspects of the system, safety, so we're going to have Deontay talk more as a safety manager about what he does.
The takeoff, autonomous takeoff, after the waypoint, so we play about 7 minutes maximum to detect all the waypoints. After we're gonna raise the altitude to the minimum required to be dropped at 8 meters per second. We're gonna drop, hopefully the closer we can. And after we're gonna try the search area task, trying to locate the QR code in every target. As an autonomous search. We're gonna try after that the up-axis images with another camera, Raspberry camera, because it's gonna be enough to just check the target. And after that, we're gonna do an in-flight retasking and inject a mission on the drone, maybe to check the emergency targets. And after that, at the end, we're gonna land. But meanwhile, a lot of tasks are going to be played in the background, like the SRIC task, trying to bind the server at the time. Besides, we're gonna we are not able to reach. We're gonna go to the location, and hopefully we'll have the time. We're gonna try to detect the message on each target.
One of the main is that
the probability we're gonna be able to send the characteristic of each target to the server to inject the code.
Isn't that IO can allow for us to continue manual control even in the failure of the autopilot?
Roll to there.
That allows for a nice backup system. And the autopilot has another fail-safe built in. Of course, we have the 3-minute flight termination that's required by the competition. So if we lose communication from most of this, but we also have additional fail-safes in the event of a smaller loss of connection. So we lose our safe time after 10 seconds, we go into safe mode. After 1 minute, we will return to launch, and after 3 minutes, terminate. And similar fail-safes exist for loss of communication to the ground control station. So these fail-safes work together with redundancies to make a safe aircraft. And that's really important to us. And one of the biggest ways we're able to ensure safety of our aircraft is through extensive testing. Because if you haven't tested it, it's not safe.
We're going to fly well.
Talk more about our testing
There's
procedures.
no problem or anything. But I'm pretty confident about it. I'm going to all enjoy it and see other teams also doing well because
by the subsystem by itself, the individual
We're also pretty much confident because 1 month ago, just in a competition in Canada, and it was pretty windy, and we were able to fly without any problem. So we
it was about 50 kilometer speed.
And for the planning, we have like an estimate time of each task, how long it will take. So we're going to be after 3 minutes, we're not done our task with the drone. So the 15 minutes after will be like treatment of the data.
And it's pretty flexible. We can because we don't have any coordinates of every target, so we don't have pre-planned the mission.
Yeah, we're going to the full system according to the new target we found. And we're pretty used to flying those drones. Normally we, like in the last competition, we were flying the two drones at the same time. So it takes a good level of planning to achieve that. And we've been practicing a lot during the last few months. And we've tested in approximately every single test, wind turbos, windy, a little bit of rain. We've tested everything, so we think that we're ready for this competition. As I said, we're going to outperform most of the drones here.
So yeah, since we're from Canada, it passed through winters.
Yeah, it's a hard winter. When your battery life drop like you,
we tested them. We did some integration tests.
Do you want to talk about any of the, you talked in general about the testing you've done. Do you have any more detail on how you tested test results, anything like that?
Test results for each mission. Okay. Well, in the few past 2 months, we've done a complete scenario of the competition. So as much as waypoint navigation goes, we've done some complete mission plan. So we start with autonomous some waypoints that we pre-determined, and after that we went to QR code recognition. The real QR code recognition. We've used the interoperability on our own server because we rent a server, and we did the same setup as here. So to test if the interoperability was working. Also, we tested our own imagery software. So if we were able to find the targets, to transmit the target location with every other aspect that we have to. We tested the drops a few times. Well, a lot of time. Yeah. Also, we had some guys who were on the field laying down and see if we could find them and tell what they were doing. We also tested the server connection. Yeah, the SRC task. Also, the off-axis have been done a couple of times in our test. Yeah, we pretty much tested every single scenario. Also for all the problem that we might have, that goes for data link loss, RC loss, loss of GPS, everything we've tested it, and we know how the platform reacts and what we should do according to that problem. So we've tested every weekend. We were able to.
That's a 2-minute warning for the 15 minutes.
Okay.
Then we'll have 5 minutes for questions and answers.
Okay. So yeah, we went outside in the field almost every weekend, and we tested both of the drone and set up every single weekend. So we had a lot of flight free with them. In the last a big part of the pre-mission brief for me as the team captain, I make sure that all of my team members understand what we're in.
Okay, so we're Team Animus Ferris from Twin Hill High School in Oakton, Virginia. I'm the team captain, Gregory Ben. Recently graduated senior from Twin Hill High School. I'm going to be attending Purdue University next year.
I'm Jack Moore. I am also a recent graduate from Twin Hill School. I am attending Booster Polytechnic Institute in the fall. I am the safety pilot for Team Animus Ferris. I have created test platforms to test the software and hardware before we onto the competition platform. I am a novice pilot, so it was imperative that I train using those test platforms. I have 20 hours on those test platforms, which helps me build confidence onto flying the competition platform, in which I have additional 4 hours onto the competition cockpit, which I have had no incident. On top of which, we have programmed fail-safes onto the controller, so if an error in autonomous happens, I can switch it to manual. If
we require the copter to come back and set to return to launch. Or if an emergency happens while in air, we can set it to immediate landing.
I'm Brady Coleman. I'm the safety officer. I am also a recent graduate of Flint Hill High School and will be attending Bucknell University next year. From the very beginning, safety was one of our main concerns. That's actually why we chose this craft. As you can see, we are located close to a major road and a major highway, so we didn't want the runaway risk of a fixed-wing craft. With this, we can ensure that it won't go into oncoming traffic. Also, with this craft, it's designed to be able to lose power to 2 of its motors and still stay in the air. We've also, because we follow a strict set of safety checklists before each flight, we've never had a catastrophic crash with this craft. Catastrophic crash being defined as a crash in which we needed to replace a major component or multiple components. During calibration, we had a hard landing in which we needed to replace a propeller, but other than that, we've had 100% success. In the very beginning, we started with 4-cell battery, but we had a brownout ones, so to make sure that never happened again, we switched to 2 6-cell batteries. This allows us to have well over the 30 minutes of flight time, so we don't need to change our batteries. As you can see here is a graph of our flight consumption with these batteries. We've also used fold-away propellers instead of carbon fiber or solid ones to ensure that to minimize damage if this does hit anything. I was also part of the team that designed the water drop component. We decided to 3D print it so it would fit perfectly with a specific water bottle in mind and also work well with our craft.
I'm Benjamin Fabell, also a recent graduate of Flint Hill High School and will be attending the University of San Diego this coming fall. As Brady mentioned, we use the water drop component as well as a camera and gimbal system. Both of these systems mount to 2 20mm military specification Weaver rails on the underside of the aircraft. This allows for a quick swap system as well as a lockdown, so there's no shifting during flight, so it will not affect our balance or get in the way of our laser ranging system. As far as communication with the aircraft is concerned, we run off 2 frequency bands, 2.4 gigahertz and 915 megahertz. 2.4 gigahertz is our manual control channel. It's always active, but is only used when there's an error with autonomous control or manual takeover is necessary. That's run through the antenna on the controller. The 915 band is used for autopilot through the Pixhawk system. It runs via a 3DR radio to a 16 dBi patch antenna using the Madeline protocol.
My name is Kaylee Azar. I'm also a recent graduate of Flint Hill and I'll be attending University of Delaware in the fall. Our ground station is run by Mission Planner, which allows us to map out our mission to our unique specifications. Mission Planner also displays the intended flight path and the current location of our copter to ensure that we're going on the right route. The mission screen also displays the status of all onboard components, allowing us to search for any errors. We have enabled fail-safes in Mission Planner to ensure we have complete control over our vehicle. The fail-safes include a distance fail-safe. If the copter goes a certain distance in radius from the home position, it will return to launch. If there is a battery fault or a drop in battery voltage, it will return to launch. If it loses communication with the manual controller, it will return to launch. And we can control from Mission Planner if we need a return to launch or a land in emergency situations, we can initiate that from Mission Planner. I'm Gianna Fiore and I will be a senior at Flint Hill next year. As such, a large part of my role in this team has been preparing for production, learning about the competition as a newer participant before. I've also been operating the antenna, which has 360 degrees of horizontal rotation and 180 degrees of vertical rotation, which creates industrial environment.
Hello, my name is Ian Schmidt, and I'm also a recent graduate of Flint Hill. I will be attending the Nuclear Flight Training Institute in the fall. And I was part of an SUAS team last year, and so I brought that experience with me. Because of that, I worked mostly odd jobs here and there around the team, but I focused on software and then hardware locations. And thanks to the accurate and pre-planned flight path in Mission Planner, we were able to take the images in post-processing and map them accurately to look at the targets.
So this is our second year competing. Our first year we learned a lot, but the biggest takeaway we had was we needed a lot more preparation. As such, we wanted to start out and build a solid platform and not overstretch ourselves, and we put in over 8 hours of autonomous flight, over 60 flight tests. We've tested with 100% accuracy every time our autonomous takeoff and landing, autonomous waypoint navigation, search area task, and the deployment of our water drop task. In addition to testing each of these individually, we've run 9 full flight missions as we will for the flight demonstration, all falling within the 30-minute flight parameters. Because of this, we are very confident that we will give a successful flight demonstration course. Are there any questions?
Our introduction section from that side.
Hi, my name is Ankan Datta. I'm from MS Raman Institute of Technology. I study my third year of Electrical and Electronics Engineering, and this is my first year here at the SUAS.
I'm Kevin Donar.
My name is Sandesh. I'm a mechanical engineer. I'm in my final year studying mechanical engineering. This is my first year at the SUAS, and I'm also part of the airplane testing and safety pilot.
Hi everyone, my name is Arjun. I'm from MS Raman Institute of Technology. So just to give you basic system overview of electronics and communication, the system is 6.1 or approximately 30 pounds. The speed of first time during the mission is 6 meters per second. The range of our system has been tested to 1.5 miles, as well as that it will work till that range. And the endurance has been tested for approximately 20 minutes. I'm in third year of BE Mechanical Engineering. Our crew members are extremely well trained because we have been flying since late March. Even in Michigan weather, we have been making flights every weekend. We're at least trying our best to. We've had a few minor crashes, but we've the experience. And we've had approximately 30 plus autonomous takeoffs, which means
everybody, I'm in my third year of mechanical engineering, and
our testing commenced in March, which also provided us with extensive time to validate all the subsystems and make sure that everything is working in order. Our propulsion system was actually also placed on a vehicle of the first information vehicle, which was delivered to a department on campus. So we actually sold the product to a department on campus, and it has been an active service for almost a month and a half. It's been used for commercial operations. So that also validates our propulsion system because we use the exact same
for the SUAS.
And to talk a little bit
I'm my third year mechanical engineering. This is my second year at the SUAS, and we thank you all for being with us today, and basically we thank everybody else watching us for making us very nervous. Yeah, so welcome to the flight readiness review of Team Edison. This is our 6th year of competing at the SUAS, and over the years we've learned a lot, but essentially our guiding code remains the same. We want to build UAS that is capable of surveillance and search and rescue operations, and we want to make it as removed from manual control as possible. So, as an extension of that aim, we want it to be commercially deployable as well. So we want to use as cheap products as possible, and therefore achieve that aim of being able to conduct search and rescue missions at a very cheap cost. So that has always been a driving force. Now to talk about the secondary link and control station. Yeah, this happened this year while testing. We were having a full mission simulation, and mid-flight, one of our servos got stripped, and basically we had a lot of roll imbalance because the aileron servo had got stripped, and while coming in for landing, the airplane just went into a spiral, and we had this devastating crash. We lost almost all our components, and so these are kind of lessons, especially when you're running on a low-budget project such as ours. These are the kinds of lessons that you learn from from conducting tests, right? So that's where we learn to prioritize safety, design safety, operational safety. That's where we learn to literally imbibe them into our project management skills, and therefore we will talk to you further about how we've done that. So we've actually logged a total of 9 flights, 9 hours of flight time, a total of 32 test flights, and 4 manual test flights with autonomous test flights of 8+ hours. So we have a pretty good testing schedule, and through this rigorous schedule of testing, we have individually eliminated each and every problem and defect that we have in this system. And we have
with vibrations.
So moving on to the airframe that we have chosen for this. And
we did some testing for vibration dampening.
The main objective airframe sub-team was to set up a robust airframe which is capable of carrying an all-out weight of 6 kilograms and having an endurance of 30 minutes, more than 30 minutes. So we divided our tasks and evaluations to establish our flight readiness as static evaluations and dynamic evaluations. Part of static evaluations were using computational fluid dynamics software to evaluate performance parameters, and dynamic evaluations mainly had flight tests, which were basically to find out how much payload we could carry and the endurance time. According to our calculations, we found that our endurance was 35 minutes, but we were able to safely fly our plane with an endurance of 22 minutes. One particular experience which I'd like to share about the airframe would be that of extra landing gears. When we bought this airframe, we didn't have the extra landing gears that you see on the mid-wing. This is because of this, we used to land on the wingtips, and that damaged our wings. So to solve this problem, we had to add these 2 landing gears, and the lesson that we learned from this is on adding the landing gears more towards the end sections, we didn't get a uniform lift, but when we put it here close to the prop wash, because of the turbulence and the minimum lift that we generated here, we allowed the rest of the wing to generate sufficient lift to keep us afloat. So that's something we learned.
We have our gimbal on the bottom.
Also, in addition, we also worked on reinforcing our wings. First of all, the wings were not stable while flying. They used to bend and they used to flex a lot. So what we decided upon is modifying our ribs so that they take care of that. But even that didn't work. So the next step was to reinforce the wings with another set of spars. That helped us a lot. So tiny problems were solved step by step in order to obtain an airframe which could be in a state to compete at a competition like that.
Hi, I'll be talking to you about the electrical and software subsystems that we have in our UAS. So if I could direct your attention towards our UAS layout and our UAS layout. Now, a better understanding of the layout is necessary in order to truly evaluate our readiness to fly. Now, the main point, now we categorized the different points of failure and we identified mitigation strategies for each and every point of failure that we identified. Now, after analyzing the different missions, the subtasks that we are expected to do, we realized that a large portion of a large probability of our mission success depended on us capturing and getting images. So image processing constituted a major part of the success of our mission. Therefore, we concentrated on improving the data flow between our ground station, our board which is our onboard camera, and the camera itself, such that at no point of time is there a failure in the transfer of images or in the capturing of images. So in order to completely autonomize this process, we use a library, we use special libraries to control our camera on board. It goes by the name of G-Photo2. So using G-Photo2, we were able to remotely trigger images. Now in the beginning, while using the software, we had a problem such that if there was ever a loss of connectivity, the camera would stop taking images, and that was not something that we wanted. So after further research and manipulation of codes, we came up with a process that would allow us to effectively take images up till time equals infinity, or we ourselves kill the process. This ensures that even if there is a loss of connectivity, the camera still takes in images, which means that these images are available for us during the post-processing time that is allocated to us. So in no way do we not get images. Also, G422 allows us to manually control the different settings of the camera. Now this is important in cases of changing weather. For example, I mean, you can take the situation over this weekend itself. We had a very sunny weather on Friday, but now if we fly today, we'll have a very cloudy outlook. Now, we have to modify the camera settings according to it. Now, our plan of action is that we start taking images before entering the search area grid, so that the manual operator who's getting the images can monitor what sort of images that we're getting, and if they are perfect for our ADLC algorithm. If not, the operator, based on experience, changes values like the ISO, the virtual, as well as the shutter speed, to get images that are perfect for our ADLC code. Now, loss of imagery data and failure of detection, localization, and classification of algorithms, this is something that we had to deal with. So what we did was we implemented redundancy in each step. Now the camera captures images, it stores it in its internal SD card. It also stores a copy on the ODroid, which is the onboard computer. So there are 2 points in which we can acquire the images from. It also transmits the images to 2 systems. One is the ADLC system, which is totally autonomous. In fact, you can see the ADLC code running right now. This code takes in images from the SUAS 2015 competition. So we have developed our algorithms to simulate the conditions that we get here. However, we've also developed this so that we also acquire images from where we fly back home. So it takes into account a wide variety of terrain, so that this code eliminates all possibilities of false positives from occurring. Now we'll move on to navigation, and
so the navigation team was active ever since we started flying the airframe. So initially we started with the flight controller in a data logging capacity to help the airframe team determine the flight envelope and the limits of the airframe. So once that was determined, we moved on to tuning the gains of the flight control itself. So to streamline the process, we used an auto-tune feature that's available on the 3 Robot Express, which was tested after about 3 flights of auto-tune with fairly rigorous waypoint navigation tasks, which we expected to see at the competition as well. So initially we saw that path tracking itself was pretty good, with demanded and actual attitude changes being pretty close. We did notice that waypoint transition behavior was subpar. So we moved on to different controls that are opened up to us by the flight controller, such as the L1 control loop and a few other features to do with when a waypoint is captured. So tweaking of these loops enabled us to capture waypoints wherein a cross-track error over the entire mission wouldn't exceed any more than 8 meters, which would be well under the objective requirements at the competition. Our altitude hold would be plus or minus 4 meters, which would also be significantly under the objective requirements at the SUAS. So the navigation system itself showed that we were capable of achieving all the objective requirements at the competition. The interoperability task being made primary was also a factor in the navigation system, because it involved a lot of navigational parameters being sent to the interoperability server. So the first step was, obviously after reading the rules, we noticed that our GPS unit was capped at 5 Hz on an update rate, wherein the average update rate required by the interoperability server was 8 Hz. So we switched our GPS and started testing, but noticed that there was certain faults which led to telemetry update rates of about 4 to 5 Hz. So we suspected our GCS, which was running the interoperability code, of being a bottleneck in the system. So we experimented with different GCSs with lightweight deployments to ensure that it was reduced GCS, which we eliminated as. So the next thing we moved on to was the telemetry module, which provided the telemetry data link.
So we had access to
the data link we initially used was a 100 milliwatt capable 3D robotics radio, which was set to a transfer speed of 64 kbps. So what we did was we cranked the rate up to 192 kbps with with its trade-off in link stability, but it did prove to us that the telemetry modules, when asked to perform at a higher speed, did give us the transfer rates that we required of about 6 to 7 Hz. But obviously we couldn't work with a loss of link stability because that would trigger one of our fail-safes during
exactly like this.
So the easy alternative was to go with substantially better hardware, which would be the RFD900 modules, which are capable of operating at ranges well over 10 or 15 kilometers, which compression does not require energy. And so with the telemetry changes, we also experimented with code changes on the flight controller to enable prioritization of GPS, prioritization of sending GPS data back to the ground control station. We did achieve to elevate our rates, but had buggy code. So with within probably a week ago, a new version of the firmware was released, wherein coincidentally the developers made the changes we expected to make, but did deploy a stable firmware. So this firmware in tandem with the telemetry modules that we had and the changes that we made, turned out to give us good average rates of about 9 to 10 Hz, which would satisfy the firmware. So that about wraps up navigation.
We don't know what happened because mid-flight,
this year we decided to attempt sensitive detection and
the previous night all the batteries were shot. They were 60. The charger would have told me, and we also check all the stuff.
One is a form of underlying algorithm.
That's it.
So,
good morning, judges. We are Team US and IMS from Patel School of Technology, Management and Engineering. That's NMIMS University, Mumbai, India. And we are the first year, and the team captain, myself, Vakas Agarwal. I'm playing the role of safety officer, image sub-team, intergravity server. That's my role.
Hi, my name is Shadaj. I am in charge of the electrical hardware stuff for the...
Hi, I am Sunil Patel. I am in charge of mechanical hardware and safety.
I'm Nishit. I'm in charge of I'm the autopilot operator.
Hi, I'm Vinal Rajan. I'm the safety pilot.
Hello guys, I'm Aditya Matri and I'm the flight spotter.
Hi everyone, I'm Pratik. I'm the IS operator.
Good morning judges, I'm Arushi and I'm also an IAS operator.
To start with, we are here with the flight readiness review. We are going to tell you how we are ready for the flight. Throughout, for last 1 year, we are practicing for this competition. And it's our first year and we have many problems, we have really faced gone through, we have faced many problems and we've rectified them. And for that, we have a test flight report too. If someone wants to go, we are handing over that with a proper date, time, wind condition and everything mentioned over that and the lesson learned from that. Okay, I'd like to start with, I will call my hardware team, Chitish, to start with.
Hello guys, this is our plane, we call it the Silla. Basically, I'll just give you all a brief introduction to the system. It's not a very complex system, we are just focusing on a few tasks that are like just the primary task and one airdrop. Looking at the diagram, we are not using any kind of additional circuitry boards or anything except for the flight controller. Moving on the focus to the safety measures, like for our readiness for the flights. I would like you all to go through a few pre-flight checklists that we have. Basically what we are focusing on is doing the stuff we are doing really very good with all the safety measures we are actually performing. Each team member is assigned a particular role which he or she is perfect with. So this is our system. This is a lot of customization with the airframe we have brought. My role in this thing, my contribution to the system has been the integration of all the circuits. And I feel that the best way to detect any problem or error and solve it is to maintain a cleanliness and neatness in the circuitry. You see my system, you will be impressed, I am very sure. Yeah. So moving on to the pre-flight checks, we have a lot of stuff. We make sure there are minute details that we need to focus on. For example, maintaining the CG, checking CG before every flight.
checking all these servos, checking all the other connections and components, whether they are intact or not. We focus, we make sure that before taking any flight, we don't miss any spot from our side. So I'd like to move on to Hamid.
Hi everyone, my role is to basically take care of the plane, like thing instructor physically, it should not be damaged. And internally, like the parts, circuits, cameras, the mechanisms, they should not be damaged anyhow during the flight or during any period. And we check it and we take care that even during a crash, the airframe should be intact. Basically, search it up. The camera is just inside the airframe and it is being protected by the lid, which is it's connected to a servo, which will be protecting the lens of the camera. And the airdrop mechanism basically during the starting phase of a journey, we decided to go through a hook mechanism in which a hook is used to hold the bottle with the ribbons and a zip tie. But as we went past, we noticed that
I'm sorry, I would like to take over. Okay, there are these mechanisms, these servos that we have integrated into it. The main purpose of the servo, the lid for the camera, was that while landing, there are these small stones or something that can hit the lens, and to protect it from that, we have this lid embedded into it. For the airdrop mechanism, earlier as mentioned about the hook mechanism, there we had to use a zip tie, which we confirmed was not allowed. And the second problem that we faced was just in case if we were not supposed to drop the package, then landing was a big problem in that. So here we have integrated a structure over here, tiny structure you can put in the package over here, and using the bungee mechanism. And using the bungee mechanism, we have a servo attached. The servo can be controlled using the transmitter. We just, on a click button, the servo opens up, the payload is dropped. So that's a basic, simple and neat airdrop mechanism. Other stuff that we have embedded into it is using sellotapes. Like believe it me or not, but it is very impactful. When you have a crash, tapes really prevent it from moving. At least the impact is less. So that's all with the hardware of the thing. Now I like what to listen. Thank you.
I'm the autopilot operator, and basically after searching a lot and after asking a few expert people and doing everything, we decided to go with the Pixar autopilot board, which is actually much more stable than any other board available in the market. And for the software integrated with the Pixar board, we are using the mission planner board. The mission planner board, the mission planner software, is actually a very easy to use software as compared to any other software which are available in ATM planner. It shows you all the airspeed, the ground speed, and all the satellites available over there. And you can set up the mission over there. You can and you can calibrate. And for a landing, we actually tried many different types of mechanisms, but we chose to go with the land command for landing, because after a lot of testing and all, we came to know that using the land command, the plane lands much more smoother than any other command. So actually after testing my autopilot system for like 21 days, I'm actually very confident that we will be able to successfully able to complete the primary task of auto landing and auto takeoff.
Hello guys, as earlier explained, I'm the CP pilot for the team, and it's my responsibility to take care that all the connections are ensured, all the connections are intact, along with checking out for any physical structural damages while the pre-flight checking being conducted. Along with that, it is my responsibility to ensure that the drone can conduct a safe and controlled flight while performing all the mission tasks. Furthermore, in the unlikely event of an onboard flight system failure, it is my responsibility and my job to get along in coordination with my flight spotter and my autopilot operator and switch on to the manual mode in the manual control mode and guide the flight to an emergency landing on the runway. Furthermore, we are using a Readiness 9HD 2.4 GHz transmitter, and we have set the telemetry data link at 900 megahertz. And furthermore, we actually conducted flight checks for the past 12 months, wherein we built up 2 prototypes and the final vehicle here. The first prototype was a basic RC model, wherein we determined all the payload capacities that we will be requiring, along with the optimal material that should be used while the construction of the vehicle. And after determining the basic requirements and finally planning out on a task that we need to be fulfilling here, we moved on to the next prototype, that was the Ranger 757. We actually conducted 6 months of extensive testing on that, wherein we integrated all our onboard flight systems and all of equipment as planned to be performed here, which will be required for the task. And we checked out for the efficiency as well as the functionality of each and every onboard flight system. And we obviously encountered a lot of problems. The first problem was that when we had initially started with the Ranger 757, we used an SGX 4000 cam. That's as good as a GoPro Hero camera. And the image quality wasn't very good. We weren't satisfied with the image quality. Furthermore, that was a single motor engine, and in conditions of high wind speed, we actually couldn't get a stable flight. And the airdrop payload capacity of it was very less as per our requirements. So we identified all these problems and we rectified these in our final model, the MDT SIA 260. As you can see, we've gone for the twin propeller engine, the twin propeller motor system, wherein it actually provides a better flight stability in high wind conditions, and theoretically speaking, as we tested it, in the event wherein one of the motors is malfunctioning and it's not working properly, under manual supervision, I can control it and get it back to the runway for emergency landing for a while. I can control it for a while. Furthermore, as you can see, we made a modification to the airdrop payload bay, where we actually attached that. That wasn't the initial model. We actually attached that, we designed it, we created it, and the use of all these fiber tapes and all, it actually reduces any structural damages while vehicle landing. And we've conducted all the flight tests on this model for like the past 3 months, and after encountering various problems as reported in the test flight reports on experiment 10, 11, 12, and successfully retrieving the actual model without any damages, we are pretty sure that this model is actually ready, and we are actually ready to perform all the tasks as we planned safely. Thank you.
Then comes the role of a flight spotter. When I say flight spotter, the question arises, why a flight spotter? So during our test, as my safety pilot mentioned, we had our testing done on Ranger 757 also. So during our testing on Ranger 757, we encountered a problem, wherein even though the plane was in the line of sight of the safety pilot, in cases of emergencies such as improper abnormalities in the plane, in the flight, he could not control it manually because it was out of his visual range. So therein comes the role of a spotter. A spotter is aided by a visual aid such as a binocular, wherein he should continuously observe the flight, looking for any abnormalities and letting the team and the safety pilot know about the same. So as if there are some abnormalities on the plane, I can talk with the safety pilot and arrange the proper maneuvers that he should do to get the plane landed safely. We have tested the same with the Ranger 757 and the SIA 260, and we are pretty confident that in cases of some abnormalities, when the flight is out of the visual sight of the safety pilot, will be easily able to land it down with map avoiding onto projects on
For the search engine task, we required a high quality camera and high shutter speed. So initially, as the Vinay said, we used a GoPro, but the image quality wasn't good. So finally, we shortlisted two cameras, Sony, one of Sony and one of Nixon. And we chose Sony because it was having very high resolution picture and very lightweight itself. Further, for image viewing, there is an internal server with high speed such as far as 13 bps, and which can share the images through a server with the system, and when the data is retrieved and the program is decoded, which will be
we tested various heights, and we started with actually 140 meters, and then we came down to 100 meters, then 80 meters, and then 60 meters. But when we were at 80 meters, we weren't getting very good quality of the images. Then we came down to 60 meters, but we were covering very less area in 60 meters. Therefore, we again went back to 80 meters and then zoomed in from 16 mm to 25 mm so that we can get good quality images, also cover a larger area. Then the next problem we faced was where to put the camera in the vehicle, because the camera has a significant weight of 218 grams. So it is important that it should not interfere with the CG of the vehicle. So we tested it on our spare plane, and then we concluded that it should be placed closest to the CG of the vehicle. As we are a debutant team, we are not very proficient with the image processing systems. Therefore, we have decided to manually judge the characteristics of it.
We are from Project Jatayu, RD College of Engineering, Bangalore, India. I am the team lead, Siddharth Singh, and the safety parasite team.
I am Mukul Seth, the autonomy lead for the team.
I am Mushki Stock. I do the SDA.
My name is Naga Gautam, and I am into the airframe engineering.
I'm Shreya, and I'm the IP lead of the team, image processing.
So right. So our airframe is basically a twin. Is basically a twin propeller. Airframe that is we have done quite a bit of testing on this. It has been about 8 hours of flight in total. So we are the sensor systems. So our system is basically controlled by the autopilot called Pixar. It is interfaced with the Futaba module and the Futaba T7C transmitter receiver module. For the primary communications, we are using Rocket M5 by Ubiquiti, both on the ground station and a decased version on the aircraft. We are using circular polarized antennas both on the aircraft and the ground station. It's alright, we can move on.
So I'll continue the mission planning part of the team. So as we got the waypoints yesterday, I have already mapped them out on the mission trailer. Here goes the geofence, and then this is the waypoint, and this is the search area. So I'll be gridding the search area into rectangular kind of thing. So plane goes like in the rectangular spiral, and then so I have created this geofence, and the parameters we have done. We have quite tested with the auto flights, RTL flights. It has given good performance with all the. We have been trying it out with around 25 feet accuracy, and our waypoints were captured pretty good. And we have done the telemetry part. So telemetry, we are uploading we have connected Introp server, which is our own server for the testing, and we were successfully able to complete all of that. And after the mission planning, Gautam Naga will take over to the secondary task of the system team.
So coming to the airframe perspective, so let's look at the perspective. So what we've done is we've taken the whole plane is built of plywood and balsa. So we have plywood surface parts which run from the far end of the trailing edge of the fuselage to the leading edge of the fuselage. They have a parabolic perspective, a shape, so they will give you a aerodynamic profile, and we
we have added a 1 mm balsa skin, so it gives a nice shape and a structure. And what we've done is we have added these trusses here with the balsa doubles. And what happens is when the aircraft is rolling, it prevents. So you will have all the structures in place. And this is a custom build. We've designed it, we've set around a lot of hours, we've put in a lot of hours. We've designed it, we've got it laser cut, and we've used softwares like SolidWorks, and we've used ANSYS fluid mechanics to try out all the forces which act upon the aircraft. And coming down to the wings, so the wings have a wingspan of 2.4 meters, and we have a carbon fiber rod which is running through the wings. So it has a nice sturdy support, and the winglets. So now coming to the winglets, what we've done is, why the winglets are on scale is we're taking inspiration from the Airbus A320. And why is it jutted out from here is because when suppose the plane lands and it crashes, so this will take the impact. It will not impact any of the wings. So this is one of the safety features we've added. And why we didn't go for a blended winglet? Why didn't we go for fillet? Considering the aspects of carrying the plane and logistics and all of that, it's going to be very tough for us to have a curved perspective. So what we've done is we just split this winglet and it just comes up. We just fit it in, so it has a friction fit. If you want, we can just glue gun it. And how we've carried the plane all over from India is with these boxes. They're coated with 40 mm foam, thick foam. So they're nice and sturdy. And it is beyond more so they're nice and sturdy and it will not budge while we're transporting the aircraft. Landing gears are a little bit weaker than the body. Why we made it weaker than the body? In case the plane crashes, the landing gears start off and reduce the baseline. So thereby we're reducing the impact of the fuselage. And coming down to the bombing way, so we add 2 rows of the bombing way, and here you can see is we are not using servos to lock the bombing bay. So in case by mistake we pull the servos off, the bottle doesn't drop off. So we have a 2-stage door. So first this opens up, and then we have a servo pin. So you can see the lock pin here, and we activate the servo and the pin pulls up, and then you have another bombing bay which just opens, and here you see the bottom. So that's what. And coming to the aesthetics view of the plane, so we've got coated blue and white. Why blue and white? The dangerous, I mean, parts which you have to be careful of. Control surfaces. So the most important and sensitive parts of the plane, so which we don't get a damage or touch. So that's why they've been color coded. That's it.
Coming to the interoperability server, we will be uploading the data into the interop server. So we have made a GUI which you can see here. We can log into this using the IP address and the login credentials provided by the SUAS server. So for interoperability server, the mission planner will be pulling out the data from the mission planner, backend of the mission planner, and will be giving out as altitude, longitude and latitude and the heading of the flight to the server. So that will be, we have achieved almost around 15 hertz of data rate. So I think that is pretty much it. And then interoperability server has a GUI, so it's basically very easy. You log into the server, you get the server time, server message and the date, and then you start posting. Just click start and you start posting. And there will be optional buttons, get obstacles and submit targets. So you can submit targets as well, and you can submit you can get the obstacles which we'll be using for SGF. So that is pretty much simple, very user friendly. You can use it anyone. Like I'm not from IT team department basically, so but I am still handling it because the members couldn't make it to US because it's very far for them and they are busy with their own work. So we have made it user friendly, so anyone can use it with a very basic knowledge. So that's all, and she'll be taking over to the other second part.
I'm the image processing lead. So here the process that we'll be using mainly is that we have most of the processing that happens at the ground station and not on the plane. We have about 2 systems at the ground station. We'll be using one of them to get all the images, and we'll be using that for the primary search area task. And the other system will be holding it using an FTP mechanism, and there we'll be running the ADLC so that both of them don't clash. The process we'll be using for our ADLC is we take the original image. For pre-processing, we'll be doing a basic denoising and we'll be blurring the image, reducing the size. And we'll be splitting the image usage into the BG and R components. We'll be doing this so our efficiency increases and we don't miss out on any of the targets. On each of the BG and R splits, we find close contours and we map them all back to the original image. So we make sure that the contours are closed and each of the contours have a child contour because the outer one will be for shape and the inner one will be for the alphanumeric. So even if the random closed contours are found, they will not be taken as targets because they might not have an internal contour. So we make sure that they're closed and they have a child contour. And once the contour is detected, we map it back to the original image and get the shape. That will be passed through a k-means process. So there we split out the background, the shape and the alphanumeric separately. So we can pass each of them parallelly. The shape will be doing a basic shape search by matching it to templates and finding out which shape it is. For the alphanumeric, we're using test track that's already available. And for color, we'll be converting the RGB colors to LAB colors because those are more perspective based. And using LAB lookup tables, we'll be mapping them to the right colors. And that's how we'll be doing our classification.
Coming to the SDA part, so in SDA what we basically have is, we have obstacles and we have the waypoints already known. So we consider each waypoint as a point, as a circle, and we try to map the path between 2 points, and we then take the obstacles and we put them along the, we check if the obstacles lie in the path. So if it lies on the path, it then tries to detect which is the shortest and the best path. So it will try to take the shortest path and and it will plot another waypoint such that the flight easily can turn and avoid the obstacle. And what we also did was we also have a GUI where we plot all the obstacles and waypoints and the previous path as well as the new path, so that we can know exactly how it does. And later on, this file, there will be a file created that will be uploaded to Mission Planner, which will change the path autonomously. We are aiming for static SDA, so we'll be easily achieving it. Now, me being the safety pilot, coming to the safety aspects for the operation of the aircraft. So first of all, before every flight, I personally check all the control surfaces and the links that connect the surfaces to the servos. Then all the servo extensions have been locked with servo locks that are to prevent disconnection mid-air. And about this aircraft, this has been designed for a total wing loading of 8 kilograms but we are loading it only up to 6 kilograms to keep a safety margin of about 2 kgs. So with these, we are using 13 cross 8 propellers with the motors, which gives us around 4 kilograms of thrust. So the thrust to weight ratio is pretty much in the medium range. We have tested the aircraft at altitudes of about 500 feet, and the pitch angle, the maximum allowed pitch angle for this aircraft, we have limited it to 15 degrees, so that it can continue a steady ascent approach. So then coming to the dropping part, we have Vasishtha here has written a code on an Arduino which interfaces with the Futaba receiver, and I will have 2 switches on the transmitter, in which one of them will be for the safety authority. Until and unless that switch is on, I would not be able to trigger the bottle drop. It is just for enhanced safety. And as we said, the landing gear has been made relatively weaker compared to compared to the airframe.
And so being the autopilot lead, I have made sure that we do a checklist before every flight. So I have made a pre-flight checklist which includes all the servos are intact, all the connections are done, telemetry is connected, all the servers are running. So as you can see, this is a box of this is basically a flight attitude control. We call it flight attitude control, which has 2 GPS. So why 2 GPS? It is again a safety measure. To avoid the failure of 1 GPS, we are using redundant positions. We are using 2 GPS. So that is again a safety measure. And the checklist will be a measure. We had a packaging checklist. We had a toolbox checklist, and then we have a pre-flight checklist, and then we have a checklist for a secondary task. So as well as we are using 4 checklists, the 3 checklists will be done in the pit, 4 checklists will be done on the flight line. So that's pretty much about it. And we are using 3DR radios here, which are very high range frequency for our device. You can use it for very high range. So that is again gives us the high range. This is again a safety measure, so we don't lose connection. And again, so safety measures, we have done 2 fail-safe. If there is a short fail-safe event, if the RC connection loses, plane will be flying autonomously, but in case if we are taking manual control and RC connection loses, it goes to circle if it's a short event. And if it's a long event, more than 3 minutes, it goes to RTL. So it comes back to RTL automatically, and we are using safe to prevent while carrying the batteries. We are using LiPo safe bags so that we don't the batteries don't explode or something. And I think that's pretty much about it, the safety part.
Of things like fire extinguisher and safety features, which can easily, if there is an emergency case, we can easily put out fire and handle emergencies. Last thing, one thing that I forgot to mention is our whole payload system is in this. It just plugs into the rear side of the aircraft, so that it can be easily removed and accessible when we are required to change the machines.
Thank you.
Thank you so much.
Any questions?
I'm Evan Calderon, I'm a senior mechanical engineer.
Hi, my name is Mike Vitas. I do my third year mechanical engineering and I'm an aircraft subsystem.
Hi, I'm River Kai. I'm a software computer engineer and the electronics subsystem.
Hi, I'm David Harris. I'm in software engineering, and I am the operations lead and the...
I'm Kalani Danas Rivera. I'm the image processing lead. I'm also a third-year mechanical.
Hello, my name is Jordan Bayang. I am the financial and logistics officer, and I'm also a senior mechanical engineer.
So this is the first year that we participate in science competition. We don't want to wait out for 1 week and choose, so we decided just to do the primary task. Once we have a certificate, our expect performance for each task is not more confident that we can see at least the threshold ability. We have at least 7 documented flight tests inside the binary practice. We complete these studies one after the other. We have a brief systems. We have ready to control our servos and motors, sensors. So camera we chose is a power shot S100. Overall weight is about 4.75 pounds. The biggest program risk that we have is that we just mentioned that some of us are seniors and we'll graduate very soon. However, some of us are freshmen, so we're going to stay on the project longer. So the way we mitigate losing knowledge is we're a VIP team, better vertically integrated project. So we pass down knowledge from juniors to juniors to sophomores and freshmen. And the freshmen continue jumping on the project year after year. So the entire body of knowledge is constantly our biggest safety risk is propeller. We don't want it to be accidentally armed. If it's somebody, we actually hit the controller. So we only put on the prop and test it outside the airfield for practice. So we don't put it on inside where it's open. Another safety risk we had earlier, and that's first year team, we want to make mistakes. So we're integrating some things with some problems that we have. We look for connectors for a device to make sure that we can integrate it correctly.
now I'll pass it off to Alex to talk about system safety. I'm going to be talking about the system safety procedures for flight mission demonstration. So at the beginning of the day of the demonstration, we follow a series of checklists. The first one being the pre-departure checklist. This checklist will involve this checklist will occur when we're at the hotel, making sure that we have the equipment that we need for the demonstration, as well as equipment that we may need to repair or do any adjustments to the and also, this will also include personal safety and what that we may need, such as sunglasses, sunscreen, bug spray, all that stuff. Once we're at the field, we will do our pre-flight checklist. This checklist will involve procedures similar to the safety inspections, checking all the servos and making sure everything is stable, nothing is loose. And this may also do initial testing with the aircraft, making sure that autopilot is working properly. At the flight line, we will continue our pre-flight checklist to ensure that telemetry is working as well as during the flight we have two safety implementations for requests that will both be manual takeover as well as skill sets. So we're expecting to require 0 manual takeovers for our flight. If we do need a manual takeover, it will likely be due to a on-site failure. For fail-safes, we have 3 fail-safes. The first one is the ground station fail-safe, which will occur after disconnection from the ground station at 2 seconds. The other one will, and this will cause a turn to launch feature. The second fail-safe is the RC fail-safe, which also occurs after 2 seconds of disconnection and will also return to launch. The third fail-safe is flight termination, which will cause the plane to immediately dive out into the sky. At the end of the flight, we will do our post-flight checklist, which involves making sure that connection is safely connected and increase the procedure for post-flight post-processing. Now I'll hand it over to Micah. I'll hand it over to Hawaii to discuss.
Today I will be speaking about the many tests that we conducted throughout our preparation for this competition. The first of which are the flight tests. So before we program the aircraft for flight autonomously, we first had to navigate it manually. That was done through the use of flight simulators and actual real-world flight testing and whatnot. The second of which, autonomous flight, we were able to program it using mission planner. Have the code of our aircraft and be able to fly autonomously through the search area path. The 3 modes of flight that were involved in this competition are auto, I just search area task. The second of which is fly-by-wire, which enables us to manually control the craft. And the last of which is a built-in mission planner function called RTL, or return to launch. So in the event that we lose communication with the craft, it returns automatically to the launch site and then further the craft or Next, our interoperability network was tested to be able to meet the minimum 8 Hz requirement in data transmission. Next, I will speak about the image processing testing. The first of which is the image distance test. So we captured images at a sequence of distances from the target, and we came to the conclusion that at 330 feet, we were able to both identify the target and its characteristics. So we will be flying below that altitude. The second of which is the FOV, or field of view testing, in which we calculated the amount of area captured in one single image. And from that conclusion, we discovered the amount of images required to capture the entirety of the surface area. And the last of which, we will be using the CHDK, the Canon Hack Development Kit, to access the intervalometer of the cannon S100 so that every 4 seconds one image is captured, resulting in a total search area task of 10 to 15 minutes. Now, into you, man.
Okay, I'll talk about the prelim. So we wanted to test our systems to make sure that we would be able to perform the competition. So for our first test, we tested power systems. To test this, we ran our flight system at 50% throttle, and we ended up getting a maximum flight time of around 45 minutes. We also obtained our ideal cutoff voltages as we the trenches. We also tested our navigational systems. So in all of our flights, which is about 50 autonomous flights, we never had any navigational issues in terms of positioning and getting our communication systems, we initially tested them on the ground in clear line of sight conditions, and we were able to obtain guaranteed ranges of at least 1 kilometer. These ranges have also been confirmed with in-air flights. The overall payload of the is about 4.75 pounds, and this is less than the maximum of 5.8 pounds, which is listed in the airframe's manual. And now David will talk about the mission accomplishments.
So we've been talking about early tests. We haven't said how we've been able to accomplish them. And really the key was that we had a place to fly them on Oahu where we had about 1.2 kilometers by 3 kilometers that we could fly, and we could fly in that area without any worry. It was over marsh, but it was marsh that we would be able to cover. Both of these images were taken from that flight area. In this flight area, we have accomplished the entire mission in its entirety. Here, there will be the static display that will be displaying the mission from that area. We have been able to capture images with the S100 with targets that we've made that are on the ground, imaging them so that, and then processing them after they've been taken. We process them by taking the images and putting them through the Mission Planner geotagging software, which takes the images, gets the GPS location, and then we put it through an Excel equation sheet that takes into account the orientation of the craft and gives the GPS location of the corners of the image and the center of the image. Based on that, we can calculate where the target is in the image. From there, we have been able to complete everything according to the primary tasks, which is the minimum to compete. But as we are a first-year team, that was our goal, so that we could bite off more than we could chew. As we've been going, we have had to do a couple design modifications to the original payload. The original had a large dome right here. The idea was to be able to mount stuff in it. We were having issues with heat inside the dome and not being able to mount stuff and then fogging up on the inside of the dome. So we altered this to allow no dome and cut off the chunk here to allow for more optimal flow. Down the original servo for the elevator was positioned here. Way down here was a really long servo arm. We moved the servo down there because the servo arm was bowing and it was not good for the practice. So now I'm going to introduce Micah, who is going to talk a little bit more about what we've done.
So coming back to UHB and a first-year team, we didn't really fully grasp the spectrum of what we needed to be accomplishing for these tasks. So we came to find the guidance of two of our main mentors, Mr. Bure and Mr. Castaldi. Mr. Bure specializes in Mission Planner and Pixhawk devices, so much of the majority of the people flying and doing this competition use Pixhawk and Mission Planner to conduct their missions off of. So using that, we're able to complete our fly-by-wire, assisted manual flight, and our autonomous flight, and be able to conduct autonomous missions off of that. And Mr. Castaldi just has a very vast knowledge of flying RC devices in general. So when we took to actually taking off of the simulator into the real life application of actually manually flying this Penguin. He helped us a lot in finding stability and looking at the characteristics of how it stalled, how it flew in crosswinds and headwinds. So he gave us a lot of knowledge into how we actually should be flying this device. And coming into a little bit more about the actual team, while we're doing our mission, it's split up into about 3 groups. So the first is the safety pilot, so that would be Alex and David over here. Both of them have a combined manual flight time of about 6.5 hours and a total autonomous flight time of 9.5 hours. So they've tested and tried this Penguin. It's lasted through a couple crashes, so it's tried and tested, so we know we're pretty confident in flying this thing during our competition. And the other 2 would be image processing, which is me and Kalani. So after the Penguin comes in, you'll remove the SD card and then put it into the Lenovo. And from there, me and Kalani will hardwire through Ethernet and manually inspect the photos to look for the targets and the descriptions, and from there, hand that off to the judges. And the remaining crew, the pit crew, deals with the startup and breakdown of the Penguin, making sure all the electronics, all the interrupt networks, and breaking down of the Penguin is set up and broken down within the time limit needed. And through that, we've tested everything, and we've done it all within the time limits. So we are very confident that we'll be able to complete our mission statement that we which was to complete all the primary tasks set before us. And with that, I'll hand it off to Jordan, and he'll wrap this up.
So with the integration of the 4 subsystems of aircraft, electronics, ground control, and image processing, we have confidence that we can finish the 2 primary tasks of waypoint navigation and search area. We've conducted tests and we have implemented various safety features along with the entire system. And as a first-year team, as we previously stated, we hope to pass down knowledge gained from this semester to next year's teams, and continuing on the continuity of knowledge for the team. And we hope to accomplish more in future years. But for this year, we have confidence that we can do our tasks. We would like to thank our team advisor, Dr. Wayne Chiroma, and a few of our mentors, Dr. Trimble, Ian Barrett, Ted Ralston, and Mahali.
Hello, we're SUAS, Cornell University's Unmanned Aerial Vehicle team, and today we'll be doing a flight readiness review for the Theseus Unmanned Aerial System.
Hello, my name is Brendan Quinn. I'm the autopilot lead for SUAS, and I've been a member of this team for 3 years, and this competition I will be an MDLC operator. My name is Grant Lemire. I've been on the team 3 years. I'm the Vision Sub-Team Lead, and I will also be an MDLC operator this competition.
Hello everyone, I'm Rahul Holly. I've been on the team for 2 years. For this competition, I'll be an MDLC operator, and I'm a software developer for the team.
Hello everyone, I'm Dan Edders. This year on the team I was the electrical sub-team lead. I've been on the team for 3 years, and at the competition I will be an MDLC operator.
Hi, my name is Nikita Yermoshkin. This is my 2nd year on the team, and I work on the aircraft power systems. Now at the competition, I'll be a spotter for the safety pilot.
Hi, I'm Sam Rosenstein. I'm the team lead of SUAS. I've been on the team for 3 years, and at the competition, I'll be the mission lead.
Hi, I'm Chris LeBrunner. I've been on the team for 3 years. On the team, I'm the airframe sub-team lead, and I'm the safety pilot. In this competition, I will be.
Hi, I'm Kevin Treblesetter. I have also been on the team for 3 years. I'm the mechanical sub-team lead, and on this competition, I will be an MDLC operator.
Hi, I'm Troy Joseph. This is my 2nd year on the team. I'm on the autopilot sub-team, and I will be manning the autopilot ground station at competition.
Hi, my name is Yogisha Dixit. I've been on the team for 4 years. I'm the software sub-team lead, and I will be the lead imagery operator. We will begin our presentation with a system overview. We use the Point Grey Fleet 3 camera to take pictures at 2 Hz and send them to our onboard computer. The camera is gimbaled to ensure that it constantly stays pointing at the ground. Furthermore, we send GPS and altitude data from the autopilot to the onboard computer for geotagging.
The images that are then on the onboard computer are sent to the ground over a link set up by a ubiquity rocket base. On the ground, we have patch antennas that are extremely omnidirectional that are attached to the antenna tracker that we have set up back here that tracks the plane through the sky. These images are then directly available for MDLC software for manual target recognition and tagging. On the autopilot, all telemetry data is fed down to the ground via the RFD 900 Plus. That data at the ground is then immediately linked into our autopilot ground station.
Over on the top left here, you'll see an image of our fuselage that you can see inside of. So this fuselage is movable so that we can change our CG in the case that we need to.
On the top right, we see a cross-section of our wing. For this wing, instead of using fiberglass and Kevlar as our laminate, we use 1/16 and 1/8 inch balsa laminate. What that provides is a very lightweight wing. We also use Mylar, which is professionally made fiberglass, and those are strips that run on the inside of the wing. That created an ID effect that allowed us to make a very, very lightweight, very extremely straight.
This year, since our plane obviously does not have a landing gear, we have a folding prop on the front of our plane so that as we land, we do not break our prop.
And on the bottom of the tube, we see Theseus and Odysseus, and our two planes we built. Between the two, we have over 40 flights, 40 test flights. So, and we've done those flights to get ready for this year.
Theseus is safely secured to the catapult through two holes at the bottom of the fuselage, as seen in the image. The custom-built pneumatic catapult is the same one we used last year to launch our plane design. The system is loaded to 110 psi to launch Theseus and is rated to 180 psi. It has been tested up to 150 psi, which shows that the system is capable of safely launching our aircraft. It contains a safety pin, which has been demonstrated to stop a launch up to 150 psi. If the catapult fails to launch, we can degas the system using a manual release valve. After 40 test flights last year and an additional 62 test flights this year, the catapult has sustained no damage and it has proven to be a reliable device.
This year, we decided to design for reliability and the core functionality of our aircraft. Therefore, we are confident that we will be able to complete the four aspects of the competition. After testing the core functionality up here, we then went on to tackle what we deem as secondary tasks. And we are confident that our system will be able to complete these secondary tasks, however, not quite as highly and reliably as the core four tasks that we tackled. We assessed the major risks associated with the system and came up with procedures and methodologies to mitigate these risks. We developed extensive safety checks to ensure that the failure is small, including pre-flight checklists and both hardware and software-based measures, such as a multi-step throttle arming process. For each failure point, we have multiple mitigation methods. For example, we have redundancy and reconnection logic to mitigate a single link failure to ensure that our system will continue to run even on a single secondary link loss.
The team also conducted various tests to ensure our aircraft safety. For example, the maximum torque the hose clamps can sustain without slippage is 134 newtons centimeter. The maximum torque we expect to see in the air is 78 newtons centimeter. Therefore, we are very comfortable saying that this plane flies very well. Also, the hose clamps will not slip on the top. In addition, we also tested the strength of our wing plate. Our wing plate can withstand 384 newtons of upwards force. Our maximum force that we expect to see during flight is 200 newtons. This gives a safety factor of 1.9, which indicates that the aircraft is very safe in the air. Lastly, we put a distributed load on the bottom of the wing, and this mimics the load that we see at a typical flight. However, the load that we apply is 25 kilograms, which implies a safety factor of 2.5. The wings handle this load very easily and therefore are extremely strong and strong enough to withstand aggressive maneuvers during flight.
Each subcomponent of the fuselage was tested and loaded beyond expected values so we could come up with the best configuration of materials and structures. For instance, each bulkhead of the fuselage was tested in numerous iterations and different loadings, as can be seen in this chart here, to determine the most optimal design pattern. Once that was done, each subassembly was assembled and then tested as a whole in both mock takeoffs, landings, and even minor crashes.
For our software system, we have more than 470 unit tests. And we also use the Travis continuous integration platform for running all of our tests for each increment of our code. And this ensures that whenever we release new code or features, that it follows the exact specification that we designed.
In terms of the autopilot, it is essential that any new development does not impact flight-critical features such as navigation. To ensure that all of these changes are optimal, on each change, we run over 100 build tests through Travis CI and continuous integration. Additionally, we do code reviews over every commit to make sure that multiple people can see the change. These measures ensure that the autopilot will always perform safely and reliably in flight.
Evolution of the electrical design creates a more mature and reliable system. Necessary changes are revealed through thorough testing both on the ground and in the air. For example, we conducted both ground and in-flight tests of the entire power system using features designed into our power board to collect data about power consumption. The entire electrical system will run a detailed test matrix which measures things like maximum current and maximum operating temperature to make sure they are within spec. And each subsystem is then designed and redesigned to make sure every box in the test matrix is filled green with a pass.
The design goals of our communication systems were to make the community have the highest possible quality. We did this through environmental and field testing, as well as through simulations. We started with simulations to try to produce the antenna that has the greatest omnidirectional characteristics. What we came to was what you see right here is a skew planar antenna. It has a much greater half-power beam width than like a traditional monopole, so no matter the orientation of the aircraft, we're always going to radiate towards our ground station. We took this antenna, as well as the patch antennas that are on the antenna tracker, out and did field tests. We stood them apart, about 2,100 meters apart, as shown in a map down there that's on our campus. At 2,100 meters, we connected the links, and we basically, with different wireless modules, such as the Ubiquiti Rocket AC, Ubiquiti Board Amplifier, we tested all of these systems with different antenna configurations. And what we found, you can see in the plot right next to the map, is different performance levels. And then ultimately had us choose what antenna and wireless module we decided on, which was the Ubiquiti Rocket AC and the skew planar antennas.
One of the unique challenges about the AUVSI competition and UAV development is that we must complete rigorous testing before we even ever fly. To do so, we use a number of comprehensive benchtop system testing. To test our autopilot code, we use FlightView, a flight dynamics simulator, in conjunction with a software-in-the-loop simulation that simulates the autopilot hardware. This allows us to fully simulate and test autopilot flights. In addition, we use the same software-in-the-loop simulation to test our ground station software, as well as all of our imaging software through some past flights. Only once all of our systems have passed all of these tests do we put the code in the production system.
We have defined the design requirements as seen on the left based off of the primary objectives and reliability. In order to verify the maturity of our system, we created a bunch of tests specifically to address each of these objectives. Through our repeated success at completing these tests, we are confident that our system is going to complete the competition reliably and safely. Of course, with every design decision, there are going to be implications on the rest of the system. For example, we decided to use a fixed-wing system that is able to quickly and efficiently navigate the entire field. However, by making this design decision, we approved the limitations of a large turn radius, as well as a more complex navigation system. We have additional limitations that we self-impose, such as safety limitations on our gimbal. For example, has a limitation of a 60-degree rotation lock to ensure that on landing it will not rotate past what it is capable of rotating without.
Before each mission, we go through a thorough checklist to make sure we have the required personnel and parts we need to fly. The checklist also helps us with setting up the planes and servers we need to take off. In addition, we have a test flight card that we use to record weather conditions, as well as notes from each of our test flights. The two of these ensure that not only do we get the best out of each test flight, but when it comes time for competition, we'll have a perfect set of them. Our go, no-go list gives us a list of situations that might occur in the field and how to handle them. No-go scenarios are situations where we won't be able to fly until we take the action prescribed by a certain contingency plan. Go situations are things that we must do before we fly, or non-critical complications that we can safely fly through, such as minor command. 2 minutes. For the 15. Guidelines ensure that we handle any complications that might occur at the competition. From our extensive testing, we acknowledge that there are inherent risks with flying an unmanned aerial vehicle. We work to mitigate those risks through design and safe build, redundant systems, extensive training, and repeated successful missions to make unmanned flight as safe as possible.
Thank you so much for listening to our presentation. Please feel free to come up and look at our static display, as well as we'd be happy to answer any questions.
Good morning. We are Team Andro from Embry-Riddle Aeronautical University, and this is our flight readiness review. My name is Nicholas Schultz. I'm the team captain and an autopilot operator, and I've been on the team for 18 months.
My name is Chad Weibel, and I'm an autopilot operator, and I've been on the team for 6 months.
My name is Mark Berry. I am a support crew, and I've been on the team for 10 months.
My name is Dave Lodado. I'm the air boss, and I've been on the team for 34 months.
My name is Trevor Brooks. I'm a payload operator, and I've been on the team for 10 months.
My name is Shamazala. I'm a payload operator, and I've been on the team for 10 months.
My name is Robert Morris. I'm a safety pilot, and I've been on the team for 18 months.
To start off, the Andro system consists of the crew itself, the ground control equipment, and the aircraft. The crew is delegated into 4 main roles. We have the air boss, myself, who is the person in charge of each crew operation, as well as the liaison between the judges and personnel during the mission. The safety pilot is in charge of meeting all safety protocols before, during, and after each operation, as well as having authority for a manual takeover in the event of a controlled landing. The autopilot operator is responsible for controlling the onboard autopilot system for the aircraft, as well as conducting secondary tasks such as the airdrop. The payload operator is responsible for controlling the camera on board the aircraft, as well as secondary tasks like the S-ring mount. This team before you has had 75 total flights in preparation for this competition, 38 of those being full autonomous runs. This is a substantial improvement from our 2015 preparation, as seen in the image. Team Andro is prepared for this competition. We expect to perform all primary and secondary tasks.
The internal components of our 2016 Andron system utilize COTS hardware and are easily available and readily available to our consumers. For our payload subsystem, we utilize an Android smartphone. Our team specifically chose the Galaxy S4 because of its lightweight, compact size, its 13 megapixel built-in camera, and its network capabilities that allow us to complete our expert tasks. For our autopilot subsystem, we continue to utilize the 3DR Pixar. We have had great success with this system, and it has proven its reliability with our previous models. Another reason we choose the 3DR Pixar is because of its multiple redundancy system. One of which is if we utilize an external GPS and compass, the Pixar will not allow the autopilot operator to arm the aircraft if there are significant variances between the internal and the external GPS compass. For our ground control station, we are utilizing Mission Plan. One of the reasons we utilize Mission Plan is because it allows the autopilot operator to easily retest the air vehicle in flight and receive near real-time feedback. we are also able to monitor the health of the aircraft so that any situation does arise, we are able to take immediate corrective action. We are also able to enable multiple fail-safes that give us the peace of mind in case we lose control signals between the ground control station and the aircraft.
This year, we've also incorporated a new open-source module, MapProxy system. MapProxy allows us to take advantage of multiple downlinks to communicate between the PIXOC and multiple programs running on our ground station, such as the 3D Live Display. The 3D Live Display we've developed allows us to display the plane, objects, and waypoints all in one comprehensive 3D environment, which enhances both the team and the judges' spatial and situational awareness during play. Control which we developed to allow the autopilot operators to easily log in and maintain connection with their autopilot interrupt software. We also have these autopilot controllers, the ability to calculate the drop distance for the airdrop.
Our last two software modules pertains to the payload system. The first is fitted with an app that runs the Android smartphone that takes timestamp images and relays it to the ground station. On the ground, we developed a payload control interface that will receive timestamp images. Correlate them with GPS and orientation data to be used later for automatic and manual target detection. The interface also includes a section to allow to set parameters for missions such as the way in which we take pictures, as well as the ability to start the extra task.
When we perform a flight operation, we have potential risks, and we mitigate these through the use of safety protocol and equipment. Some of these potential risks include loss of control to the aircraft, loss of communication link to the aircraft, or LiPo batteries, potential miscommunication between crew members, and health risks. With potential loss of control to the aircraft, we have a safety protocol where if we lose control, the aircraft will automatically terminate the flight by spiraling down. If we lose connection to the aircraft, it will automatically return to home, but if the judge requires us to terminate the flight, I can flip a switch on my transmitter and terminate the flight that way. With our ground equipment operation on our launcher, we have LEDs. That way we know what mode it is, whether it be in safe or armed. That way we can safely operate the launcher. On our aircraft, we have a two-step arming process. That way we can arm the motor independently of the rest of the aircraft. That way we can safely operate within the propeller circle. Also, to aid in orientation during flight, we have LEDs on the wings and on the tail. With our LiPo batteries, we have these storage stacks. That way, if we have fire, it will prevent it from spreading. And also, we have a fire extinguisher in the case we have a fire in the crash. To prevent possible miscommunication between crew members when recovering the aircraft, we have two-way radios in order to establish communications. Also, the autopilot and the safety pilot have a positive exchange of flight control protocol where in an emergency, if I need to take control, I say, I have control.
You have control.
I have control, and we both know who's controlling the aircraft. We also have these safety vests shown here, which clearly show where we are in the flight line, and for the judges, it shows what roles we are, that way they can easily identify us. Finally, for potential health risks, we have a first aid kit, bug spray, sunscreen, and water.
In order to ensure that the Android system can adequately complete all tasks that we have planned to complete in this flight demonstration, we had to run and execute many various developmental tests and simulations in both our lab and on the field in flight testing. In the lab, we primarily focused on testing individual subsystems and then integrating it into the plane. Once the team is confident that the system has been integrated properly, we take it out to the field and add it to our flight plan to be tested later. In the lab, one of the tests that we did was the utilization of a development test server in order to check our interoperability capabilities that simulated the judge's server for the flight demonstration. We were able to connect to the server and transfer data to confirm our capabilities. In addition, as this is the first time that we have attempted the airdrop task, we had to run many developmental simulations in order to ensure successful completion. In the lab, we prototyped and iterated various designs of an air-drop mechanism, and once we were confident that we had found a design that both minimized drag and the risk of failure, we integrated it directly into the airplane. We then ran additional simulations to ensure that the air-drop mechanism would work seamlessly with Mission Planner and other Andron software. Once the entire team was confident that the airdrop task would be successful, we added it to our next flight plan. And on our next flight test, we ran our full mission, and during the autonomous flight, we were able to successfully complete the airdrop task. In addition, after each flight test, we have an after-action review, where the team comes together and figures out problems that occurred and possible solutions to those problems. One of the improvements to the engine system that came up as a result of this after-action review is the payload vibration damper. This came up as a result when the payload operators had noted that they were unable to identify targets in the field due to blurry images. Since adding the payload vibration damper, we have noted a significant improvement in the quality of images and our ability to identify targets on the field. As a result of our developmental tests and simulations, the team is very confident that these tests have improved both the reliability and the safety of the Andron system substantially.
Team Andron has had 38 autonomous flights, 26 of which have met the autonomous flight task parameters of flight, takeoff, flight, waypoint navigation, display, and landing to the objective requirement. Using the payload control GUI during autonomous flight, we are able to complete the search area task parameters of localization, classification, and imagery to the objective requirement. For the autonomous search area parameter, we are able to meet the objective requirement using the PIXOC and Mission Planner. Also using the payload control GUI, we are able to complete the task of auto detection, classification, and localization, actionable intelligence, emergent target, and off-axis target. The airdrop task has been tested 15 times, 9 of which we have been able to meet the threshold requirement, landing within 100 feet, 6 of which we have been able to land within 30 feet of the target, meeting the objective requirement. The ESSER task has been tested 7 times during autonomous flight, and all 7 times we've been able to receive and send the message for ESSER. The interoperability capabilities of Team Andron have been tested using a developmental test server, and ground control station has received a refresh rate averaging 16 Hz. The sense detect and avoid task will be met to the threshold requirement by remotely retasking the plane to avoid the objects. Due to the current limitations of the Andron platform, we are unable to meet the objective requirements of the sense detection avoid task because we are not able to autonomously retask the plane to avoid objects. And the off-axis target, because we do not have a gimbal system, we have to bank to capture an image. Also to note, we have been experiencing issues with the timestamp mismatching, causing target localization errors. Although we believe we have fixed this, we have not had enough testing to verify.
Team Andron performs pre-flight checklists before each mission, the night before. For these checklists, we ensure that all equipment is properly charged, secured, and stored before travel. At the test flight site, the crew is responsible for their own individual checklist to verify that the ground control station, launcher, and aircraft are properly connected. Once the air boss verifies each individual task, he begins the pre-mission brief, where the air boss documents all assigned roles for mission, time of day, flight characteristics, weather, various components. Each test procedure is documented per flight, specializing in a full mission or a secondary task test between. Once the aircraft lands and is recovered by personnel, the crew conducts their AR to ensure that they address any issues that arose during the flight and conduct more tests to ensure a safe and successful demonstration for the competition. Based upon our data from our 75 tests, We are confident that our aircraft is flight worthy for this competition, flight ready and capable. We expect to perform all primary and secondary tests in this competition. We thank you for your time. This concludes our flight readiness review. Are there any questions?
My name is Bahadur. I'm team captain of Unmanned aviation team. We came from Istanbul University from Turkey. It's our second year competition, and this year we came with the same contribution but modified mission systems. According to the last year, we have performed more tests, and also we have improved our emission system performance. All of the systems will be handled with my team members.
Hello, I'm Murat, the safety pilot of the team. I want to talk about the batteries. We use two 12 milliamps per hour battery, but separately, which means we will stop.
It will work till that range. And the endurance has been tested for approximately 20 minutes.
We plan to use 15 minutes flights for each battery. According to our experimental flights, we can fly 23 minutes on hour and 18 minutes on mission flights.
Which also provided us with extensive time to validate all the subsystems and make sure that everything is
Hi, I'm a member of
our propulsion system was actually also based on the legal of the first iteration which was delivered to a department of all missions. So we actually sold the product to a department of
we couldn't perform ST mission because we couldn't add waypoints
for almost a month and a half and it's been commercial operations.
Because
so that also validates our propulsion system because we use the exact same propulsion system.
My friends will continue.
And talk a little bit about the pre-flight checks I will be talking over.
Alright, so hi, I'm Arthur. My job is content creating. Now I'm going to talk about our autopilot and mission map. First, our autopilot is DJ here. And DJ autopilot is a closed source autopilot. And we are using DJ's ground control station for controlling our system. And as you see, these are taken by last year's competition. This figure shows us the standard time for each unit, and also these data is taken by last year's flight. And according to these data, our flight time will be 25 or 26 minutes for this competition, and we will perform tasks in two separate flights. In first flight, we will perform primary test, and after executing the primary test, we will change our battery, and after that, we will perform secondary missions. The most of secondary missions locations will be given us after the setup, so we will determine the waypoint sequence of secondary missions will be determined after setup. So the last I want to talk about our secondary missions time criteria. Firstly, our off-axis missions, this will be stopped at the closest point to off-axis target, and it will be hover for 20 seconds. For SRIC missions, our UAV system will be hover on the SRIC locations for 45 seconds, but according to the mission situation, we can extend the time to 60 seconds. And lastly, we will perform emergent target mission, and we will scan the circuit area that has radius 200 feet. It's based on the last known position. And my friends,
Talk about test section, test cycle, planning of tests, performing of tests, back processing, and system. Also, we can separate the test into three groups: vehicle performance test, mission test, and the final group is full system test. The objective of the vehicle performance test is improving the vehicle performance according to our mission planning, because all of these missions are based on the vehicle performance, so it's so important for us. And the second group, which is called mission test, in this group, the objective is also again improving the performance in order to achieve threshold level. Our first success criteria is threshold level. When we reach threshold level, our criteria rises up to objective level. And the final test group is called full system test. Actually, in this group, in this test section, we simulate the competition in order to calculate estimated success rate for full system and also for each system independently. And also we have a constant number of tests. At the end of the test number, according to data that we collect, we calculate the estimated success rate. And my friend will
Hi, I'm Ozan. I'm the avionics sub-team leader of this team. I'm going to talk about interoperability of Readiness and airdrop missions. We have ATY as my friend mentioned, but in addition we have Pixar to perform these three missions. Pixar is an open source and its ground station also open source program. We customize it for to complete perform this mission. And we connect this Pixar via 400 MHz data link. For interoperability, we basically upload the UAV position to the interoperability server and download the server info and obstacles and display all of them into mission planner. All the mission positions, surge areas, waypoints will be shown there. And secondary, interoperability. I will talk about interoperability test. At the beginning of the test, we have some problem about telemetry update, telemetry upload frequency. But we change our antenna directly via antenna 400 MHz is reinforced. It's reinforced our communication link. Now we can successfully upload and download and display all the components. Second, I will talk about OPEX mission. For OPEX mission, we have gimbal. We calculate gimbal angles and camera angle of view, and we write a tool to compute the altitude we must scan to see OPEX's target. In the mission planner interface, we can do it during the mission. We test OPEX's different distance from fly boundaries from 200 feet to 500 feet. After 400 feet, we can sometimes we take blur images because of the high altitude, but smaller than 400 feet radius, we can successfully achieve the mission. And the last one, airdrop. To complete airdrop, we write the airdrop script. It's basically compute the distance, airdrop point and the distance between airdrop point and UAV, and it releases the airdrop case at a certain distance in beginning of the test. It's 5 tests. Our average airdrop distance 83 feet. After the last 10 tests, we achieved 20 feet. We change our airdrop case and we try and find the distance, optimize the distance to complete that. My part is over. My friend will continue with essay. I'm responsible for the execution. In order to perform SUAS
definition we built an HTTP server from the Raspberry Pi. And then Raspberry Pi, which allows us to control the mission. We send comments from the ground station using this interface. The aircraft, we have Wi-Fi communication, and the Wi-Fi communication will be built between the station on the ground and the followed M5 on the aircraft. These two work with the frequency of 5 GHz. We are planning to perform this task in 45 seconds using this interface.
Hello, I'm Emir. This is my second year in the team, and I'm responsible for the image processing. In the flight, my responsibility is to initiate the image transfer sequence and to supervise the autonomous image processing sequence. For the image processing system, we have 2 computers and 1 wireless bridge on the ground, and 1 wireless router and a digital camera on the vehicle. These 2 systems are linked via a 5 GHz Wi-Fi link. On the image processing software, we are transferring our images to our main image processing computer. These 2 computers are connected by an Ethernet link, and all computers can access the same images downloaded by the main computer, and autonomous image processing is done by the main computer. We can initiate and pause the autonomous image processing arbitrarily, and our software is designed to be modular, so image download, autonomous image processing, and manual image processing is all modular, so if any crash happens or any Wi-Fi link loss happens, all our software can be restarted without affecting others, without any data loss. And
the off-axis target was attempted and fully accomplished, but
our found targets are scored according to the number of properties determined by the software and properties certainty. So because we can only send 6 autonomous image from the report, we are selecting the best score 6 targets and a QRC target. And we tested our image processing system thoroughly this year. Our image processing system is actually based on the previous computation photos, and our success rate is greater with the computation photos. The background is affecting the success rate greatly. We designed the software for the green grass background, and I don't know if you can see the success rate. I know these are some of our tests. I don't know we also have geolocation. In final test, we arrived at 15-meter circular problem for the geolocation. And my friend Ella will talk about the manual image processing in great detail.
60-degree field of view. Hi, my name is Ella. It's my second year in this team.
Such that we can detect as many targets as possible
and search area task, and I am in charge of the manual detection interface.
Most of the targets we have laid out in the
provides us a manual detection hot target and market target. Emir mentioned about that the image sent to the first computer, and after that Emir will be informed about it, and I will reach the both image file and the GPS file text using the ground station network, and after that I will search each photo if there's a target or not. If there's a target, you can see.
Did you have how many robots were in?
If there's a target,
and then what does it
mark the target by having a rectangle around it, and it can be seen in this photo, the second image box. And after that, I will fill the characteristics of target and accept location and
orientation. Location will be calculated by the program according to this rectangle, and also orientation will be calculated by this drawing line. I will draw a line, this green line.
The crash that we
Green line, I will draw a line according to the direction of the letter, and the program will be calculated. After same conflict, the crop image, the crop target, and characteristics of targets will be saved. And also the off-axis target, if target is off-axis, there is a off-axis flag, which signs if the angle is greater than 20 degrees. So we understand this is the off-axis. And right description is the off-axis target. And we will test according to.
Good morning and welcome to the Flight Readiness Review for Team Exhibitor from My name is Charles Donato. I served as the team lead for this year. This is my 4th year on the team and my 3rd year competing. For this mission, I'll be serving as the flight director. As flight director, I preside over the entire operation and make any final go-no-go decisions based on the information from my subordinates. Also, in our flight operations hierarchy, our advisors, Mr. Calderon and Dr. Lady.
Hi, my name is T. Chufa. This is my 3rd year on the team and my 2nd year at the competition. I am Team Exhibitor's airframe lead, and for this mission I will be serving as crew chief, which means that I am responsible for the assembly, the deployment, and the recovery of this airplane.
My name is Jonathan Hathcock. This is my 2nd year on the team, my 2nd year at competition. I served as the avionics lead this year, presiding over all hardware and software aspects of the UAS. For the mission, I will serve as guidance, navigation, and control. I'll be monitoring the autopilot and reporting over the radio the status of the aircraft at all times so everybody knows what the aircraft is doing.
Hi, my name is Nicholas Jones. I have been on the team for 5 years. This is my 3rd competition. During typical operations, I work with the avionics subsystem integration group. And for this mission, I will be serving as safety pilot. I've been flying since the year 2000, 16 years of experience, over 300 hours of long flight time, and over 2 hours on this particular airframe.
Hello, my name is Joshua Dupont. I've been on the team for 3 years. This is the 3rd time I've been in competition. Back home, I primarily serve as the chief machinist and also aid in many other airframe activities. For this mission, I will be serving as the shooter. I'll be responsible for the launching the aircraft, basically just pushing a button and overseeing the entire process. I've had over 30 successful launches, 0 unsuccessful.
My name is Taylor Powell. I've been on the team for 2 years, and this is my 2nd competition. I primarily do airframe fabrication during the year. For this mission, I will be serving as the safety officer. I will be monitoring the weather, the air traffic, and ensuring that we have a safe flight from takeoff through landing.
Hi, my name is Hunter Nessa. This is my 1st year on the team and my 1st competition. During the year, I worked on the airframe as part of the airframe sub-team during the fabrication of airplane parts. During the mission, I'll be serving with the ground crew and also assisting ISR post-image processing.
My name is Brady Siegel, and this is my 1st year on the team, 1st year competing. I serve as a supplemental and this competition will be looking at the which entails operating the cameras first like someone. My name is Cody Jennings. I've been on the team 5 years, and this is my 1st competition. On the team, I am in charge of the catapult and any launch systems or subsystems that go with them. So in this mission, I will be in charge of all the catapult gear that goes.
So our mission goals for this year, we're going to be attempting both primary tasks of flight, including takeoff and landing, and the tertiary tasks, as well as the emergent target and taxi target, and the quick taxi. I'll hand it off to our airframe to speak a little bit about here.
So one of the things that Team Exhibitor prides itself on is that we fabricate our own airframe models. The only part on said airframe that we did not create ourselves is the carbon fiber. The aircraft is made out of fiberglass, carbon fiber, and Kevlar composites with foam ball support. And through our testing of this aircraft and its design, it has proven to be both a safe and robust platform. So it's held it together with, again, homemade 3D printed brackets. We have an electronic brushless motor, and we are held by 2 carbon folding props, which facilitate our belly landing. Now, to our avionics.
The systems on the plane are split into 2 systems. The flight system is comprised of a Pixoc autopilot controller with a RF design 1 watt telemetry link and a Dragon Link long range RC link. The avionics side of the system is comprised of an ASRock B box, a 8.8 megapixel camera, a ubiquity rocket for our data link, and a wireless card for our SUAS system. Our ground station is built using custom computers. We build the computers. They are housed in a single housing with monitors, so it's a quick deployment in the field. Put it on the table, flip it up, you're ready to go. We're also using a ubiquity rocket on the ground station with a sector antenna, so we have point and shoot, but there's still range where we don't have to be directly pointed at the ground. We're also using the Readiness with a Dragon Link long range module attached to it and a joystick for gimbal control. I'll pass it off to Cody for our pattern.
This year we wanted something more reliable and robust to launch our aircraft anywhere at any time. So this year we went with our 2nd generation pneumatic catapult. It is 12 feet long and has a 5-inch wide aluminum rail as the main system, which has an inner 2.5-inch diameter PVC pipe. The piston and rope system. It also has a spring damping system to ensure that there's no damage to the carriage itself. The carriage is made of aluminum honeycomb with an outer carbon fiber shell to help ensure the reinforcement of itself. And also has low friction bearings to ensure smooth operation every time. And also it's designed to be able to be used with multiple aircraft systems. One of the main things that we pride ourselves on is safety. So one of the big aspects of it is safety. So everything is minimum maximum pressure that everything is rated to is 200 psi. But we also have another safety, 167 psi safety valve on the tank itself. We operate around between 100 and 120 psi when launching, and also the tank is a dump tank, and it's all done to where everything is easy to use. Our launch system is a custom switch box that has four switches in series to ensure that there's safety. You connect it via 100-foot shielded wire, which connects straight to the 24-volt solenoid valve, which activates in 0.2 seconds, ensuring that all air is dumped efficiently. And you'll see this in action in the next slide.
Moving on to our test planning and execution. So every test, we write up a test plan and we use a specific format for that test plan. So it starts out with the system or systems being tested, and then it goes into the actual test that we want to perform. There's an example of one right there. The test methodology, so the procedure to go through that test, the expected outcome that should happen, the actual results, conclusions from those results, and then recommendations for further testing. So for flight testing, we actually started out with a surrogate airframe. It was a Penguin aircraft, which is an RC aircraft off the shelf. We used this to test the flight control system, which is still the same Pixoc board, and we used it to learn about some of the things we hadn't had experience with before the aircraft was actually, before our aircraft was actually built. So the first, we did the fail-safe testing on the ground, auto-stabilization, auto-tuning. We primarily used it this year for autonomous takeoff and landing. Autonomous takeoff was done with both hand and catapult launches, so we can set up the parameters for both cases. And autonomous landing was the same thing. We used it to learn more about how you have to set up approach to get a good landing every time. So after we learned everything with the Penguin, we moved on to Sockeye. So the first flight test we did with Sockeye was the autopilot control and navigation tuning. We used the Pixoc's auto-tune feature to tune the control gains. So the pilot will put in natural inputs, and the controller will automatically tune the pitch roll and yaw gauge to increase the responsiveness of the aircraft. During the same flight, we also tune the navigation. I don't know if you can see it too clearly here, but you have the yellow here, which is the rectangular waypoint pattern, and the purple is the actual aircraft track after tuning. These smaller loops are when the aircraft was under manual control. Moving on, after we achieved successful autonomous flight, we moved on to autonomous takeoff with the Western profile, auto takeoff, auto nav, and then manual landing. So we had no auto land yet. We used the experience from the Penguin with the parameters and the setup to set up the same system through Docket. And then we moved on to auto takeoff, auto nav, and auto landing after that, using the same experience that we used with the Penguin to set up the approach correctly and some of the landing parameters. So a summary of the flight test, we went a total of 16 flight tests. 15 of those were successful. We did have one unsuccessful manual hand launch, which kind of facilitated the construction of the catapult a little bit earlier. 14 of those flights included autonomous navigation. 13 of those were deemed fully successful. I'll go into that a little bit later. We did have 12 successful autonomous takeoffs to date and 3 successful auto landings. So during one of our simulated missions, we were attempting to use an antenna tracker system using a picksock with antenna tracker firmware. We realized when connecting through the antenna tracker to the aircraft, some of the parameters, such as the control gains, were translated from the antenna tracker to the aircraft, which made the aircraft fly completely terribly and not track well. So we elected to not use the tracker at all and just manually track the aircraft. I'll pass it out to Jonathan for assessment.
Once our flight test was deemed successful, we had autopilot working, we moved on to avionics system testing. One thing we did was for our flight control system, so to test our long-range radios and our telemetry link, we put the plane on the truck, drove it at least a mile, and made sure the aircraft was still responsible while on the ground. It wasn't in the air. We also did the same thing with our imagery system. We put the imagery system into the plane, drove it a mile or two down the road, and tested the data rates we were getting. And we deemed that the data rates were fluid enough that we could see what we need to see while flying. I'll pass it off to Brady to talk about the SUAS system.
For the ground test for the SUAS system, we used a total of 3 computers, 2 different networks. One computer represented the aircraft, the second represented the ground station, the third represented the FTP server. One network represented the communication link between the ground station and the aircraft, and the second one represented the network for the FTP server. The ground test went perfectly well. We were able to upload and download files necessary. However, when we did our first flight test, we ran into an issue where if we went into the range of the FTP network and got back out before the script finished, it would bug out and crash. So in order to prevent that from happening, we implemented a more robust air handling system.
Once all of the individual systems was tested, they all came together to the systems integration testing. We powered everything on, we flew that aircraft. One problem we were having is the imagery software on the plane was overtaxing our computer, so the SRIC software was running super slow and was not able to pick up the communication and get the files. In order to compensate for that slowness, we integrated the SRIC software into the imagery software. So it's all one software package, and the SRIC software shares time for the imagery software, so it's not being pushed under. These are some of the targets at 300 feet we were getting. We're planning to fly around 300, 400 feet in mission. We can see that these targets are visible. We can read the letters and see the colors of each target.
So moving on to system safety and some of our risk mitigation. So one of the risks we identified is untrained personnel. So once it was determined who would go into competition, each person was assigned a role and they were trained to make sure everyone understood their role throughout. Make sure everyone understood their role and what they're supposed to do. We also have a formal pre-mission briefing before every test to make sure that everyone involved understands what's going on. For every test, we also have Sun System Leads checklist. Here's an example of our airframe checklist. So our airframe and avionics leads each have their own pre-flight checklist in addition to a catapult checklist. that required all those items to be checked off and validated before any go no-goes are given. If any of those checks are not checked or any of those are no-go, the entire operation is no-go until it's fixed. So go criteria is airframe, avionics, and shooter pre-flight checklists are all complete, and then the required personnel all get together. So as we mentioned before, we have a dedicated safety officer that monitors weather and traffic conditions, and safety is one of those personnel that give they go no-go. They are the last person in the chain before myself. If they give a no-go, immediate halt to all operations until we mitigate that risk. We also have our own portable weather station that has an anemometer and wind vane, so we can get the precise wind speed and direction where we are flying instead of relying on power reporting. We also have our own first aid kit and Class BC fire extinguisher if any mishaps should happen. Our batteries are sided with reflective tape, so we'll be able to see them in the event. RC Link is also rated well beyond visual range, so the Dragon Link is rated out to 6 miles. So any point within that 6 miles, the aircraft will still be able to be taken by the safety pilot. The launch sequence requires those 5 switches and clears 4 different personnel before the aircraft is actually launched. So all mission objectives have been tested and proven before we have gotten here. This is not the first time we are attempting any of these. All those systems have been independently tested by themselves before integration to make sure everything works. System performed successfully in the required weather limits.
So we are students of Northern India Degree College, and our team name is Unmanned FC26. Actually, this is the second year for the team, but all 3 of us are first time. It's our first time. So I'm Rishabh Joshi. I'm the captain of the team. I'm Shubham Agarwal. I'm electronics tech. Electronics and communication. She's the intern. Like, we are trying to keep it like seniors are the CEOs here, and the new admissions are interns.
French tried this strategy.
So this is our story at Zeppelin FC26, and let's fly. This is what So, understanding the competition. Last year, in July, this competition was introduced to me, and there were a lot of things that I thought I need to excel on, so that I can participate and lead the team. I was by the senior, and like, do you want to be the captain? I said, no, why not? Sure, that would be a great experience for me. And here we are, and I'm happy that I led the team here in this competition. So basically, being from a computer science background, I try to keep everything the way we design software or something, like keeping the modularity of the software, the abstraction and all that. We study as the OOPS concepts in computer science, the object-oriented and all that stuff. So everything in our project was divided into various modules, and we had a systematic approach for everything. We started with analyzing our requirements, what for to be able to do. Requirement analysis, then we define what do we need to do according to the rule book. Then we design each unit differently, like the airframe was designed differently, the propulsion system, the batteries and everything was designed in separate ways, and then combined what we call it system design, and we system testing for the final flights we took. Here we are, and obviously error handling at each point on. Now the big thing, the expenses was we had construct such a model and all that stuff. So how did we meet our expenses? Was we organized workshops at our places.
workshop to make flights, airplanes, and models like?
For example, just for the starters, we provided this, a simple aerofoil wing made up of chloroplasts for the students.
We can get to know how to design aerodynamic shapes and how it works, which
the safety pilot of our team delivered this workshop, and it was like 200 students at a time. It was a great success. We approximately collected around $1,000 from that. One of our students. I myself took a delivered a workshop in MATLAB for introduction on that. Both were my students. That was a small one for the side.
So are you undergraduate?
Undergraduate. Like I'm in the third year and they are in the second year and first year. These are some of the models that we also made during the workshops. This is a 3D plane. It can take vertical takeoffs and maneuvering skills. And this quadcopter was designed the frame was designed by us. We fabricated the whole thing. Now, the main thing is the airframe. We concentrated a lot on the airframe this year because what I think is quantity over quality. Quality over quantity. My aim wasn't to, do a lot of tasks. It was like do one task and do precision. Let's start with the autonomous flight and all that. So we designed a plane so that it could last long in the air. We had a number of planes. This was one of them. We took a lot of flights in it, and this helped us to understand the working of big software out by them. This is an example of flying wing. This thing. Here we have made this is a flying wing plane. We designed the whole thing. We used the high-density polyethylene sheets, the basic foam we use for building, packing stuff, the electronics, and we carved the wing out using the hot wire cutting. We did all
by using hot wire. How effective is to make a plane with a HTP, that is the foam they are using, and how much it floats, and how good it is, how hard it is.
Within $10 we can make such a glide out of it. And this is two types of testing to understand the workings, the aerodynamics of our planes. One was like this, we just threw it forward and it would glide the way down. This was the basic, we do not use electronics and all that stuff. It was the initial step we took. And after that, had a flight. This is a flight of the same thing.
Really very good.
This is our plane, and we had long flights in it. We used this as the stencil for carving of the wing. Put it down here, and so the workshop also introduces technique to our students. Make you understand how tough this thing can be. Let me just tell you how this works. We tried a lot of testing in this plane, and the height ranges were from really low to 30 meters. 200 meters, 150 also, and we also tried the fail-safe technique, and we let this plane crash. Still, the thing is right here in front of you. This is a little bit, on the taping stuff, but this thing has, survived through numerous crashes. We are really proud of this thing.
It takes about hundreds of flights.
So am I.
And one more incident when we made a little blunder and we moved this wing in our room for calibration. And this wing is intact and the ceiling fan increases. So this is a really quality of the wing, a real quality wing. That's why we call it a tough wing. Other than that, as you can see, we have other electronics stuff. We are using Pixhawk as our pilot system. Last year we had an HK Pilot 32, which is a clone of a Pixhawk. But it got cranked a little bit and so yes, we had to go for another autopilot Pixhawk. We also look for other pilot systems, for example, Piccolo and NASA, from especially we looked on the journals of the last year, what the teams were using, what other teams were using, and after that, this is what we put up for. So let's improvise with what we have. And these are
BLDC motors.
BLDC motors.
It's 1000 kV BLDC motors.
The problem was that if we try to make it very, the performance-wise, we have to deliver a lot of things. So, but in India, we do not have a lot of resources and everything to be imported. We have to wait for months, and the pricing is really high. So we try to provide what we have. So we were limited to 1,000 kV motors that are easily available, and 10 or 4.5 inches of propellers. So it's like you have a limited resource, the best you can build out of it. For starters, we were thinking to go with a single rotor, but since it did not provide us the proper payload capacity, we went for imaging system, yes. Imaging system, here we are using Ternary HD cam. Well, it was easily available. Wi-Fi cam, it is approximately the same thing as 403. But I'm not sure, I think it was easily available and like 1 day delivery stuff. So we went for this and it was quite cheap. This is our live video transmitter. We are using an EM 100 megawatts, 100 milliwatt of transmitter here. Last time we had around 1000 milliwatts, but well again, so we had to work with this. It has a little low range, but well it can do. Next, what we have is the here we are using, presently we have 4,000 milliamperes of 3-cell battery. Yes. Modularity and all the concepts to define what we are using, so that at any point if we have an error or any something unexpected, we can easily so we have a big SOC, which is the autopilot system. GPS system is just mounted inside safely. The power system.
Power system is the battery is pumping. So system you can see
the networking, we are using 3 bandwidths. One is 915 megahertz for telemetry, 2.4 for control. We are using an avionics RC6i radio transmitter, and we are using it for about 3 years. Like the seniors were like, so they used to fly local planes and all that. So this has been really reliable. We also have a 9X, but we need a medium encoder for that, along with the receiver, which increases the weight and the range. It's pretty good. So this is what we have. ground station basically since we cannot show you the system running because so we have some modules of our own transport control system. One is the vision system that is we use for the ADLC task and other such stuff, search area task. The remote data connection we have in Raspberry Pi, which is no more with us. It blew up last night and what happened, I'm not sure, but we have another one and we are hoping to bring the SRC task. The coding is complete. We tried it on our mobile phones and other systems. We connected the same code. We connected to a Linux system in our laptop and it worked fine. And the range was pretty good and the speed was pretty impressive. Within seconds we can transfer and download and upload. Both the tasks could be done within seconds. And the code was really good. Well, it helped me with, it introduced me to shell scripting in Python, so I have 2 more languages than everything. So, well, this competition has got a lot of things. So this is the Linux system I told you about, the Raspberry Pi we would be using.
Raspberry Pi is like a mini computer. We can just we have a computer. So we can implement this Raspberry Pi on a slide and it can work as a computer. The whole thing is a computer can Raspberry Pi can.
So basically, this is our system here. As I said before, our aim this year is on quality over quantity. So our star products for this year would be our mainframe top wing, which we are really proud of, and the unit system we have, which we made ourselves. And yes, we are really, hoping to make software very reliable, and we have very risk testing with it too.
The whole system is very reliable.
Okay, so we're UAV Gilman. As some of you have already asked, we're a UAV team from Northern Baltimore. And yeah, so I'm Casey Nealon. I'm the team captain. My background is mostly in both RC flight when I was younger, and then as I got older, I moved into the controversial field of FPV. So that's where most of my knowledge and experience came from.
I'm the ground control engineer, I guess you could say. I'm mainly interested in home computers and stuff like that, and hardware, so that's why I got involved in the ground control systems.
I'm Chris Song. I'm in charge of the imaging systems and also the safety officer. My background is a lot of photography. I'm editor-in-chief of the yearbook, I was. And also, I guess I'm just a safe person. Okay.
Okay, so first thing we want to show you is our graphs over here. So, I hope you guys can see this. So this graph over here is the amp of the aircraft as it's completing 15 minutes of autonomous flight. This is both waypoints and just circling the airfield. So you can see this is, you basically divide that by 100 of the actual amps. So max of cruise is 56 amps, and we have a 7 amp ESC, so it's nice bit buffer, so we don't have a flight failure where maybe the ESC catches on fire or less buffer. The minimum is 0.1, which is just motors off. And the mean is 11.42 amps. That is really good for us because we're using a 11,000 amp hour or 11,000 mAh 3-cell LiPo. So we're only drawing 11.42 amps on average. That means we can fly very close to an hour, which is far longer than what we need to complete the off-stage mission. So that's what that graph shows. It's a little ups and downs, but
Next over here is a range test for our safety pilot. That could be very bad. So this went all the way out to 2.7 kilometers. This is actually was done on the test plane, the Sky Surfer. We use the Sky Surfer because it's smaller, it weighs a lot less, and it's been with us for a few years, so it's very common to do more tests a lot more safely. I wouldn't want to send this one out that far because it's big and I don't want to hit anything with this thing. It weighs less than like 1 pound. Yeah, so, but it uses all the same radio here, so the tests apply for the radio. So what this shows is at 2.7 kilometers right here, we still have 44% signal strength, and that is on low power mode. These radios have two power modes. The low power mode is 200 milliwatts, and the high power is 500 milliwatts. So if you see that you're getting very low on your 200 milliwatts, that's when you flip up to 500 milliwatts and turn around. So that's another safety feature, but it's nice to see that at 2.7 kilometers, which is much farther than what we'll be doing in off-state, that we still have very solid control.
Yeah, I'll talk about the ground station bit. So we have a screenshot down here of one of our test missions, and this was with a different airframe, but it still shows. Okay, it's Sky Surfer. But you can see again at like 2.5 kilometers, we still have very good ground control connection health, and that means a lot to us for a few reasons. First of all, because a few years ago, we lost connection a lot, and that was one of our main errors. And also last year, we had problems, so while we were having those problems with the PID controls, we were also having problems on the ground with disconnecting and having to restart Mission Planner. Another thing, we're using Mission Planner this year for a few reasons. First of all, it's pretty easy to use, but also for the interoperability server integration, the scripts that you provided us, we really wanted to make use of those, and we found the easiest way was to use Mission Planner. So that's another reason. And speaking back on the connection health, there are two main improvements that we made from last year that are going to help a lot. So the first is pretty obvious, but we actually are using a different laptop than last year. So this is Chris's laptop. It has a lot better hardware than we used last year, so hopefully Mission Planner won't keep crashing from overusing RAM and that kind of thing. And it also has a lot better USB ports. We were experiencing some problems with those USB ports that weren't connecting to the antenna. And the second and main improvement we're making for connection is this bi-quad antenna that we're using. It's a 60-degree bi-quad antenna, so it's two 30-degree cones out left and right. And we're hoping to actually have this directional, someone will hopefully hold it. And it's actually a really powerful antenna that we're going to use, and it's been working out well for us in test flights.
One thing with our antenna, we see a lot of teams with these really cool looking antenna trackers. We tried to do something similar, but in the end it just wasn't working reliably. So we thought the safest way to do it was to go with the low-tech solution, just have someone point the antenna at the light. So we thought that would be much safer than using a sketchy system that we built for not all that good antenna trackers.
I'm going to talk about the photos. So at the bottom left of the poster you can see 3 different photos, and we actually have on our plane, this is our plane by the way, it's a commercial off-the-shelf airframe because we realized that the commercial ones go through a lot of testing, and rather than build one ourselves, this would be the safest option to go with one that's been pre-tested. We have 3 camera systems. The first one is, there's one at the front. There's actually 2 at the front. One is streams live, so we can detect targets. It doesn't have to be very good quality, and it isn't, but we just need to be able to see it, and then we can fly over with our other camera systems. This is an Apple iPhone. Here is a screenshot of, we developed an app that on the, it's going to be on the iTunes store, but after the competition. It shows the coordinates and also the compass heading, so that we can get a precise idea of where exactly it's taking. These two are from this camera, which will be attached from the front as well, and that's just a more high-def camera that just records video the entire time. Yeah, it's processing.
Right. So one interesting thing we can do, this is an option, is with this camera, we have two options. We can either put it on the front and record HD video, on the bottom of the plane, we actually have a cutout here, so we can put it inside the plane facing down. And it has the option to either, it can do both at the same time. It can stream video, which is what this port is right here. It can stream video, and it can also take 1080p video at the same time. So we're going to put that either, depending on the circumstances, what we decide, we're going to either put it up here or back over there, which will either give us an HD video forward or down. And that should allow us to either scan a larger area or look at a more specific area, which also, outside of just this mission, gives it more versatility.
Also, the bottom is protected by, this is just a sample of polycarbonate sheet that is, it's tough, virtually unbreakable, so it also provides good protection.
I would let you test this with any strength test you want.
Yeah,
in fact,
it doesn't break.
This plane has had some serious crashes, as you can see, and the polycarbonate has saved us so many times. The polycarbonate, which actually is that thin little oval you see on the bottom, provides more structural support than the entire rest of the airframe. It's really incredible. But that not only protects the airframe, but the battery is wire tied to it. That's to make sure the battery cannot move from side to side. We actually had some errors with that earlier on in our testing. We noticed it kept tipping to the side mid-flight and then crashing. And we were like, what is going on? So we watched the control surfaces, and they're actually moving in the opposite direction. So then from there, we knew it had to be a problem. We figured out it was the battery that was rolling to the side because the Velcro was not strong enough to hold it in. And we just wire tied it down, and we haven't had any trouble since. So it provides a nice hard point to attach to.
As a pre-flight jump.
Oh yeah, definitely.
So we've all worked together to develop a pre-flight checklist in Mission Planner, and some of this is automated and some of this is manual. The automated ones are sensor reading, so it'll say, for instance, one of the things on there is radio controlling solid. So if the autopilot is sensing a steady and strong connection from the manual controlling, it'll change from being red to green, and that'll also allow us to fly. If it doesn't, we have it programmed in there so it won't actually allow you to turn the propeller on. Therefore, unless you want to go into the parameters and change the pre-flight setting, you actually cannot fly by accident. That's 2 minutes, right? 2 minutes left. You have 4 minutes. Okay. And some other ones we have here are, we have control surfaces. That's one of the ones that's not automated. You have to actually move all of them and check the box off. We have battery levels, GPS, all sorts of things like that. And when we're on the flight line, we're going to go down each and every one of those, verify that it's working correctly, and prepare to go. There are some which are, we can go even if we don't have that verified. For instance, the cameras. There's a thing that says make sure the cameras are working, and even if the cameras are not working, and we cannot get them to work in a reasonable amount of time, we still want to get the autonomous flight test. So that's not vital to the safety of the flight, so we choose to fly anyway after trying to troubleshoot that system.
And they're a completely separate system, and we did that on purpose because in the past few years we've wired them all together, and if something went wrong with the cameras, then it would affect the entire plane, which we decided was not good. If the cameras decide not to work, that's okay. They can just not work, but the rest of the plan is still good.
I think it's worth mentioning too that the main tasks we're looking for, the primary tasks, are mainly just navigating waypoints and looking for targets. We experienced last year we tried to do too many things with the egg drop, with the S-rig, and all that stuff, and that kind of took our attention away from actually taking off and flying. So we're hoping to just hit those objectives.
This year we really concentrated on just getting the autonomous flight down. And we've actually viewed the search task as being secondary to that autonomous flight. We still think our iPhone is going to do pretty well, but first and foremost, we just wanted it to fly correctly. If that happens, at the end of the day, I think all of us will be happy. But we'll be extra happy if
Got 2 minutes.
We'll be extra happy if our cameras and everything work too. First and foremost, we just want the plane to fly safely. Do you want to talk about that?
So we brought a couple emergency things. Fire extinguisher in case of a fire. We got the bug spray to keep the ticks away. I think this is also bug spray. In case we ran out of the other bug spray.
Oh, redundant bug spray, that's good.
Sunscreen, protect from the sun. Dehydration, we don't want that. So we have a lot of water, and also you guys also have a lot of water, so that's great. First aid kit, just in case someone gets hurt. And this right here, this is it's a skin protector and also a pomade, so in case of care emergency, we got that covered too.
And also I think it says on there, it protects you against frostbite as well, so if we have the ice age tomorrow.
Did we talk about the hardware?
I'm Justin Readiness, I'm the safety pilot.
I'm Brian Poe, I'm the autopilot engineer.
I'm Jack Manner, I'm the autopilot team member.
I'm Rachel Mendiola, imagery lead.
I'm Kevin Yang, I'm communications.
Okay, so starting with a really brief system description here with a diagram of all the avionics we have on board the plane. We based it around the FixHawk, which is a really common, well-documented system, 32-bit, plenty of processing power, and safety features. We also have an Intel notebook that's running the payload, Intel Amplified processor, plenty of computation power. Everything over here, including the egg drop water bottle, comes up to 4.2 kilograms, which is 5 times around 1 minute. So here we're at the ground station here. We have several laptops on the ground running stuff from mission planning software to our custom GUIs to some command line stuff. This all goes through the antenna tracker hub right here, which is also controlled by a ATM, which we repurposed last year. It's motorized and will track the plane while it's in the air. Safety pilot, of course, always has the ability to override the system. So that's independent of payload communication. Our telemetry goes over 433 megahertz, gives us nice long range, and Wi-Fi runs from payload, and it's at 5.8 gigahertz high power and long range.
So for flight testing, over the course of the year we have accumulated 55 total flights. That's a total of 22 hours in the air. We have accumulated 20 manual flights with a simulated payload to test our airframe, 35 fully autonomous flights with absolutely no manual intervention, and a total of 14 full simulated mission run-throughs. So we feel we are very ready for this competition year from our testing we've done so far.
So each of the modules were tested very extensively, and this is the autonomous flight test module, which is the three primary objectives that we have. So for the planning of this module, I would plan a series of waypoints in a software simulator and observe how our software simulator would react to each of these waypoints. And we would run the waypoints multiple times in series. Just to verify parameters such as maximum stage angle or normal cruise speed, and all of these parameters we finalized in the air when we were testing it in our various flight tests. And these were all tested in full autonomous mode, so we could get the most accurate, say, the maximum speed, minimum speed, the best loiter radius, the minimum takeoff distance, the minimum landing distance, the minimum turning and the loiter radius, because that's a very big concern for connection speed to the ground. Based on this multiple rounds, we determined turn radius, multiple passes to determine the maximum angle and
other various parameters. So this module is the sense detect and avoid module. So in order to test this module, we had a lot of software in the loop testing. A lot of this testing was done in a simulator, and I would have the virtual obstacle set up. This is our flying field. These are the obstacles, and this white line symbolizes a directed line from the center of the obstacle to the current location of the unmanned vehicle. So from these lines, I can calculate the current distance away from the obstacle, and from there I can set a threshold. Say if it's 15 feet or like 30 feet away from the obstacle, I will take the basin from the nucleus to get away from the obstacle. After I take the basin from the nucleus, say I will go from south to north. It will reduce the current flight path. Multiple flight paths were planned from like south to north, east to west, diagonally. Many of the test cases were considered, and my algorithm for SDA passed every single test case that I do. I'm confident that my SDA will work tomorrow, and it'll work as planned.
So for the planning section of the airdrop system, we use kinematics equations to determine the maximum possible distance that we could safely test from. And then we determined that at 400 feet and 29 knots, we would need 364 feet of lead to drop the bottle on the target. So we'd have to drop it 360 feet early for it to hit the target. For airdrop, we decided to focus more on real-world testing rather than equations and planning and stuff. So we found that we got the most consistent results at 360 feet, 27 knots, and we needed actually 130 feet to lead into the drop to hit the target. Because safety is such a big concern, we also added an big drop enable button into the autopilot module so that we had the final say over whether or not the egg will be dropped.
Alright, so for the search area task, we did a lot of camera testing because it's important that our camera is able to consistently take pictures and that we're able to transmit them back to the ground. So we came up with a couple different parameters that we had to test for our camera. Those are blur, the spatial resolution, and reliability of the camera to take the continuous amount of images while during the competition. So for blur, decided as far as for ADLC reasons that we needed roughly 11 pixels minimum of blur. The spatial resolution needed to be roughly 2 pixels per inch, and the camera reliability, we decided that we needed at least 500 images continuous to ensure that we would be able to compete. So for ground testing, what we did was we did some testing with the camera both horizontally as well as vertically. So we tested horizontally in a field and took pictures. We made replica targets of all the targets that we had during the competition last year. We made small scale targets as well as large full scale targets. And we tested them at full range horizontally as well as vertically at shorter ranges, but with scaled down targets. And then we also used the ruler to kind of measure to make sure that we got the correct amount of spatial resolution. And then in flight testing, we tested it during the full system integration, and we did that mostly for testing the blur to ensure that we were getting appropriate shutter speeds and getting appropriately blurred images so that we could actually detect the targets on the ground.
This is summary of expectations for primary tests. Algorithms running under ADLC. So each of them was tested incrementally, like individually, and then they were tested within the ADLC system, and then within the entire UAS. So the goals for the ADLC testing was to minimize the false positives, so the false alarm rates. Bottom line is, for the ADLC, I ended up with a 23% false alarm rate. Another goal was to verify the safe operation of the software within the full system, and also the reliability. And then for each algorithm, it's important to account for the image invariance. So there's some test data down here from images that we took during the 2014 and 2015 competitions.
So for the pre-mission brief, as a safety pilot, I'm in direct communication with the mission commander. The mission commander will relay information from the 3 team leads directly to me if need be, and also the 3 team leads are in direct communication with each other. So for the go, no-go criteria, we have several listed things, such as whether or not the airfield is safe to fly, whether or not the people, trees, obstacles, or other things. Whether or not the radio links are working, whether the reach test is good, and also is whether or not we have GPS lock, compass variants, things like that. I, as a safety pilot, am ready. I also have the final disclosure as to whether or not it's a no-go situation. The payload control also has to be ready, and also the aircraft has to have full batteries, all the mechanical linkages are in proper working order, things like that.
Although we'd always like our system to work exactly how we expect, we know from previous years that's often not the case. That's why each of our subsystem controllers has their own contingency plans to deal with failures of things such as power, communications, payload, and the plane itself. So what you see here is just a sample of some of our more common problems that we have experienced before on flight tests. We have tested almost all of these on the ground because, well, we've experienced them. In addition, we also tested them in the air as sort of a live fire by pretty much unplugging parts of our system and seeing how the UAS responds. Some responds well, sometimes not so well. In either case, we gain experience that we can use to refine our contingency plans to mitigate those situations in the future. With our experience and our multitude of flight tests, we are confident that we'll be able to reasonably handle any situation that encounters on the flight line.
Alright, and finally our mission planning. So we basically figured out how we're going to do our mission and allocated specific set amount of time per task. So for our autonomous flight and SDA, we have about 4.5 minutes, search area ADLC 6 minutes, although due to the fact that the search area is a bit larger this year, we've actually increased that time closer to 10 minutes, I think. So we weren't expecting the search area to be so large since last year was a bit smaller. So with these numbers, we're going to have to adjust them a little bit. SRIC emergent target airdrop we allocated about 2 minutes. And then we also accounted for a couple extra minutes for takeoff, landing, fluttering, going from one task to another. So in total, we think we should take about 18.5 minutes. We would like to have our maximum time in the air be 20 minutes. So that gives us a couple minutes to mess around. But if we run out of time, or if we wind up spending over 30 seconds over what we were planning on doing, what we're going to do is we're going to terminate that portion of the mission, continue on to the next portion so that we don't eat up all of our time doing something that we're so yeah, and that concludes our presentation.
So quick question. So we're a team of students from the University of Texas at Austin. My name is Blake Younger, and I'm the team captain.
James Goss, system engineer. Wes Adams, mission planner pilot. Bradley Burgess, conceptual operations lead.
Israel Hernandez, configuration lead.
So as you can see, we have a fixed wing aircraft right here. We have 3 computers with us now. We actually have 5 on our ground station. We will be attempting the autonomous flight tasks, so autonomous takeoff, autonomous flight, and autonomous landing. We will also be doing the manual image recognition, autonomous image recognition, the emergent target task, all of the interoperability tasks, and the threshold level of the sense detected weight task. So now James is going to talk about the safety of our aircraft.
So as you all know, most likely, the most dangerous thing about an aircraft, especially one like this, is it crashing. So there are 3 main ways that it will crash. So the first one would be structural failure, we also have electronic failure, and then finally we have loss of signal, which will result in a fail-safe, which will cause it to crash. So for the structural failure, some of the things we've done, we've made these foam wings, we've wrapped them in fiberglass. We have carbon fiber tubes through this, right here, and we have a central wing with carbon fiber tube all the way through. This will prevent any sort of torsion, any sort of braking like that. So even though it's a really large wing, it's very strong, very stable, not going to collapse. We also make sure to do all of our checklists before the flight, any sort of checklist, so we make sure that all the control systems are working properly, the propulsion's working properly, and then we check for our sealing. Secondly, the electronics problems we could have would be including wires coming loose. So we have clips before every flight to make sure they're all clipped in. And we could also have issues with batteries. So with our batteries, we actually have two sets, just in case one of them has an issues, one of them isn't working properly. We have a second set, a backup set, which can power the entire flight for 2 hours. Each set can power the entire flight for 2 hours. And finally, we have enough propulsion to perform 2 actual flights for this competition. And finally, so lots of our C-Link, we use 2.4 gigahertz. It's a very well-known system. It's frequency hopping spectrum. It can't really be jammed for more than like a few milliseconds. So pretty much it's got a couple miles flight range. We can't actually test the range on it simply because A, it's dangerous, and B, it's out of sight before we use action. So all in all, we are not too worried about this plane crashing. It should do very well in different that. And to go ahead and talk about some more range specifications for the test we have.
So we have the range test, and we have a 3D-R rating. And so previous flights, we had problems with it. There was an objective that the competition wanted us to do, which was we needed our safety pilot to fly the plane 1,000 feet away from itself. And we still had to have connection with the plane and the computer. The issue was that when he did that, we lost connection with the plane. So we had to go back and look at it and see what was wrong with it. We realized that the previous 3D-R radio was out of date. We had to replace it with a new one with an updated firmware. And when we did the objective again, and we had connection, 95% connection with the plane. But we also wanted to improve that and enhance it, so we got a 7-foot antenna stand right there. And so ever since we've been using that, our connection has been enhanced significantly. So we're not worried about losing connection at all. We had connection with previous flights, and it's been pretty strong. Talk about speed,
All right, so our aircraft has a cruise speed of about 20 knots. The stall speed is about 19.4 knots. We want to maintain our cruise speed to conserve power for the duration of a 30-minute flight. Reason being, we want to have maximum maneuverability for positioning the plane for various image recognition and whatnot. The plane is rated for a flight with wind at a minimum of 15 knots, 15 to 20 knots, and crosswinds of up to 8 to 12 knots at a maximum. The plane itself has about 50 hours of flight time. About 10 of those hours were dedicated strictly to PID tuning. And one of the things we did with PID tuning was we did a little bit of yaw and roll mixing to kind of mitigate some of the effects of crosswinds during takeoff. In addition to auto takeoff, we also had an issue where the plane would veer off to the left prior to liftoff. So what we did, we ended up decreasing the initial deflection of the elevator to increase that ground impact with the nose gear, so the plane would stay level and on task before lifting off from the ground. As far as autonomous landing is concerned, we did conduct several landings at altitude of 20 feet. Our safety pilot, Mark, would take control of the plane once it got to 20 feet. All we were really looking for is to ensure that it had a proper approach for the final descent and leveling out with the runway and whatnot. We didn't want to risk crashing the plane potentially, but based on the results we've seen, we are confident that we can successfully produce autonomous landing. Besides that, the aircraft itself is supposed to fly at about 225 feet for the image recognition. A lot of our tests have shown that flying at that altitude will allow us to get the best quality of pictures and allow us to get the best results, and that's what we like about bots are getting to that. Besides that, with 50 hours under its wings, we're fairly confident that the aircraft is flight ready.
So for our ground system, you see behind the router here, we have, initially what we did is we decided we were going to use Raspberry Pi in the plane to work with the SDA cast because we want to have very low latency between having an obstacle approach and being able to move around that obstacle. So what we ended up doing was we had the Raspberry Pi on the plane. It was sending, it was working with Mavboxy, which allows us to have two or more ground stations. We have one going to Mission Planner, and the other one was coming over to our interoperability so that we could upload stuff to the server. However, we found that that was not a high enough rate frequency of upload, and we were also doing a connection on those 1,000-foot flights away from our base. So what we ended up doing actually is we decided that rather than risk everything for the mission and lose out on that 10 hertz rate of upload, we decided to put everything onto the 3DR radio and then move the Raspberry Pi code, the SDA code, to the ground so that way it could still send plane coordinates to our interoperability, but at a much higher rate because it was working through the 3DR radio. Since Wi-Fi has a much higher, basically you have to have a much better connection for Wi-Fi than you do for this 3DR radio. We weren't able to get the correct connection with the Wi-Fi. So that's how we fixed that. Also, as you can see on here, this is the interoperability GUI. This allows you to see, judges you all to see where the plane is, where the waypoints are, where all the fly boundaries are, where the obstacles are, all these different things. You can see all the upload rates and everything, longitude, altitude, all that stuff. That allows our mission planner pilot to focus solely on what he's doing over here, so that way he isn't bugged by y'all trying to get information from him, and y'all can always see what he can see. And then to discuss some more about the interoperability tasks we have there.
So the code that was running on the Raspberry Pi is actually now running the same computer as Mission Planner background. It has been stripped of the obstacle avoidance mainly because of the latency. When they were trying to send traffic to the plane, you could see the plane getting in a place where it should have stability. On the GUI that we have we could say with a dotted line around it, that was the radius that we didn't want to get that close to the obstacles, and if we did, we had this. But because of the latency and just because of that, we had to make the radius so large that because it was about a 2-second delay, that can be quite a bit. So we still currently have the Mexico sitting with data and they're also what they make but it won't take it. So instead, we have the two ground station computers dedicated to just dedicated to like itself. We'll have one person sitting here directing west who will be on mission planner. Dealing with place waypoints and whereabouts. And if it's necessary to avoid an obstacle, it would be me. Tell them to select the guided waypoint, which is effectively what we said before. That way the plane will get out of the way, and when it got out of the way sufficiently, it can go back to its original mode, auto, the mission phase. On the other side, right there with that, there are actually three computers that will do the image recognition. There's one that will be for automatic recognition and two for manual. One will have an image in the camera at all times, and the pictures can be saved at a timestamp. After the images are saved, we'll save them later, that will actually upload the pictures that were saved, and it will request the position of the place that we have, and then all the characteristics of the officer can be the camera will be pointed down pretty much at all times, so whenever we have a picture taken, we do know where the center of the image is.
Alright, so alongside manual image recognition, we're also doing automatic image recognition. And this is done via MATLAB, primarily because of its very friendly. So alongside MATLAB, we also are running an open source code called FFmpeg. And what FFmpeg is, it takes a live video stream that we're getting and it converts it to images every 2 seconds. And so the images that are coming from FFmpeg are then transferred into our shape detection algorithm. So for example, this is an image, maybe a little hard to see, but this is an image that is extracted from the FFmpeg file, and there's a green circle right here. This image is then transferred into very good detection algorithm. So the image detection algorithm creates 5 subparts. The initial image, the pre-processing, which basically is blob detection and edge detection. It outlines the areas where the shapes are, and it also crops the areas out. That is then transferred into the blob approximation, which is numerical approximation for the shape with coordinates, and that allows us to determine the shape of the object, and also an HSV file is used to detect the color. So in this case, we have a green circle, which the algorithm accurately determined. A simple example with the yellow square, and the code was able to accurately detect the square. Currently, initially when we started out with this code, we had about a 30% accuracy on detection, and that's absolutely unnecessary. It's absolutely. So in order to fix that, to mitigate the problems, we modified the code a lot. For example, initially during our flight tests, we were getting the lines on the runway were detected as white rectangles, and it took a very long time for the images to process. So we modified the code a lot, and after many tests, we were able to increase our detection rate to 70%. In addition to the image detection, we are attempting to do QR code recognition. We haven't really had much. We haven't really practiced much with the QR image. However, we feel that it is ready. We did use Photoshop images to test our 2 minutes. We used the Photoshop to test some of our algorithms, and they were accurate as long as the orientation of the QR code was feasible. So during the flight, what we plan on doing is, when we're searching for the targets, we plan on flying in a way that we can get the correct orientation of the square of the QR code, and therefore be able to recognize the imagery. This is the output that we received from the algorithm. And now Blake, you can discuss more.
So in conclusion, we've had 50 hours of flight time with this plan over the last year. We've rigorously tested every objective that we want to accomplish at this competition. So we feel very confident in this plane's ability to achieve our mission. That concludes our presentation. Are there any questions?
We are Unmanned from the University of Sherbrooke, which is composed of various experiences. And we're here to show you that we are ready and safe to fly. So first we have team leader Jan. He's on his 3rd year with the group and 3rd year experience with imagery. We have Charles, which is our chief ground control station operator. He's on the 2nd charge. We have Nathalie here, which is the main pilot. He has 2 years experience with various RC and simulated flight. And finally, the rest is Cédric, Marc-Antoine, Alexandre, Benoît. Benoît here is a mechanical engineer, also happens to be a system pilot. The rest is an electrical engineer. And we're new to the team, and we're 1st year of engineering here to follow
To better explain our situation, we'll start with the completion and briefing of the mission. First of all, the GCS will order the team to start the pre-flight procedures. Once the GCS has collected all the goes from the team, he will order the pilot to initiate the auto takeoff sequence. once the plane is in the air, the plane will start the waypoint navigation, and will continue on to the search zone, where the plane will do a back and forth search pattern for all the targets. Because time is critical for such a mission, each one of these three objectives, the questions will only be done if we have enough time to do them. So once all of them are done, or time is up, the plane will go on, will continue for its autonomous landing, and the GCS will proceed to its post-flight procedures, where it will turn off the radios and park the plane away from the runway. Then the team will start the post-processing. Weather is a very important factor when operating a UAV, especially a small one. The rain, for tomorrow we can expect a lot of rain and a lot of wind. So for this reason, we do not think it will be safe to fly tomorrow. Fortunately, for the next 2 days, we expect much better weather with winds that are less strong but still there. For the intentions of the team, we give them mistaken, give them this flight, this search, actionable intelligence, emergent target, interoperability, district, and the attack system. The team will also attempt the ADLC, the sensitive deploy, and won't attempt the airdrop for reasons that Matt will explain later. This is a small technical overview of our plane. The most important part is the autopilot. The autopilot is a pixel, and it is connected with GPS and the actuators of the control surfaces of the plane. There are two wireless surroundings for this autopilot. The first one is the RC link for the pilot. It operates on 2.4 gigahertz, and the secondary link is the high power 900 megahertz extend. This is all connected with GPS. You can see an example of our previous mission a month ago. And this computer is connected to the interoperability server to give the position of the UAV at high frequency. The payload of the aircraft is composed of two cameras and a wireless link for the street. The main communication channel is a 2.4 gigahertz ubiquity Wi-Fi access point. The onboard Linux computer communicates with the video server, which is our custom software called Episcom, which allows many people to work on the pictures at the same time, which enables very high efficiency. The second payload is the S-Ring link, which uses another one of this Wi-Fi access point and enables us to access the information contained in the string. So next up will be Alexandre, who will talk about the safety procedures of the team. These systems are fun, they work well, but they can also be dangerous. So these are the main safety risks we found, and now we mitigate them. First of all, with the plane, the electrical motor is quite dangerous. This is why when the power is on the plane, everyone has to stand behind the wings of the plane at any time, and there's no reason for it. On the other side of the wing, and we also have a mechanical switch that allows us to disconnect the power going into the motor to ensure it won't start up without any reason if we don't want it. We also use LiPo batteries in our plane. So we have all the safety equipment necessary to manipulate and recharge them safely. So we're talking here about 12 glasses and wires, a complete recharge station with current control and a little safe bag for transport. During the mission, the environment can affect our team health. So at any time during the mission, we provide our team with sunscreen, bug spray, and water to ensure everyone is in good condition. We have also informed everyone about Lyme disease problems, because it's not something we're we have in Canada normally. So now everyone is informed to check their legs for bites every night to ensure no one has got bitten, and if they have, can react correctly. For the human errors that can happen during the mission across the problem, we have checklists that we go through before every flight to ensure everything is going well, and we did as much ground simulation as possible before going into the real competition to ensure everybody knows what they have to do. Now, if something was going to happen during the mission for any reason, two of our members have CPR formation. We always have first aid kit with us, and we are extinguisher. And everyone on the team has health insurance with United States. In the long term, we always fly in conditions that we judge safe and design. Safety is quite a big design criteria. For example, we decided not to use an X8 at this competition because it would have been too dangerous to end launch it. Now, on the flight, if we ever lose control of the plane, it became a big safety error. And when we talk about host control, we're talking here about GPS losses or IMU or mechanical failure on the plane. If possible, our safety pilot would take control of the plane and land it back safely. However, if this is not a possibility because the failure is too big, we can at any time kill the plane to ensure the safety of everyone on the base. Now, if we lose communication to our plane and we're not able to communicate with it until the kill us, after 30 seconds it's going to turn on if we are not able to take back control either, so we kill itself according to rules.
As you can see, safety is paramount. However, we cannot properly apply it without proper testing. This is why it was our year the school starts in September, where we analyze the environment competition and choose what will be our plans for the year. This is also where we start our first tests with our new members who will join the team for the years to come. During the fall and the beginning of winter, we start heavy development and subsystem tests. About mid-January is where we start the airframe test. So we go flying during winter, and after around 1 month, we decide whether the plane has a go. So in which case we will finalize and stabilize the airplane for the next competitions, or if it has a no-go, in which case we will fall back to previous proven version of the plane so we can move on and complete safety competitions. Once the plane is safe to fly, we start flying with the autopilot. The autopilot has to go through the same measure, the same evaluation. And once the autopilot is chosen, we start the imaging test in flight. The imaging test then go through the same, have to pass the same requirements. And once the imaging systems are tested, we plan a mission simulation. Our first mission is the US expedition, which happens around the 1st of May. And right as we come back to the competition, we finalize our advanced test. So, for example, the ADLC, the SREC, they are the kind of tests that we prepare around the beginning of May to make sure we are ready for the US competition, which happens right now. Now, this doesn't explain how we integrate a brand new subsystem to the plane. So we start with development and some tests in the lab. Once the sub-tests in the lab are promising, we go to the integration test, which is where we integrate the subsystems into the airframe, but do not fly it. We instead simulate flight by walking around and having the plane into the car. Once these integration tests are conclusive, we fly the in-flight test, and once these tests are successful, we start the mission test, and we finally bring a new subsystem to the competition. However, nothing asserts our capability to complete this mission safely as much as a similar mission. Unmanned Systems Canada competition is a competition we participated in about 1.5 months ago. We completed 3 flights of 15 to 30 minutes. We reached 1 nautical mile distance between the plane and the ground control station. We completed 6 airdrops and recovered 5 QR codes, which was the maximum possible. Retargeting, target search, and use our access target for the target detection. This mission does not other secondary tasks that are only present in this competition. However, the serve observability were tested in previous years, and since then, improved upon and more structural. And have been thoroughly tested in the field to ensure we're ready for these benchmarks. For some more specific important subsystems, airframe, it was designed as Artemis. It was designed in 2014 to comply with the 50 iterations of airframe. We have more than 3 hours of testing time, and has been seen at each 50 minutes. We have also developed wings of up to 15 knots, and have also been able to transport a payload of up to 9 pounds. Now, for the autopilot, this year we switched from the paparazzi autopilot to Pixel because paparazzi used infrared sensors for its timing, which prevented us from auto data. So since we switched to Pixel, which is 2 hours takeoff and autonomous landing, we have more than 12 hours of flight and have reached a distance of 4 nautical miles. Now, the imaging system, which was designed 5 years ago, and we are currently flying the third iteration, which improves our second iteration with a higher processing power for secondary tasks such as the S-ray, and also a higher image capture frequency. We have taken over 40,000 pictures with various simulation missions. We have the camera able to obtain a steady rate of 25 images per second for the main DSLR camera and almost 4 images per second for the second. The geometry section is usually around 5 feet, and the duration is also 4 nautical miles. Now, the subsystem that we have tested is pilot up to about 3, but since we had issues with sending the water bottle to the drop, the application decided not to try. The QR code system. We have simulated the QR code detection with a very similar QR code at altitude of 150 feet, which is what we tried in competition. We cannot kill this target directly, however, with multiple processes in order to come to the target. The link. After it, we are going to repeat the this position does not require a link between the GCS and the plane, which prevents a lot of troubles. And we have about 3 seconds connected time to watch the mode around the S-ray. We also tried to fly over mode. The test showed that we get pretty good results.
Alright, so we would like to thank you for your attention, and we believe we are really ready for this mission, and we only fly safe. Thank you.
I have some copies of the safety procedures and checklist my colleague talked about that earlier. So I'm going to pass them to you for look at. Unfortunately, I only have 6 copies, I think, so you will have to share.
Good afternoon, folks. We are the UC San Diego Autonomous Airplane Team, also known as UCSD. I'll allow my team members to introduce themselves. My name is Michael Flowers on this opportunity. I'm Dr. Mike. I'm Leonardo.
My name is Glenn Wally. I'm the co-airframe team.
I'm Anton Q. I'm embedded system.
I'm and my name is Ryan Coop, and I'm the overall product manager and team captain. This is our 13th year for meeting, so almost as long as this competition's been going for. And we believe the system represents our most robust platform as a result of 13 years of lessons learned, past experiences,
and probably every single mistake you can make in this competition. This year we will be attempting the following mission tasks: autonomous realty tending, autonomous flight, autonomous waypoint navigation, interoperability, SDA, ADLC, emergent target, SRIC, and QR code, and actionable intelligence, ADLC, which I made. This year, this year's system constitutes the refinement of our custom-coded student design software system, which handles not only target classification and waypoint navigation, but the overall prioritization of mission tasks. The autopilot configuration, which contains, has also been tested over many hours in different repeatable test platforms, in addition to this airplane, amounting to upwards of 30 hours. Let's talk more about our airframe.
So this year we're actually flying a commercial off-the-shelf package. It's the Rascal 110. It's about 6 feet long, 10 meters wide, speed around 30 miles an hour. We fly it at about 20 pounds. It's a pretty fully wooden airframe, so it's RF transparent, which is good for what we do. We also mount the antennas as clearly as possible, given space and seatbelt issues, and that's to keep it as far away from the as possible.
We use a gear motor that's rated for 2,500 watts of peak power and 1,250 watts of continuous power at 25 amps. Our ESC is rated for 60 amps, so we're looking for the batteries we use for the motor are two 6S 5,000 milliamp hour batteries. They're connected in series, so the voltage is around 50 volts. We also have a secondary battery for all our other electronics, and that's a 4S battery. That powers everything else that runs at around 12 volts or 5 volts. And since there's such a large difference in the voltage and the power of the two systems, the two separate power systems are completely electrically isolated through an opto-isolator in the ESC. The flight batteries are a limiting factor in how long we can fly. They allow us to fly around 25 minutes. The payload battery, however, that powers all the radios, the onboard computer, and the servos, that lasts around 2 hours with all the systems on. So that allows us to have the plane on and functioning on the ground, where we could do like configuration on the onboard system while it's on. And that also allows us to have it on the ground in standby and have us ready to take off very quickly. Since the payload battery life is so much longer than the motor's battery life, the motor battery runs out longer, we still maintain like full control of the aircraft and full telemetry limits, and that way we could land it without the motor or like guide it into a safe space for a we also monitor the payload battery voltage through our ground station system, and that allows us to know when we're about to lose power for our telemetry system. When the plane is on the ground, since the motor is fairly powerful, to safely work on the plane, we have a shut key that physically disconnects the motor from the power system. An advantage of having a shut key at the power system is that the person working on the plane can have the shut key in their pocket, and it would be impossible for some other member to accidentally switch on the plane due to miscommunication or something like that.
So we have over 9 hours of flight time on this airplane, so we are very comfortable working with it. And before every flight, we run our pre-flight checklist to make sure everything is on there and working properly. Some of the items on our pre-flight checklist includes checking the internal electronics to make sure that they are powered on and working, and checking the airframe components to make sure that they're all secured tightly. Overall setup time and completion of this checklist is about under 10 minutes.
While we're performing the checklist, the thermal safety switch actually has the additional protection from unexpected arming of both the servos and throttles. This is actually one of the major reasons we chose this platform to take on. Compared to the APM 1.6 we used previously, it has a 32-bit processor with a side failsafe processor just in case of system failure. And almost all the sensors has a backup accelerometer and gyros, basically ensure the overall stability of the system. And faster CPU, more RAMs gives us a better performance during air. And we know telemetry data is very important, so this year we actually implement almost all of our radios. Telemetry data can be transmitted through both the 900 megahertz and 2.4 gigahertz radio, so we're trying to make sure telemetry data is always accessible. In addition to this, we have 2 antennas for each radio in different orientation for signal diversity. And Pixhawk, this platform can handle 3 types of failures. First will be RC signals for throttle if it's down for more than 1.5 seconds. That will guide the plane into circle mode, which will loiter. And if it's more than 20 seconds, it will try to get back to the launch position and loiter at 150 feet. Same thing for the telemetry. If we lose our telemetry heartbeat messages for more than 20 seconds, it will also go back to launch. And also this year we have the extended Kalman filter implemented, which means if we lose our GPS signals, the autopilot can actually calculate the location, the velocity, angular orientation based on all the inputs from GPS, all the left sensors, GPS, gyro, accelerometer, airspeed, and so on. So just to make sure we have all the sensors.
My job is to operate the ground control station, which is mainly responsible for interacting with human operators by displaying flight data. But it is also important piece of software for integrating different parts of software companies. So one of its jobs is to send GPS data to the observer and pass them. And using that information, takes the position of the plane and then calculates whether the plane deviates from the ideal path, and if so, it makes it generates a new set of breakpoints that attempts to correct the path. And that reduces the likelihood of the plane going over the flight zone. And another job the ground control station is responsible for is checks it communicates with the onboard computer and check whether the piece of hardware are connected properly. And if any of them lose connectivity, then it receives the signal that it has been lost.
So the main focus of our software system this year was reliability, safety, and completion of mission tasks. And so for our software system this year, we attempted a new task, static SDA. And so that's pretty much created a new module, and mission planning. And then for our command center, we updated our communication links and increased the reliability of our computer. And we, of course, improved our computer vision system for better results. And so for our communication links, for status updates, the status update is late, I don't care about it anymore. And then we explored HTTP APIs in most of our different modules. And so this is going to allow, in the future, instead of having the operator pretty much like turn on S-rig and stuff like that, the mission planning module itself, and just call the HTTPIs when it's on a certain mission task. And so it's pretty much the communication system is built in a sensible way for the future to continually automate our platform. So we have on the ground level command center right now, and so the operator can manually check the onboard computer and see what's going on and make sure that everything's working correctly. The onboard computer itself, all the tasks auto reconnect if there's failures, and the OBC itself, if there's a power loss, it will automatically turn itself back on. And so on the onboard computer, we changed the first part of our computer vision, which is CLT, to crop out targets of interest. And then we send those to the ground. The other one, the first one, we start figuring out with a number of targets in the 31, false positive of 85, and false negative of 62. That's not bad. And so when the props are sent to the ground, they can be sent to the ground pretty fast because they're pretty small. The rest of the computer vision system then filters out the props that aren't targets by through like a deep convolutional neural net for our OCR. And so pretty much if the deconvolution neural net and also the shape recognition, if they don't recognize the targets, then in the last stage of our pipeline, we pretty much have an aggregator, which because we're getting multiple looks at each target, can then say based on location and also attributes, we can just filter out the targets and we can get the best clusters of targets. And this is also important because after we go over the search area once, we get pretty much targets of interest. We'll talk about that later, but pretty much we go over the search area again to get better pictures of the targets, and so the aggregate gets even better. Because if we have 10 pictures of the same target, then we can choose the best target. So yeah, now to talk about our test field procedure.
So in order to actually test features, someone has to fly the airplane. That is me. Test flight, test pilot, and as a test pilot, flew the airplane. And for this, I flew a lighter foam model in order to less risk of failure. But for this airplane, I used my prior RC experience in the desert. What I did is I gave my user input and feedback as an RC pilot to help me tune the autopilot. So during autopilot testing, maintain a line of sight with the airplane at all times. And if they made any jerky movements or they lost altitude during the plane for some reason, any abnormalities like that, I would point it out to the embedded team, which is the autopilot system, the adjustments, and push the result again, giving feedback, repeating to get the best performance.
So these three aspects altogether make sure that we operate safely. Since I've been with the club,
always avoid the autonomous system and also create a viable path. So first step is to generate a path for the entire machine. So this will just take this connecting. We also automatically generate a path for the search area. Focus for generating a path for the search area is to generate a path for the target path and the search area.
Something we usually will end up doing similar procedure in these kinds of flight testing. And we're usually doing flight testing, 5 minutes
testing this type of path.
So
after you generate this path, check
have our
never define obstacles.
like 8 hours on the airplane, different tests that we attempted, like 15 flights, it's 20 minutes, that's airplane for last year, so
and so we had to do that. We had a batch script that ran and continuously tried to connect with Esri. And we had range tests to ensure that we connected and were able to download and upload to the ground station. And so we tested a lot of times to make sure that it worked well. And another one was emergent target. And to do that, we used a library called Readiness in order to upload the additional waypoint of the emergent target to the end of the path. And if that didn't work, we would use Mission Planner and manually input it. And then for secondary passes for the Heimdall, the computer vision system, we did the same thing, appending the waypoints to the end.
Thank you, Matt. Thanks for coming to the Edwards This is the pleasure speaking with you. Thank you for your presentation. We'll be happy to take any of your questions.
Roles at the flight line. We'll be giving a system description of our system, as well as the system risks and mitigation strategies for those risks. Then we will discuss our testing plan, the tests we conducted, as well as the results and lessons learned from those tests. This leads into our expected mission performance, and finally we'll be discussing our pre-mission brief.
So my name is Oliver. I've been with the team for 3 years, and I will be manning the ground control station.
Hello, my name is I'm Nathan Trielli. I just joined the team this year, but I've been working out at Western University for 3 or 4 years before that, and I'm doing the payload control station.
My name is Eric Chow. I'm going to be the safety pilot today, when we fly, and I'll essentially be assisting as the communication relay and I'll be running some of the safety checklists between ground control and the safety pilot.
So my name is Ricky, and I'm the safety pilot. I've been with the team for 4 years, and I've been the safety pilot for 4 years. So next we'll be discussing our systems.
So just begin with our airframe is a fully customized design. We've been building it as a team for the last 3 years. It's a pusher prop with the electric motor power plane, and it's made primarily of carbon fiber, wood, and balsa wood and plywood. And it's also a modular design, as the front and after fuselage can be taken apart easily and substituted if there's any crashes or whatnot that ends up breaking the fuselage. Any quick fixes.
Our payload system consists of 4 cameras. The primary camera is the Bell & Delta TSC-4096. It's a 12 megapixel machine vision camera that's run by an override onboard computer. Our second camera is the Xiaomi E action camera, which is hidden underneath, but this gives Nathan a real-time view of the images on the ground. Our third camera is the Canon SD1200 IS point-and-shoot camera running the Canon Hack Developer software. And our final camera is the EasySBC Quadro from Vision Components, sponsored to us by MDA Space Missions. And that's our final camera at the front here.
So our autopilot is the 3D Pixoc. I'm sure you've all heard of it many times today. So we've been refining this system in our aircraft since 2013. We're using the plane software. And we essentially use it in conjunction with several softwares, including GPS, magnetometer, accelerometer, airspeed sensor, and sonar for altitude to receive inputs from the ground control and the safety pilot if necessary. So our intention is to fly the entire mission autonomously, and then this is how we're going to finish up.
Yeah. So in terms of communications with the ground, air to ground, we have the telemetry unit. So this really big turn up here is our 900 MHz telemetry unit. It's a 1 watt transmitter, lets us get up to around 40 miles of range. We have a RC manual override link. It is a 433 megahertz 1 watt transmitter. We also have a 2.4 gigahertz redundant link in the case that the 433 goes down, or vice versa. We also have a 5.8 gigahertz video transmitter that Nathan will be able to view on the ground in real time as well. For a ground control station, we have a GAI computer. It has daily readable screens and a pretty powerful processor that lets us do everything we need to. Great. So with system safety overview, it's a very big plane, so there are many inherent risks involved with this. And some of the things we've noticed is that it's a heavy plane, it can look really fast, it's fast-moving propellers, and it has lighter batteries inside, which means in the event of a crash or any other case, they can explode, cause fire, lots of damage. So in light of this, we put safety at our #1 priority. So with safety features, in order to make sure batteries don't go down too low, we have a battery monitor. We also have margins, so at a certain voltage, we won't continue to play will actually land to make sure we don't crash. And basically, we have shielded servo wires such that we don't have any interference between the servo, basically between anything, so we don't have any intended accidents. With safety procedures, the US will only be operating within line of sight or ground control range. And in case of any emergency, we'll automatically terminate the flight to prevent damage. So safety features are our plane is made for durable wood design, such that upon crashing, the plane breaks apart, releasing the engine faster. And basically, separate forward and afterwards basically allows us to replace parts in demand. And safety procedures, we have a list of procedures that, so in case something happens, we know exactly what to do. So risk management, we have 16 risks that we've identified, as well for this machine. 4 of them are accepted, and the rest are not. So right now we have these top 5 risks. These risks are the point failures that basically, if they fail, our player comes out of the air. We can. Like the top one is if our RC multiplexer link fails, then obviously we can't fly. But we basically mitigate these risks to such a degree that they're very unlikely to happen.
So our results and development of our tests. So we've been developing this as a team for the last 3 years, and this year we saw results from that. So we went through the major progress here of unit testing, the integration, simulation, then we went into autopilot and full flight mission testing. So just with the autopilot itself, we broke it down to five steps. First, begun with the full manual flight test. Then we did the waypoint navigation, and then took it on to the autonomous takeoff, the autonomous landing, and put it all together for the full autonomous mission. So this is just showing our autonomous waypoint navigation, how we were able to do it. This is at the Unmanned Systems Canada competition in May, and it's just showing that we accurately followed the waypoints that were given to us. And then this is 2 videos of our takeoff and our landing. We'll just click on the takeoff. So this is at our RC field in Toronto. So takeoff, and then the landing right after. So from our autopilot testing, there's a couple lessons learned. One big thing is understanding all the parameters in the autopilot, make sure that we're able to tune them properly. One thing with auto landing is we ended up having a lot of crashes because we weren't able to hit the right descent rate and flare tuning. It was very sensitive, that's what we found. And also we were able to make a lot of manufacturing changes. One was with the nose gear setup. We had to change how it was built just because it kept cracking on this front face here. And also we ended up having a dedicated autopilot fuselage because when we were testing this autopilot by itself, we don't need all the cameras. So we have this phone that we could swap in the front just to ensure that we'd be able to take the impact but still be able to make changes on the field if you do.
So in terms of payload, our payload testing plan consisted of lab testing to make sure that the cameras perform as specified. Then we customize the payload such that we can make the payload behave as we want it to. Then we mount all of the payload into the airframe as our test line to get test data and get the target. At this time we also test our payload link to make sure that we get a solid link between the FPV transmitter and the receiver on the ground. And finally, we do full system testing to make sure that we perform as expected. The payload system performs as expected at the competition. So some of the test results. So this is from the Canon camera. So here is a QR code that we made ourselves. Our next image is the flight target that we have. So it's a relatively small white circle with a blue line. Pickup targets on this side. Resulted from here. You can see fairly clear image in the beginning, but what we learned from our first test flight with the Teledyne was that the focus ring on the camera was shifting due to vibrations. So one of the lessons learned from that was to take the focus ring. So those things were all from the same flight. In terms of data processing, we initially aimed for automatic detection, localization, and classification, but because of lack of experience and expertise, we decided to automate the manual post-processing instead. So here is our software showing an image with a target, and all the software does is it crops the target out of the image for manual classification.
Based on that, we can calculate where the target is.
Some of the lessons learned from our payload. We have found from both last year's competition, the Unmanned Systems Canada competition, as well as our test flights, that flying with multiple sensors, we can overfly the search area only once and get coverage many different times at different ground resolutions and angles of view. This reduces the amount of times we have to overfly the area, meaning we have more time for post-processing. So that's our strategy here, and that we should find additionally, having multiple cameras adds in redundancy. If one of the payloads fails, we can still fly. So one payload failure at the flight line is not a no-go. So it's one of our final validations for our system. We wanted to integrate all of our fields the airframe together and attempt what was considering a full mission simulation. So essentially we had some of our members develop a mission plan in secret containing an operational area, search area, target waypoints, things like that, similar to exactly what we're giving here at this competition, and we tried to carry it out. Essentially, our results were we were able to achieve waypoint navigation with similar accuracy to what we showed at the Unmanned Systems Canada competition earlier. We had 8 minutes of flight time within the search area. Of the 5 targets located within the search area, we were able to locate 3 of them. Another task which we accomplished was the in-flight retasking, and we were able to geolocate the 3 targets which we didn't locate classified to within 80 feet of accuracy. So as a lesson learned, we did miss the off-axis target as well as 2 of the targets within the search area. So our lesson learned here was to really put a lot more consideration into our flight planning to make sure that A, we have full coverage of the entire field, and that B, we're doing this reliably. And this was also drove part of the decision to include the extra payload imaging systems relative to what we had indicated on the journal paper.
Right, so as a result of the flight test, we basically logged almost 12 hours for the entire generation of UTX planes. And our latest plane here is over 7 hours with 1.5 hours on our current payload. And so today for expected mission performance, we're going to be attempting, we're going to be doing the autonomous flight and search area primary tasks, and then we'll be attempting secondary tasks such as actual intelligence, off-axis access, targets, and emergency. So, most important thing to note here is that every subsystem has passed at least 1 full mission test. It's important that we don't fly at all if we haven't tested it.
So we do have a series of pre-flight checklists. For the sake of time, I'm not going to go through every element bit by bit, but we do have a written checklist that we've been developing over the last couple of years of lessons learned. I invite you to come see it when we do our 5-minute review. One thing I want to emphasize is, with the exception of the payload, so the computer vision functionality, each one of these criteria is a go-no-go decision for us. So if we do fail any of these tasks, then we essentially do not allow ourselves to fly unless we can correct the issue. As we alluded to earlier, we also have a full risk matrix and mitigation strategy. So we have several procedures. Again, for the sake of time, I won't go through every single one. But just as an example, as we are remaining within line of sight for this competition, if we lose telemetry link to the ground control, or if we lose GPS, then we will, if we cannot establish the connection, then we'll be forced to take RC control within 30 seconds. And again, we have the full analysis here if you want to come see it in the minute review. And then finally, we have several post-processing procedures for after flight. So essentially, the first step is just to taxi back to the GCS. Then we will remove power from our propulsion batteries, power down the vehicle. So our pick socket has a separate power supply, so we'll do that. We'll remove data logs from the computer vision or from the imaging hardware, and then we will post-process it ourselves to find issues or missed targets in the data which our automated script is trying to find in the photographs. And then finally, we will submit all of our results to the judges in the electronic format as required. And just for your interest, here's our tentative mission plan for tomorrow. We do actually have 4 separate plans for 4 different directions depending on the wind, so we prepare ourselves for a variety of different environmental conditions as well. And that concludes our presentation, so thank you very much, and we welcome your questions now.
Hello, we are the University of Alberta Aero Robotics Group. I'm Cindy Xiao, I'm the imaging lead of the group. I've been with the group for 4 years now.
I'm Andrew Josie, I'm the airframe lead of the group. I've been with the club for 3 years now.
My name is Jay Augustine, I'm the safety pilot. I've been in the club for 3 years now as well.
Introduce the other members back here. We have Jonathan Cook, who will be assisting with airframe, one here, who will be assisting with the autopilot, and Sebastian Werner, who will be assisting with both autopilot as well as airframe repairs.
All electrical engineers.
Somehow.
Losing points already.
Alright, so just for an overview of our presentation, first we're going to go over a brief system overview of both our air and ground systems. Next we'll go over a review of our expected performance, both historical performance as well as the expected tasks that we're completing at this competition. After that, we'll go through an overview of safety measures, mitigation, as well as ground station logistics that we bring to our operations. So we'll start with the system overview.
So I'll start with airframe. So we have a modified factory-made airframe that was from an online retailer, Coffee King. The airframe is called the EPP FPV. It's made of expanded polypropylene, reinforced with different structures that are carbon fiber, basewood, and PLA plastic from 3D printing. It's a lightweight, modular, durable airframe. Weighs about 2.89 kilograms, so it's very lightweight and very modular as well. It can be disassembled very quickly, reassembled quickly. It's been our main airframe for now 5 different competitions, both at ABSI and also at Unmanned Systems Canada. And this is our 4th iteration of the plane. It's going to be hand thrown, hand launched, and have a belly landing. There is a bit of a risk, as always with the hand launch, having the propeller on the back there. I'll be the launcher, and it's never been an issue in the past having the kind of topology there. The propeller's far away from my arm directly. As well as, that's our overview. For the modifications, we've reinforced this airframe. Since it is a factory-made frame that was made for FPV flying, we modified it for a UAS. So for this, we're actually just focusing more on the modularity, making sure that all the modularity is not reducing the repeatability and the performance of the system. So we modified our tail mount to make sure that we always have exact, precise assembly, as well as reinforced our motor mount, because in the past we had hard landings and the motor mount actually ripped off, which could be dangerous. So we made sure that it was reinforced with stronger wood, better adhesive, as well as improve the actual performance in air by extending our vertical stabilizer, as you can see on the red tip there, which significantly improved our stability during flight. For controlling all our systems, our actuators such as the motor and servos, and as well as our RLC antennas, we have just a solid modular unit, our avionics board here. It's on top of a oxygen board here. It's equipped with our safety switches at the very front for disengaging our motor, our autopilot system, our imaging system, and our servos. In the middle there, right here, and as an image you can see here, this is our autopilot. It's a Lisa MX microcontroller for controlling our flight. And further back, we have our Odroid U3, which will be used for image processing on board. For telemetry, we'll be using an XB transceiver at the front here for 900 megahertz, which will be providing us all the information down here in the station. To power all of this, we're using 2 lithium polymer batteries, 4-cell, totaling 10,000 milliamp hours. One other thing to mention is, as a modular unit, we are able to actually take this out if there's any system issues or any kind of troubleshooting we need to do. We're able to completely pull out the board and reinsert a new PERT board with all the electronics that will be working. For autopilot, we'll be doing fully autonomous navigation, but with a manual takeoff and manual landing. As you can see here, this is a screenshot of Paparazzi. This is the graphical user interface that will be provided during flight at ground station. It'll be providing us real-time information, real-time telemetry over attitude, altitude, GPS location, as well as overlaying the moving obstacles coming in from the interoperability server, as well as the flight boundaries and our flight plan. During this time, we can actually interface with it and change our request of flight at any time. So if there's an emergent task we want to try to achieve, we will be able to modify our plan.
So I'll be going over our imaging hardware and software. So on board, as I mentioned, we have a single boardless computer, the Odroid U3. This is connected by USB to a consumer point-and-shoot camera, the Canon PowerShot 8100. So it's a fairly lightweight and cheap module that we just control by USB. So once the images are captured by the camera, they're then tagged on board by some custom software that we bring from Odroid with the telemetry that's Lisa. All of that is then sent back down to the ground by 2.4 gigahertz Wi-Fi link. Once the images are received at the ground, we have a human operator sit at the ground control station and manually mark objects of interest. They're assisted in this by custom software delivered, which will assist them in geolocating the objects based on the data that was transmitted. Now I'll be going over some of our expected results. So with our autopilot, again, we're able to achieve reliable, stable waypoint navigation during flight. This is a screenshot of both our flight plan as well as actual path of travel. Just a few months ago, unmanned systems can't seem to be competition. So here you can see in yellow the flight patterns, green are the search area patterns, and blue right here are the waypoints that we plotted for our search area. The blue lines here represent the actual path of our ground. So you can see we have a reliable search pattern at reliable. With the achievements of our imaging system, we plan to achieve the image localization task up to the threshold of within 100 measures. This image right here is actually a screenshot from our ground station image analysis program. At the field we fly at, we've actually got a points file of GPS locations of landmarks on the field, such as cinder block. So this line right here from the X to flight represents the amount of error that we're actually seeing in our geolocation. So the X right here is the actual location of that cinder block. And in this particular situation, it's about 66 feet of error. Now this image is flying flat level. We do see that when we are flying with an angle to our aircraft, we see more aerial geolocation. Or we are able to achieve within, again, 150 feet of localization error. So just as a summary of the expected performance for the primary tasks, so for the autonomous flight, we do plan to do everything automatically except for the takeoff and landing. For the search area task, again, pressure localization, as well as pressure classification of QRC and pressure for secret message. We'll see if we can find all of them. But our imagery is fairly clear, and we are able to classify targets, characteristics, again, with a human operator. We plan to achieve 3 secondary tasks, first being the actionable intelligence. So we do have a 2.4 GHz Wi-Fi link. We are able to get images transmitted down to the ground and classify objects while in flight. For the emergent target task, again, we are able to replot our autopilot path quality plots. So there will be communication between the autopilot operator and the imaging operator when a derail should occur. In case we do need to rescan for interoperability, we plan to meet all the basic requirements, as well as the download display of obstacles and the update of targets to the interoperability server. We do not, however, plan to do either manual or autonomous avoidance of targets, as our autopilot is not fully equipped for that capability yet. We haven't done enough testing in that aspect.
We're going to talk a little bit about the different safety measures we have in place. To start off, we're going to talk about crew training. Each time we have new members who join our club, they go through our own safety training courses that we have set up. This includes lab safety, safety around the airplane, safety with handling batteries, that sort of thing. In addition, we have them take a WIMIS course as well as construction safety course. This all comes down to ensure that all of our crew members and people who are here operating the airplane operate it as safely as possible. In addition, we have pilots, safety pilots, who will take manual control of the aircraft for landing and takeoff, as well as in case the autopilot needs to be overridden. These pilots have been trained by a local RC club, which has plenty of experience. In addition, being in Canada and flying UAVs, we have a restriction in that we need our pilots to take a private pilot ground school course. So our pilots do that as well, and they are familiar with the relevant Canadian aviation regulations and requirements and the rules of flying UAVs. In regards to the actual flight, we do also take some more precautions when performing flights. The first thing is airspace coordination. We make sure that when we are flying, we filed a notice to airmen, to other airmen, with our flight information center. In addition, we contact local aircraft control, all to just mitigate any risk for in-air collisions. And also, also, we make sure that all ground we're flying over is a private property or public property that we have gotten permission to use, private property as well, permission to use. And we make sure we do not fly over any other individuals who are not involved in the operation. In addition to all that, before we go out flying, we also do weather checks, and we also do checks of our airframe to make sure that it is fully functional. At the flight line, we do have checklists for making sure everyone knows their roles, their duties, and that the airplane is fully assembled and we do not end up with any issues during flight. We also have with us flight protocols and procedures for different events. A runaway event, there's a set standard of what to do. If we have failure of links, there's a set protocol in place. So we always have that with the flight commander so he knows exactly what to do. In addition, we also have field emergency procedures. So if someone gets hurt, where's the nearest hospital, what to do. So we always make sure that safety is a prime concern with us. Our actual airplane itself has a couple of safety measures built in. It is an electric plane, so it does have a high spinning prop. So we do have a motor kill switch in the front, and we make sure that the motor is always killed unless we are going to, just before launching plane or doing a prop test. And when doing that, we make sure that no one is in the line of the prop, and just so we mitigate any risk for injury. As well, for help, as well, we also have some fail-safe modes built into our autopilot system. So this includes if we lose telemetry link, it will automatically return to home. If unable to do so, it will terminate the flight within a set amount of time. If it flies outside of the boundaries, it will try to return to home or terminate the flight as well. So we make sure that our airplane is always under somehow our control, that we can make sure we terminate the flight when necessary. So these three aspects all together make sure that we operate safely. Since I've been with the club, we've never had any real incidents. Yeah. Do you guys have any questions?